here. So you can see the outline matching our agenda. So the next one here is the 02 AutoML. So if you like, just click with me here into this folder. And we always have a 00, which is kind of just an overview notebook, which will open up and introduce the section. And then we have the different notebooks here from 01, 2, 3, etc., which we will execute one by one. All right, so let me quickly open the overview notebook. And this really is just a quick introduction to the topic here. So not much code in this one. All right, so talking of automated machine learning, or sometimes even a one-click AutoML, it's a way to automate many of those manual machine learning development workflow steps, from the data exploration, data analytics, to feature engineering, to model training, model tuning, and even. And we will see throughout the workshop there's quite a lot of work involved in doing that. So wouldn't it be really nice if we would have a service that is automating all of that for us? And that's the idea behind automated machine learning. And Amazon offers a service that is called SageMaker Autopilot. And it's basically a capability and part of the broader SageMaker family of the machine learning platform services. So Autopilot got released at last reInvent back in December. And what we can do with Autopilot, which we're going to see here in just a bit, is we can point the service to a sample data set, which we put into F3. And then Autopilot will grab the data, will have a look at the data, and will, first of all, run some analysis, and we'll say, okay, how's the data quality? Are there missing values? How many rows do we have, etc. And given the data set, Autopilot can decide what problem we're trying to solve. So you would just point it to a single column in the tabular data set and saying, I want to predict, for example, the second column in this data set, which might be, in our case, it's actually a star rating of a customer review. And SageMaker Autopilot then discovers, well, okay, so this is a classification problem. And SageMaker Autopilot also knows which algorithms perform best on classification. So it picks algorithms, it looks at the data, it runs feature engineering. It also starts training the model, tuning the model. And then at the end, it shows you with a list of best model candidates to solve this problem given your data set. So really powerful. And also it documents everything and even generates custom Jupyter notebooks that you can take as a baseline and can further optimize and tune the model code. So really exciting. So let's see how this works. And I'm just gonna run this quick Jupyter magic to close my kernel here. Close that. So let's start by actually looking at the data set and doing just a very easy data preparation. So I'll open up the 01 prepare data set notebook. And because I'll talk a lot here, I just do a cell run all, which kind of lines up all the executions in the background here. So I can focus on explaining what we're doing. So feel free to just do the cell run all as well. All right, so for the data set, and this is the same data set we're using throughout the whole workshop today. We're using the Amazon customer reviews data set. And I said in the beginning, we're gonna build an NLP, a natural language processing model based on BERT, the famous BERT family of models. And what we use as the data set here, and which you can also use, it's a public data set coming from Amazon, the customer reviews. So I assume many of you probably have been at least once in their life, maybe on Amazon.com. And whenever I go there and I look for a product which I want to purchase, look at the review section on the top right? Do other people like this product? Is there anything I should know before I buy it? How many stars did the product receive? And Amazon published this data set here, which consists of over 130 million, I think it's even over 150 million customer reviews, which consists of a lot of information, marketplace, product IDs, etc. And especially interesting for us is the review text and the actual star rating. So the goal of our machine learning pipeline today is to train and deploy a model which we can feed with any review text, like, I super love this product, it's a great product, or it's the worst I've ever seen. And then the model should classify which star rating it is. So if I say, I love this product, the model should return a 5, right? 5-star rating are the best and 1-star rating are really bad. So that's the goal. And here's a lot of information how you can actually use the data set. Here in Jupyter, we have the schema. So it consists of the marketplace, which is a 2-letter country code. For example, we're using the US. So it's English US reviews from the US marketplace of Amazon.com. There's also a couple of multilingual reviews if you want to play around with the different languages. There's customer ID, review ID, product ID, the product parent identifier, the product title category, the star rating. If it's been helpful vote, so the number of helpful votes for a given review, the total votes, whether it's part of a program called Vine for reviewers, whether it's a verified purchase, the review headline, and then actually the body and the review date. All right, so what happened in this notebook now is we're setting up our Jupyter notebook here to interact with the AWS services. And we're doing this by importing a couple of SDKs. So Boto 3, for those of you who are not familiar with AWS, Boto 3 is the Python SDK to interact with AWS services. And then there's also a dedicated Python SDK to interact with SageMaker directly. And probably the majority will know Pandas to work with data frames in the Pandas library inside of the Jupyter notebook. All right, and with those imports, we then define a couple of environment variables here. So for example, we're saving the current session we're operating in with SageMaker. We're also pulling, again, our F3 bucket into this bucket variable. We're saving the current IAM role, so that's team role, into the role. And we're also polling for the region we're operating in. All right, so that's really just the basic setup. And then we're starting here by downloading this public review data set. And the way it is organized is the data set is split into the different product categories. So there's a TSV file, and TSV is a tab separated file format. So instead of comma separated here, it's with tabs. And you see one file for each category. And because we're pulling this down here locally, we're just making sure we're operating on a smaller data set. So we're pulling in the digital software reviews, which is really just a smaller category with a smaller number of reviews in it. All right, so we're using the AWS CLI. So whenever you see this exclamation mark in AWS, so the exclamation mark executes bash terminal CLI commands on this instance. And we do have the AWS CLI installed, pre-installed. And this is why we can use this. And we're querying the F3 and we're doing a copy command, pulling in the public TSV file into a local data folder. And then we're using pandas to read the TSV file. So we're reading this with a CSV saying it's actually delimited by tabs. And then we can do a data frame shape. So we see the size. So we see it's roughly around 100,000 reviews in this category. And we can have a sneak peek. So here you can see how this data looks like. So we have the marketplace, which is US. Just random customer IDs, so don't worry, it's not the real customer IDs, it's just a random identifier here. The review IDs, product ID, parent for the product, the title, the category, and you can see here the star rating. So we're gonna work a lot today with star ratings and the review text. So here you can see, for example, this review was a 4-star rating. And if you scroll all the way to the right here, you can see the review text. So far, so good. And I think, yeah, that's actually a pretty decent with a 4-star rating. All right, so this is the data set we're gonna work with for pretty much the whole day. Then let's actually do some quick visualization here. So we're using matplotlib to just do a quick visualization of our data set and do a breakdown here by star rating. And what we can see is that the majority of reviews in this product category are 5-star ratings, and then followed by 1-star ratings. And I guess that's kind of human nature, right? So we always tend to give a review when we're either super excited and we want to share the excitement, or we're really disappointed and want to make sure like others are not buying the same product or are aware of anything that that we didn't like. And there's less reviews really for the 2, 3, and 4s. All right, so this is okay for like human behavior. But if you want to train a model, obviously training a model with unbalanced data is not yielding to good results, right? Because our model will learn that approximately, I think it's roughly like 60% of the data are 5 stars. So the model, if we train it on this data set, will learn to predict more 5 stars just because of this imbalance. So what we want to do next is just an easy data prep step is actually to balance the data set. And we're just using some simple scikit-learn utilities here to actually cut down the number of reviews to the number of the smallest one. So the 2-star ratings, I think in this case was the category with the least number of reviews. So we're basically just cutting down all of the categories to this limit. And this is really just a very simple hack here to balance. Obviously, there are more sophisticated ways to do this. So now we can see we have roughly 7,000 reviews per category. All right. We can have a quick sneak peek into the data that it's still looking fine. So the data looks okay. We haven't messed anything up here. And then in the next step, what we do is we're splitting data into a training, validation, and test set. So obviously, when you train a model, you want to make sure you have a holdout data set, not to give any information to the model about future data or about any holdout data, because we want to have a real test how the model is performing on unseen data. So what we're going to do here is basically keep 90% of the reviews as our training data. You want to have the most you can for training, but then hold out 5% for the validation, which we basically check after the model training runs, and then have another 5% test data to really just do a final check after we've done with the model training to see how it's actually behaving against unseen data. All right, so we have the split of the data. So just scrolling down here. And then next, what we're gonna do is we're limiting the columns of the data set to just star rating and review body. So you could pass all of the information to autopilot and have the service figuring out correlation between the columns and the features. In our case, we want to make sure we're only influencing the star rating by the review text. And we don't want to have influences like if it's a verified purchase or if the reviewer is part of a program influencing the star rating. We want to train an NLP model, and we really want to make sure the only influence is really the review text. So in this case, in our case, we limit it to those 2 columns. And we can see here we now have star rating and the actual review text. All right, looks good. And as a next step, Autopilot as a service expects the data to be in S3, and it also expects it to be in a CSV file format. So what we're doing here is we're writing out the data frame that we just used to kind of wrangle the data. We're writing this out into a CSV file. And one thing we have to keep in mind for Autopilot is it expects header information. So in this case, we're also keeping the header information, so the star rating and the review body as a title for our columns as the header. And then we're uploading the CSV file in our S3 bucket. So we're doing this here with a session upload. And you can see here that we're now stored it in our S3 bucket. All right, we do have another service we want to quickly show you, which is Amazon Comprehend. And Comprehend is a fully managed AI NLP service. So we can use Comprehend to give us those predictions right away. And we're going to show you how you can do this. And also there's an option to fine tune the NLP service to a specific data set. And so in this notebook, we're just preparing the data and for both of those services, because Comprehend as a fact also requires a CSV file with the data, training data, but without the header information. So it's just how the services work. So we're using the same data frame, writing it out as a CSV, but in this case, without the header information. And then we're also uploading it to the comprehend service. All right, so we do have 2 training data files now stored in our S3 bucket. And what you can see here at the end of this notebook is we're using another Jupyter magic, and we're doing the %store. And store lets us save a variable that we created in this notebook and persist it in this Jupyter instance. So when we open up this next notebook, we can actually retrieve this. So it's really just kind of a local key value store part of this Jupyter instance here. So, and we're using this intensively throughout the workshop. So at each notebook, you will see at the end that we kind of storing variables, and then picking up in the next notebook, we will retrieve those. All right, so this was a quick data preparation here. Let's close this, and let's actually start the autopilot job. So I click here in the 02 train reviews autopilot. And I quickly introduced autopilot. So it's an implementation of an automated machine learning service. And what makes autopilot in its way unique is it really is what we call a white box approach, or a very transparent approach to machine learning. So it will run through all of the 3 phases of data analysis, feature engineering, and model tuning, but it will also document all the findings. So you will see exactly what happened in the data analysis, what are the results, what are the suggestions for feature engineering, and you can also see all of the model training runs and tuning runs with all of the parameters the service chose. So let's actually get this started. This will run for a little bit. So let's do a cell run all on this notebook. So the notebook will approximately run for 20 minutes. So just start the notebook, line up all the cells, and we will see how it progresses. So yeah, let's have a look what's needed to actually start autopilot. Again, we're starting by pulling in the SDKs. So variables, and also pulling in as a dedicated SageMaker client. And here you can see how we're using the store retrieve. So we're doing this Jupyter magic store-r, and we're retrieving the location of our training data that we just prepared with the header information. So here you can see it's our S3 bucket. And here's the CSV file. So we do a quick AWS S3ls show command here. And what we're doing next then is setting up autopilot now. And a first step here, we're just defining another subfolder in our S3 bucket where autopilot will output all generated code and notebooks. So let's just call this model/autopilot. And this is really just creating a location for the service to write out anything. Then let's define the actual job. So we can tell autopilot how many model candidates we want to actually have returned. So in this case, we just say, give us 3 model candidates, right? You could scale it up. You can say, give me 10, give me 100. You can go up to 250 as of now. So in our case, we want to keep the execution time low, so we can actually see the job finished. So we keep this to 3. Obviously, if you have more, the job runs for more time. Talking of job runtime, you can limit the job. So if you want to set a hard limit, you can, for example, say the maximum runtime per training job in seconds. So in this example, we just put it to 600 seconds. And the overall job, not just for the training, but for the overall autopilot job, let's limit this to a maximum of, in this case, 3,600 seconds. So you can give hard limits to when the job should just stop, right? All right, then the input configuration is really just pointing to our S3 bucket, which has the training data. And the only information in addition to the training data we're giving autopilot is saying which target attribute we want to predict. In this case, it's the star rating. And then we also gonna give it the output S3 bucket. And this is really the pretty much the configuration we have to do for autopilot. So we can start the job now. So for that, we just create a unique job name. So we're just calling it AutoML-DM, and we're creating a timestamp to have unique job names. So this is going to be our job name here that's created. And then we can, on the SageMaker client we created in the beginning of the notebook, we can call create AutoML job. And here we're just passing the job name, the input configuration, which is pointing to our training data, the output config, which is just giving it another 3 bucket to write out everything, the job configuration, which has the number of candidates and the maximum runtime settings, and as always in AWS, give it permissions. So this is the role that has enough privilege and permission to actually execute this. And this programmatically created the autopilot job in the background. So what you will see in our workshop today is that we're pretty much everything doing programmatically through the Jupyter Notebook. In many cases, you can also do this in the AWS console via the UI. Just to keep us all like in a single place, we do pretty much everything in the notebook, but just know that you can do a lot of things today also in the UI. So for example, Autopilot is integrated in the new SageMaker Studio IDE, which is kind of a nice UI and interface, which also has those autopilot jobs and the experiments it starts visualized. All right, so let's see what's happening here. So in the next cell, we're watching the progress of our autopilot job. So as I said, it runs through 3 stages. So the first, it analyzes the data set. And this is where my cell is executing. So as I said, you will see that those notebook cells will run approximately 10 minutes each. So I'm still here in the analyzing. And we are looping over this job status to see if we're still in that phase. So don't stop the notebook, don't touch it once it's running. It will execute, if you do a cell run all, it will execute cell after cell. And here we're really just looping and showing you in which phase we're currently in. So just keep it running. So I'm just analyzing the data here still. And I just scroll down to show you what's coming next. So once the analyze of the data is done, it will actually already generate the notebooks that we will see here in a bit. So it generates 2 Jupyter notebooks, one for the data exploration, which is basically the findings of this data analysis phase. And the second one is a candidate definition notebook, which will have executable code and basically shows you how the service builds those 3 candidate pipelines with a model code. So really super interesting to see. Once the phase is done, it will start with a feature engineering. So Autopilot will take its own suggestions and actually apply them to the data set. So it will do some feature engineering, and it will also then start model training, and it will run model tuning jobs. And then after this, it will show you the candidates and how the candidates are performing. And what you can do is then actually explore and look for the best candidate in that list, and then deploy that candidate as a real-time endpoint. And the notebook will all do this for us. So that's why it takes roughly 20 minutes. But once it's finished, we will have the model that Autopilot discovered to be best performing also deployed as an endpoint. And we also run a couple of predictions here on this endpoint. So let's keep this notebook running. Don't hit stop or anything. Just let it do the job. What I'm showing you in the meantime, because as I said, once it's done with the first phase, it will generate additional notebooks. And we've executed this job before and downloaded the notebooks so we can actually see how they look. So if you go into the folder structure here, you will see a folder that is called notebooks. And if you click in here, you will see 2 sample notebooks, and those are the outcomes from this autopilot job. So if you open the first one, the data exploration, which is actually the bottom one here, and don't execute them because they are from a previous job, which is not present in your demo account. So it will not fully run in your environments, but really just see how a sample output looks like. So I'm just really looking at it. I'm not running this one. So once Autopilot takes the data set, it looks at the data and it sees here, well, we have 31,000 rows in this training data set, and we have 2 columns. And we also told Autopilot that star rating is our target column for predictions. And as you can see here, SageMaker Autopilot automatically found out that it's a multi-class classification problem, and also found the 5 classes, which is basically our star review categories, so 1 to 5. Okay, so in the next step, it also gives us a preview of the data, so we can see the data here. And then it runs a couple of analytics. So we will see, for example, the percent of missing values. So in this case, our review body has very low 0.04% of missing values. And it will do some statistics here on the data set, looking into categorical features. It sees that we have a field with a text, basically text strings. And it runs also some here, the mean, median, min, and max values across the category that we want to predict. So pretty neat for an automated notebook. But even more interesting is the second one. So if you want to have a look at the candidate definition notebook in this folder, and this one is now really exciting because this one is giving you all of the code to reproduce the steps that Autopilot now runs automatically. So you could basically start the Autopilot job and then go drink coffee, go have lunch, come back and see the results. And you have an executable notebook code, which you can take as a baseline. And if you decide you want to actually optimize the model further, change a little bit of the code, you can take this as kind of your starting point and have already kind of a good start. So if we look here in this notebook, and it's really, really long. So if you want to scroll down, you see there's a lot of input. So Autopilot documents all of the environment. So here, the Jupyter versions, Jupyter Core, Conda, SageMaker. And then it downloads all of the artifacts that it created. It has here the job name, the job configurations. You can see here this F3 bucket that we defined. And pretty much all of the settings, the role information. So this one is really, once it's based off your job, ready to be executed. It pulls in all of the needed libraries. So for Autopilot, there's a couple of dedicated libraries here, AutoML. And then we can see here the 3 candidates. So we told Autopilot to give us 3 model candidates. And we can see them now here. So they are called DPP, which is data preprocessor. That's just a naming convention, 0, and -XGBoost. So in this first model candidate, DPP contains the actual Python code to do the feature transformation. And it also combined this with the XGBoost algorithm. So it picks an algorithm, it applies some data transformation strategies, and you can actually see what it is. So it produces this kind of a narrative text here and saying it used the multi-column TF-IDF vectorizer as a data transformation strategy. And if you hover over this link, you can see it's pointing to SageMaker scikit-learn extensions, which is basically a SageMaker extension to the scikit-learn libraries. So you can see here all the code that has been used. It's here public on GitHub. And it also applied the robust standard scalar from the scikit-learn extensions. And it combined it with the XGBoost algorithm. And here's the code to actually run this pipeline on Autopilot. So you can see here it's pulling in the DPP code, that's the feature transformation code. It sets up the infrastructure for AWS, so defining an instance type, an instance count, etc. And if you scroll down, you see here, it does this for all 3 candidates. So here's the next one, which is also XGBoost, but actually has maybe a different set of feature transformations. So here it also applied the robust PCA for principal component analysis. So that's a little bit a different pipeline. And then you also have the third one here. And in this case, it picked 3 times the XGBoost. Depending on the data input and the problem, sometimes it picks 2 or 3 different algorithms. So it's also optimizing across. So in this case, it found that XGBoost is probably the best one to handle this. And yeah, so executing, so it's all the code in here. Also for the step of the hyperparameter tuning, you will have the code in here. So here it defines all of the hyperparameter and the ranges that make sense for XGBoost to find an optimized value. And if Autopilot would have chosen like 2 different algorithms, let's say linear learner, which is another SageMaker built-in algorithm, it would have added another set of hyperparameters to tune for that specific algorithm. So it can do the multi algorithm hyperparameter tuning. And you see here all the code that is needed, so you can go in and change that and tune that and do different settings if you want to further iterate over the results from the job. So, and you see I'm still scrolling down here, so it's pretty detailed, this notebook. Tuning job results, so it also has the analytics code to actually display the results in here, linking it with the feature pipelines. And in the end, it has the pipeline model deploy. So you can also deploy the best performing model straight into production on AWS with this sample code. All right, so yeah, pretty detailed notebook that is auto-generated by this job. And just to give you a quick look, so if you go to the generated module section and the candidate data processors, you will see the samples of those Python snippets. So for each pipeline, so for example, the dpp0.py, this is the actual Python code that Autopilot generated and executed to do and run the feature engineering on this data set. So here you can see all the things that got applied. So you have the code, the Python code, and you have the notebooks actually to reproduce whatever Autopilot is doing for you. All right, so let me quickly check. I guess the notebook is still running. As I said, then it will probably run for 20 minutes. So let me see, the analyzing data has been completed. So this stage is finished. And I guess mine is probably now, yeah, mine is running in the feature engineering. So yeah, keep this notebook open because it will deploy an endpoint later. And we want to actually reuse the deployed endpoint and test how this Autopilot model is performing. So I'll keep this one open. And probably a good time here to quickly check in with Chris if there's anything important we want to mention here, maybe any hotspot questions regarding Autopilot.
A lot of questions around the feature engineering. You know, right now, Autopilot is a relatively new service, came out just this last December. Lots of customer feedback has come in from from the AWS customers. It's pretty primitive feature engineering, but you can actually see and I think Ansha showed the candidate notebooks, you could see some of the feature engineering happening. And okay, yeah, Ansha, I need you at some point here soon to give me some more of the instances. Let's talk offline, but when you're ready to break, we've got about 10 or so people that are waiting for instances, but.
Let's just do the last one of this section, then we can break for 15 minutes, give people time to visit the code here. And I think you just muted me.
I tried to mute myself and I muted you, sorry.
Yeah, so let's just run the third notebook in here. So, and then we can break for 15 minutes and give people time to revisit the code and the others to catch up. So let's just do the last one of this section. So I'm gonna open the 0-3, the train reviews comprehend. This will also run for approximately 20 minutes. So let's just get it started, and I'll quickly explain what it does, and then afterwards we can have a break here. So in this one, I do a cell run all because I tend to talk a lot and forget to execute the cells. So let me double check. That should run in 1 in one run. Yeah. All right. So yeah, maybe just do the same if you want to just get the code lined up and execute it in the background. So another option we want to show you here is a service that is called Comprehend. And I can actually show this here in the UI in the console. So I'm back here in my AWS console, and you might just want to quickly watch so you don't have to flip around with the screens if you don't like to just really see what I'm showing here. So Amazon Comprehend is a fully managed service by AWS, which gives you natural language processing and text analytics out of the box. So you have an API which you can integrate in your applications without even having the need to actually train a model. So this is super easy if you just need, you know, a well-trained NLP model, general model that is handling a lot of use cases, and you don't want to train anything specific. So, and you can see how this works if you click here on the real-time analysis. Actually, in the background, we have this trained NLP model. And here we're just using straight away the API. So here's the sample text input. So Amazon.com is located in Seattle. So it's really just kind of a press blurb. And I can hit the analyze button here. And this text is sent to this Comprehend API. And we can see here, it already does entity recognition. So Amazon.com organization, Seattle, a location, July 5th is a date. And you can see the confidence scores, etc. It also does key phrases detection. It detects the language. So this is English language. It detects the sentiment. So pretty neutral. This is just kind of a press text here, syntax, etc. So this is right away. You can use it out of the box as it is. Just integrate basically into your application. So here's a sample how you can have the API calls set up and how the API response looks like. And what we show you now in this notebook that we just started is how you can fine-tune this service to a specific data set. So let's say you want to leverage the power of this pre-trained model, but actually you have a different domain. In our case, we want to give very specific customer review text to this model. And we don't want to have entity recognition. We actually want to have the star rating classified. So what Comprehend offers you is also do something called train a custom classification model. And this is what we're doing here. So what we've started in the notebook is here, a custom training job for Comprehend, giving it our training data. If you remember in the first notebook where we prepared the data, we had one CSV for Autopilot and one for Comprehend. So we now started programmatically from the notebook, which I'll show you in a second, this job which points to this CSV file that we created and actually retrains the model, or basically saying fine-tuning that model, not retraining from scratch, that would take forever, but more fine-tuning to our specific language and the customer reviews, and also telling it that we actually want to predict those classes. And this will take some time here. So you see it's currently submitted and it's training. And I quickly show you back in the notebook here, back in Jupyter, how we did this. So again, pulling in all of our SDKs so we can interact programmatically with AWS. And again, everything needs to be permitted. So we do have to set up again some roles. And obviously you would set up those maybe separately, or you have people in your team that taking care of maybe roles and permissions. In our demo workshop, it's us. So we have to do the job of the data engineer, the security engineer, and the machine learning engineer and data scientist. So what we're doing here is just programmatically creating those policies and permissions that we need to execute it from the notebook here. So don't bother too much if you're not into the field of setting up security policies. If you are, feel free to have a look how it's done. Otherwise, just scroll quickly through. We're creating a policy, we're creating an IAM role. So we're giving access to Comprehend and attaching the policies, making sure it's allowed to access the S3 bucket where we store the training data, attaching those policies to the role. And then at one point here, we're ready to start the Comprehend job. So to start this, we're defining again an F3 bucket where comprehend stores the outputs. So this is done here. So it's just another subfolder in our bucket. And we're also noting here our role that we just created. And then we can actually, on this comprehend client, which we pulled in through the Python SDK, we can call create document classifier. And in this create document classifier, we're giving it a name. So this is just a random name we're constructing here with an ID that we're creating again from the timestamp. We're giving it the execution role, so giving the privilege and the permission to access the data and the service. And we're pointing it to our training data. And we're also pointing it to a bucket where it can store all of the outputs. And this is basically setting up the training job. And now you see again, this cell is looping. So again, this notebook will run for another 20 minutes probably, or even a little bit longer, maybe 30 minutes. And it's fine tuning the comprehend model. So you can see here custom classifier submitted, and it's currently in training. So again, this cell will stay running, and we're looping over the status to check once it's finished. So just line up all of the cells here with the run all command and keep the notebook open for now. And once it's done in 20 minutes roughly, we will see the results in here. And then we will also show a little bit of a confusion matrix here. We will deploy an endpoint, and then we can also run predictions against this endpoint and see how the comprehend model endpoint is performing, how good it is in predicting our star rating classes. All right, so this is what happened here in the notebook. As I said, don't stop the cells, just keep them running. They run for 20 minutes. And you can check in here, or you can check now in your AWS console in the comprehend. So whenever you're looking for a service, you can click here service and then just type it, so comprehend. And then clicking on Amazon comprehend will take you to that service site. And then here under the custom classification, if you scroll down, you can see that we have a model that is currently a multi-class and it's in training status. So this will run for a little bit. So it's time, I guess, for a break. So maybe give people 15 minutes so I can work with Chris in giving the rest of you folks this demo account and catch up here. And the rest of you have a look how your autopilot is performing. So mine is still in the feature engineering. And you can see how comprehend works. And you can also, if you like, run a couple of real-time queries here against the built-in model if you like. Or just grab a coffee, grab a tea, grab some water. And let's come back. Let's give people 15 minutes from now. So Chris can help me in translating to Pacific time. I'm here in German time zone. So.
All right, let's resume at, we're doing 15 minutes, did you say?
Let's give 15 minutes. It's been a lot of content, and I know it's going to be a long day as well, so let's do 15 minutes.
Okay, so let's do 17 minutes. Let's resume at 9:55. What is it, AM? AM, PT. Ansha, hit me. I'm going to hit you up on the other Slack channel, our private one, to get the other folks set up.
All right, so we're back from break. Hopefully everybody had a chance to maybe get some fresh air, get a coffee, get a tea, get some water. Got time to catch up here and have a look at the notebooks. Let me get set up here again. All right, so I saw a couple of you asked what is actually happening right now with those two notebooks. What are we actually doing? So what we want to show you here in this section is really before we start building manually this machine learning workflow with data ingest, exploring the data, preparing the data, etc. We wanted to show you two ways to actually use automated machine learning that takes a lot of those steps and runs them for you. So one service that we wanted to show you is the SageMaker Autopilot. And this is the second notebook we've been running here. So those are really two services that give you out-of-the-box capabilities to offload those tasks from you. And after this section, we will jump into the manual workflow in building an NLP model that is based off BERT. So quick review here. So again, Autopilot is an implementation of automated machine learning, which you can use to just point it as of now to a tabular data set. And Autopilot will then analyze the data, come up with a combination of good model candidate pipelines, produce the Python code for you, which we saw in this generated module in the Python files. And then it will apply those in different candidate definition pipelines and unique combinations of feature engineering and algorithms, and then trains and tunes the models. And you can actually see that happening. So apart from those notebooks that it generates, let me quickly show you. So I go here in the AWS console to SageMaker. So I'm going to the SageMaker UI. And I'm clicking here, let's see, to training jobs. So in this UI, Autopilot doesn't have like a dedicated own UI. You can see it actually, if you would have set it up here with the Studio UI, which we're not using in this workshop today, but you can see the training jobs. So after the data analysis, which is done, you can see here when the model is training, that jobs start to show up. So here's the AutoML DM, and you can see here the DPP 0, 1, the DPP 2, where it's actually trained the model. So those jobs actually appear here in this UI. And what's also good to highlight, and we will see this later when we do the manual training as well, whenever you're using a training job on SageMaker, SageMaker takes care of creating the underlying infrastructure resources to perform the model training. So in this case, it spins up a resource, an instance, and it loads the model training code and basically runs the training job with the training data. And once it's finished, it also shuts down and terminates those instances. So here you can see that this particular training job executed run for 82 seconds. And you're only getting billed for those exactly 82 seconds. So you don't have to care about creating EC2 instances, installing everything and terminating. It's all handled for you by SageMaker. So you can see here how that training job performed. It actually created an M5 4x large instance, which is just one of the types of the AWS instance families. And it created one instance of those to run the training job. All right, it documents everything here. You can see where the training data came from, where the bucket, where it's all stored, where it finds these Python snippets, the generated modules in this URI here. So everything is really documented for you to trace back. Yeah. So this is the training jobs for AutoML. And also after the training, it also optimizes. So they are not yet showing up because it's still in the training phase. But afterwards, you will also see an AutoML job here that actually tunes the hyperparameters. So those jobs drop in here in the console. And obviously, you can query them programmatically and see how those jobs are performing. So that's basically what we're doing in here in the notebook. So we're programmatically querying here the status and see where we are. So here, feature engineering is still running. Let me double check. Yeah. So feature engineering is still running. So you can describe those jobs here through the API calls as well. All right, so yeah, let's keep this running. As I said, it will take some time. It performs a lot of steps for us, so it needs us time. And then in the third one here, we've been running Comprehend. Comprehend, as I said, is a built-in service that AWS offers you, which you can integrate simply by an API call, and it already performs NLP tasks. What we're trying to do here is basically fine-tune that model, and it's not necessarily a BERT model, so I'm not 100% sure what Comprehend uses as an implementation, but we're just fine-tuning that pre-built model to our data set in this use case and telling it that we want to have this star rating predictions. So yeah, so this training here is in progress. So you can see here the custom classifier is in training. And once this is done, we will query here the results, and then we will also deploy an endpoint and see how it's performing. So those two are running. So keep the notebooks open. Don't stop the kernels, do anything crazy. Just make sure they're executing here. In the meantime, we will move ahead. So we will do this a couple of times in this workshop. So sometimes we'll say, keep this notebook up and running because it's still performing its task. And we will move ahead and introduce you to the next topic. And then before we have the next break, we will revisit and see the results. Otherwise, we would probably sit here for 2 days. So we're kind of trying to make the time efficient while some of the notebooks are still working. And this is one of those times. So let's actually have a quick look into the next section here. And we're not executing this as part of this workshop, but I want to show you what's also possible in the environment of augmented AI. So a big term. Basically, Amazon is offering another service which is called augmented AI. And this gives you the possibility to include human in the loops into your machine learning workflows. So when do you need a human in the loop? Let's assume you have a model deployed and the confidence score of the prediction sometimes is low. So maybe you're passing in this review text and, for example, Comprehend says, yeah, I think this was a 4-star rating, but I'm just 30% confident. I'm not so sure. What you could do is then intercept this prediction and send it to a human that is actually doing the manual review. And you can set this review, human in the loop review workflows up with this service called Augmented AI. So pretty powerful if you want to build in those human plus AI scenarios, and then the human will receive this review text and can actually label it and predict and say, yeah, no, this is totally a 5-star rating. I'm not sure why you were confused, your model. So the human could label it correctly. And then the prediction gets sent to the client. And the built-in model would actually pick up, depending on your implementation, the human feedback and improve. So it will also give you options for an active learning where the model improves once it receives all of the human feedback. So over time, you would send less reviews, for example, to the human and have the model processing more and more and increasing the accuracy. So pretty powerful concepts here. And we're not running this notebook. There's a couple of setup steps required, but we're basically just quickly want to show you and highlight the service because we think it's pretty powerful. And there's a couple of implementations. So one implementation is actually what I've quickly mentioned before, and I just go here in the AWS console to show you this. So there's one service part of SageMaker, which is called Ground Truth. And Ground Truth is actually an implementation of augmented AI in a sense, covering the particular use case of data labeling. So with Ground Truth, you can spin up data labeling jobs because in many of the cases for training models, you need to have labeled data, right? Because you have to teach the model in supervised learning how to predict based on the training data, which has already the labels attached. So what if you have a large set of data which is not yet labeled, right? So you could spend hours and hours and hours of labeling it itself, or you actually have a service that is doing that for you. And this is basically ground truth. And ground truth, as I said, is kind of an implementation of this augmented AI because it includes this human in the loop review. So the first step, what you would have to do here to actually get this going is to manually create a labeling workforce. And for the workforce, you have the choice between a couple of different options. So you can either use a public workforce, which is the Amazon Mechanical Turk, which is 100,000 of global workers that are part of this Mechanical Turk service, which will do the job for you. So this is really like a large global group of workers through this service that are performing the labeling. Or if you want to keep it private, you can set up a private workforce. So you can just create a team of your co-workers, for example, or friends. When I used to travel a lot to conferences around the world, I was just creating a private team, added myself with my email address to this private workforce. And I was spending the evenings in the hotels labeling a couple of pictures for a demo, which I've done the next day. So private teams you can set up as you like, including yourself, including coworkers, including friends, which help you label data, for example. Or you can also choose a vendor, which is basically a third-party company which has gone through review and checks by AWS, and you can leverage as kind of an external company. So all of those options are available for you to actually find workers to label the data. And then you would create a labeling job here. So you would give instructions, point to the data set, etc. All right, so we're actually not running this today because there are a couple of steps involved, like setting up this workforce. And if you're adding yourself, you have to check your email inbox and create an account. So it will take a little bit of time, which for the sake of the many topics we have today to cover, if you're interested, definitely have a look at those notebooks after the workshop. So all of the instructions are in here, how to set this up. But we really just quickly wanted to show you what capabilities you have with the SageMaker platform here. All right, so as I said, those two basically show you how you would set it up. And actually the last notebook here would work on the comprehend model once the comprehend model is deployed, and shows you how you can intercept those review and star rating predictions which have a low confidence score. And then you get an email and you actually have to do the work yourself. All right, so for now, let's skip over that because I think many people are interested in really building a BERT model, which is the goal of this workshop for the manual steps. So in the next sections here, as you can see, we're going really through the manual process of data ingest. Then we're going to have the data exploration. We're going to check for data quality. Then we're going to do the feature engineering, data preparation. Then Chris will show basically the prepare and the model training. And I'll again show how to optimize and deploy the model and to automate in a pipeline, add a little bit of streaming data. And then Chris also will show, as the last part of the workshop today, how to do work with Kubeflow pipelines. So we still have a good amount of topics here to cover. All right, so let's jump here. Let's keep the notebooks that are running just running. They're doing their job. So let's jump here into 04 ingest. And we're now basically leaving the automated machine learning land, and we're starting with the traditional manual machine learning workflow with getting the data, looking at the data, preparing the data, checking for quality, etc. So in this example here, I'm opening again the 0 overview notebook. And the first task, obviously, is first of all, you have to have data. And for model training, the more data you have, the better. And you would have different ways probably to get to the data, right? So in the best case, you would have an application, probably web application, microservices, your websites that are generating data, and then in a good, perfect world, probably dropping them to a data lake. So in our case, we're assuming we're building up an F3 data lake. So we're going to write files basically straight into an F3 bucket. Depending on your setup, you probably or might have different ways to acquire your data. Maybe you have a data warehouse where you have a lot of the data and you're dumping it out maybe into a data lake environment, or you have streaming data coming in. So there's a lot of ways to basically get data into your environment. In this case, we're assuming we have an application writing data into a data lake. Once the data is in S3, depending on your job role and depending on your background, you would use different set of tools to work with it. And normally in our workshops, we have a couple of different profiles. So some people are working as machine learning engineers, data scientists, but in many cases, we also have people coming more from a BI data analyst background and are maybe starting the journey into more machine learning. And depending on this background, as I said, you're familiar with one or the other tool set, right? So the BI data analyst people probably are used to work more with databases, data warehouses. And in their role, the goal is maybe creating business dashboards, right? You want to have insight into the data and more on the visualization, dashboarding side of things. If you're a machine learning engineer, data scientist, you probably just want to quickly check the data set, see how the data quality is, see what features you have, see if you have to enrich and add more data for the training, see if you have to do some feature engineering, etc. And then start with the model training and tuning. And in AWS, you have a couple of different options here. So what we want to show you here is how you can leverage a service called Amazon Athena to query the data in S3 without even moving it. So let's assume we have this data lake with our reviews being straight written into that, and we want to quickly query it. And most of us probably still are familiar with SQL commands or are actively working with SQL. So Athena gives us the possibility to use standard SQL commands to query the data that is in flat structure in a 3 bucket without even moving it into a database or anywhere. So really powerful. And then we're going to use SageMaker to actually do further processing. We also do have a couple of sample notebooks in here, which show how BI data analysts can work with the data in a data warehouse environment. So the Amazon Cloud Data Warehouse Service is the Amazon Redshift. So we will also ingest a subset of our data lake, not the whole data lake, but a subset of recent data into the data warehouse, and then also show you how you can work with that data and show you a couple of tricks how you can also enrich that query with data that is maybe still in the data lake. All right, that's a quick overview here and the motivation for this section. So let's open the first notebook here, which is the copy TSV to S3. Very fancy name of this notebook, I know. So what we're doing in this notebook, and I'll just do a cell run all on this one here. So what we're doing here is we're using now our customer reviews data set that I showed you before. So there are 150 million reviews. And we're simulating our application. So I don't have a website that is producing the real-time reviews right now. So what we're doing is we're basically just copying the data into our S3 bucket, which we then assume is our data lake. And we will show you how you can actually ingest and work with streaming data in a later section today. All right, so if you recall, and maybe a couple of you joined later and have missed that part, we're using the Amazon customer reviews data set today. So as you can probably tell by the name, it's a collection of more than 130 million customer reviews from the Amazon.com website across more than 50 different product categories. And it's a really nice data set, especially if you're playing around with NLP tasks. So here's the instructions. We've linked it here so you can have a look anytime if you want to work with that. Basically, it's offered in 2 different file formats. So you have that data set as TSV files, which are the tab separated files. And it's also available in Parquet. And we will come to that in just a minute. So the TSV tab separated, similar to CSV data. I guess everyone is more than familiar with those files. And also Parquet, which is columnar optimized file format. specifically suited for queries. If you're running SQL queries, Parquet is definitely one way to optimize your queries. All right, so what we're doing here is doing a quick show command on the public bucket. So this is really the open source data set from Amazon. And you can see here, there's also a couple of multilingual data sets. So we have reviews from the German marketplace, from the French, from Japan, from the UK, and from the US. And then basically the majority here of the 50 categories, they are all the US marketplace. So this is the bulk of data here available. So what we're doing in the workshop here, because we're sometimes pulling in a subset into the notebook environment, and also we want to iterate quickly. You only have 1 day for this workshop as of now. If we operate on the 150 million, the jobs would run definitely longer. So because we want to see the results, we're just pulling down a subset. So we just pull down 2 of the smaller TSV files to really just limit the amount. But obviously, the cloud is there for scale. So you can definitely pull down as much data as you want. For the workshop today, we're limiting just to be able to have training jobs being finished in maybe 10 minutes instead of an hour. All right, we can do a quick show command here, and this shows us the Parquet files, which are also published. So here you can see I think it's roughly 50 categories of products. Here are the Parquet files, which are optimized here per category as well. All right, so let's simulate our application, our data lake, and let's just copy the data from this public bucket into our own private F3 data lake bucket, which is the SageMaker default bucket, which we're operating in today. We're pulling in again the Python SDKs. We're setting up the environment variables here, and we're defining an F3 source location. This is the public bucket where all of those reviews are shared. And we're giving it a destination, which is our own private bucket. And we're just giving it, again, a folder structure here to drop it. And then we're using the AWS CLI here to copy recursive, meaning all of the files here from this public bucket into the private bucket. And we're filtering here specifically for 2 files. So we include the digital software and we include the digital video games. And those are really just a subset, a smaller number of reviews for us to be able to have the training and tuning jobs today going quicker. And I guess both of those we will see in the exploration have roughly around 100,000 reviews each, whereas the books have millions of reviews. All right, so those have been copied down, so we can see here. So that was just an easy, basically a copy notebook, not too exciting. Let's open the 02 setup Athena. And in this notebook, we're creating and setting up the Athena service. And Amazon Athena is an interactive query service, which lets you use standard SQL commands to run queries on the data stored in S3. The advantage is that we don't have to move any data. We don't have to move our whatever we might have, terabytes, exabytes, petabytes on data into a database or something. We can keep it in S3 and we can still run SQL commands. So really powerful for a quick exploration. You just want to see how the data looks like, pull in a couple of results, see if the features are good enough or if you have to maybe combine it with other data. For those of you who are interested, Athena is based on the open source SQL engine Presto, which is exactly developed for this purpose to do very fast analytical queries, basically against data of any size without having the need to move it. So let's see how we can do this. And again, I'm a little bit lazy here, so I do a cell run all just to keep those cells getting lined up. So what we're doing here is, again, as usual, pulling in the SDK, setting up the environment. I probably don't mention this anymore because it's the exact same code moving forward. What's new in here is to interact with Athena, we need another Python client, and we're installing PyAthena. And PyAthena is a Python DB client, which also works with Athena. So we're doing a pip install here with PyAthena. And PyAthena comes with a couple of constructs. For example, it has a connect object to connect to our environment. And it also comes with a cursor. And the cursor is used to iterate over the data. And it also has quite a neat integration with the pandas data frames. So we're also pulling in this so we can display the query results in a pandas data frame here in the Jupyter notebook. All right, so far so good. One thing to understand, I said we don't have to move the data, but we still have to define the meta information to give the SQL commands the structure, right? So we still want to do a select column name from table. And in order to do so, we need to define the schema for the data. And we're doing this by leveraging a data catalog service. And the data catalog that Athena works with is the AWS Glue data catalog. So what we're doing next here is we're creating the schema information. So first we're creating a database name, and let's just call it DSO AWS. And we can do this then by executing a SQL command. So we're setting up a staging directory, and this is really just a temporary folder where Athena drops the query results. And then we're constructing a SQL statement. So create database, if not exists, DSO AWS. Very simple, create database statement. And we can pass this through the PyAthena integration. So let's do this connect. And in the connect, we give it the region name we're operating in, the AWS region, which is the US West 2. And we're giving it this staging directory to store the query results. And we're asking it to give us a cursor. And on that cursor object, we can then execute our statement. So let's execute this. And then as a next statement, let's see if it worked, right? So let's do a show database. And we're running this statement again in the cursor. And here you can see how I can pull the cursor results into a pandas data frame. So I just call the as pandas from the cursor. And here my data frame, and have a quick look into that. And I see the database is created. All right, so we're almost good to go. So we have a database, we need the table. So let's open the third one here, register S3 data. And we specifically called this register data because we're not moving anything. So we're basically just defining this schema and kind of registering the data with Athena. So again, no, sorry, this was the one I just had open, right? No, that's right. Getting confused here myself. So let's do a cell run all on this. And again, we're pulling in the SDKs, we're pulling in PyAthena. So in this notebook, we're defining now the table schema and metadata information. So in our case, the data is based on those columns, right? So we have the marketplace, custom ID, review ID, etc. So what we're doing in here is basically after setting up staging directory, the prefixes, giving the table a name. I'm just scrolling down to the print command. The print command is easier to read. We're creating a create external table statement if it doesn't exist, and database, and we created a table name. Let's call it Amazon Reviews TSV. And here we're defining the table schema. So those are really our columns from the data set. And we're defining the data type. So most of it is string. A couple of those are integer values. And you can see here, we're telling it the row format delimited fields terminated by T. So it's a tab separated file, lines terminated by new line. And here you can see the location. So note that it's an external table. So we're building the schema for data that is residing externally in S3. And with the location here, we're giving the pointer to where it finds the data. So here's our bucket and here is our TSV folder. We also tell Athena its compression type, it's gzip compressed, and it should skip the header lines here. All right, let's execute the statement. So again, cursor execute the SQL statement. And let's run another one. Let's do a show tables in this database. And we can see here's our Amazon Reviews table definition. And now we've set up the data catalog service with a database and with the information of a table structure, pointing it to the data that is in S3. And with that, we can now run SQL queries on the data. So let's actually run one. Let's do a famous select star from the database, DSO AWS, Amazon Reviews TSV table, where the product category equals digital software and just limited to 100 results for now. Let's execute the statement and let's pull in the results from the cursor into a pandas data frame. And here we go. Here you can see the result from a SQL query on your F3 TSV data. And what I can also show you here, I quickly go to the console and go to the AWS Glue service to show you where the meta information got created. And Glue is actually more than just data catalog. So Glue also offers ETL. So you can also do some transformation jobs here with Glue. We're using SageMaker for the workshop, but just to mention that here, the part of Glue that we're using is the data catalog service, which you can see here on the left. So if you click here on the database, you can see the DSO AWS database that we created. And if you click on the tables, you can see the table that we also set up programmatically through our Jupyter notebook. So here you can see the schema, looks fine. And this is basically the setup we've done now to be able to use Athena to run those SQL queries on the data. All right, and another thing you can do if you open up the fourth notebook here, convert F3 data, let's assume we would not have the Parquet data. And again, I do a cell run all. Let's assume we wouldn't have that Parquet data from the reviews data set. Let's assume you just have this DSV, log file data, TSV data, whatever you have, and you wanna optimize it for those queries, and you wanna convert it from this TSV file format maybe into Parquet. You can actually leverage Athena for that part as well. And this notebook really just quickly shows you how you can do this. And we're leveraging those Parquet data sets for the next exploration notebook. So make sure you're executing this one here. Just do a cell run all. So again, setup of the notebook, the PyAthena client. And then we're defining a new table, and let's call this the Amazon Reviews Parquet, giving the staging directory. And then here the SQL query is a create table statement. So this is not the external table. This is really a create table if it doesn't exist already, giving it the name of Amazon Reviews Parquet. And you can define here in this query like with, and then format Parquet, and give it the external locations where to write the output. So this is going to be in a bucket and a subfolder Parquet. And you can specify how to partition the data. And we want to partition it exactly the way it has been before in a product category. And this is a create table as statement. So create table as, and here you can see we're selecting the columns from the TSV data table. So here from is pointing to this external table, and we're basically just selecting the columns from this. What you can also do in here is doing some in-place data transformation, if you like. So what I'm doing here as an extra is I'm pulling in the review date. I'm casting it to a date, and I'm grabbing the year. So I just want to have an extra, a new column, which is only showing me the year of the review instead of the full length of the whole review date. And I'm saving this as a new column called year. And I keep the review date in here, but I just add this new column here for years. All right, then execute the statement. And one step you have to do if you're working with Parquet and partitions, you have to load those partitions back in. So this is done with this msck repair table command, which you're running on this specific table. This basically just loads up the partitions. So let's run this command, and then let's check if it worked. So let's do a show partitions SQL command on the Parquet table. Execute the statement, pull it into pandas, and have a look. And yeah, we can see here, product category, digital software, and digital video games. So if you want to double check, you can jump to F3. So I'm in the console here. going to S3 and actually show you in the bucket that the data actually got generated. So I'm clicking here into my default bucket, and you can see we've been working a lot here. So it's a couple of folders already. Those were in the reviews PDS, I think. Yep. So if you recall, we only copied the TSV. And what we've done now, we generated ourselves the per K data. So if I click in the per K, we do have now the two data sets in per K format for us to use. All right, so those were the 3 Athena notebooks. So I'm closing them down. So this one, yeah, do a sample query and we see the data is actually working from per K as well. Perfect. So just make sure that those execute correctly. All right, so what we've done is we copied the data to our S3 bucket. We set up the data schema information in a data catalog service to be able to use Athena to query the data with S3. And we also used Athena to transform or convert the data from TSV to per K. I want to also quickly show you another project which you could use to do simple things. So there's an open source project from AWS called AWS Data Wrangler. And just to be very clear, it's not an official AWS service. It's really just an open source project by AWS, so by a couple of engineers from the data engineering side of things that open sourced this library, and it's really, really cool. So if you have a lot of those data wrangling tasks, you might want to have a look at this project here. So here are the links also to the GitHub repo and the documentation. And let me run those cells here. So AWS Data Wrangler is basically a project that integrates with a lot of the AWS services and gives you a convenient way to really, as the name says, wrangle the data, retrieve the data, interact with the services. And it's integrated with a bunch of services here, and you see a lot of tutorials. So it's working with S3, per K data, Glue, Athena, databases, Redshift, CSV datasets, EMR, which is the Elastic MapReduce service, QuickSight, and much more. So an example which I want to show you here in this notebook, so if you want to run the 05 query data with Data Wrangler, you can see how you can leverage that library. So we're doing a pip install and pulling in the AWS Wrangler. And then we can do a couple of really nice things here. So for example, let's query our per K data from S3. And now with Data Wrangler, we can use push down filters. So how does this look? So we're giving it a path to our per K data. And what we can do now is on the Data Wrangler, we call S3, and there's the function read per K. We're giving it the path where to find the data. And then we can specify the columns which we want to retrieve. Star rating, product category, review body. And filter by product category equals digital software. And this is pulled directly into a data frame. And if we visualize the data frame, here we have the result. So this is another really nice way to interact, for example, with per K data in S3. And having those push down filters executed right away in this query here. What you can also do in the same call is reading the data in chunks. So you can also use this call and set chunk to true, which then will return a new data frame for each file in your dataset path. Or you can also do chunked and give it an integer value, which will then iterate on the data by the number of rows, equaling, matching that integer you passed. So there's a lot of like optimizations, and especially if you're using chunked, it's faster and it uses less memory. So yeah, doing this chunked read, and then you can iterate here. So you can see here one chunk of the data that is being fed into a data frame here, for example. You can interact with Glue, so with the data catalog. So you can do catalog get tables, and you just pass the database information, and print the table names here. You can use it to interact with Athena as well. So you can do a data wrangler Athena and then read SQL query. And you can pass the SQL query right in here. So here we're passing a select star from, giving it the table name, limited, and the database name. And Pandas data frame has the results in here. You can also use the chunked feature in here for the Athena read. Yeah, so those are just a couple of highlights. And as I said, it's integrated with a real good set of AWS services. It gives you an easy way to wrangle the data between the services. So if you're using a lot, if you're operating a lot within those services, that might be a good library for you to maybe try out. All right, that was just a highlight we wanted to show you. All right. So any questions here? And I just maybe check in with Chris. The second part we're going to do in here is also showing you how you can get the data into Redshift. So if you're coming more from a data warehouse, data analytics, BI background, that might be something you're interested in. So in the next step here, we're filling up our Redshift cluster. And then we're moving on to exploration and then to the data quality checks. So Chris, anything around Athena that is worth mentioning or data wrangler?
Someone asked, sorry, I didn't get a chance to put my headphones in quickly here, but just real quick, someone asked about the difference between Athena, when to use Data Wrangler, which is just a pip install library, or PyAthena. You could use either. Just know that Data Wrangler is built so it's built by solution architects and by engineers from Amazon. So a lot of best practices are built in, and Data Wrangler is more than just the Athena service. It's also Redshift. It's also EMR and some other things. So we primarily use PyAthena because we found out about it first. When we were putting together the workshop, we later found out about Data Wrangler and wanted to include it. But yeah, and also Data Wrangler does pull in a few dependencies. And the general rule of thumb in Python land is be careful of using third-party libraries that depend on lots of other third-party libraries, because you might have conflicts. So that's the other way to look at it. But if it's a from scratch project, certainly use Data Wrangler. They went through the 1.0 release, which stabilized a lot of APIs. So that was the other thing, is when we found out about Data Wrangler, it was pre 1.0, so we couldn't necessarily trust the APIs. Okay. Yeah, I think that's it. A couple people are having some issues with the database table and things like that, but I'll try to work through those. Yeah, let's keep moving.
Okay, perfect. Thank you. All right, so let's do the 06 create a Redshift cluster. And again, you can do many things through the UI as well. We're just doing it programmatically again, so we're keeping the majority of the workshop really inside of the Jupyter, not to have the need to jump around different UIs and consoles. But obviously, you can also do it separately through UIs if that's something that is more or easier for you to do. We're doing it here from the notebook. All right, so setting up a Redshift cluster, let's do a cell run all. This is one of the notebooks that executes a little longer. No, actually not. The notebook actually finishes, but the cluster is being set up in the background. We split it across two notebooks here. So let's execute this one here. What we're doing here is setting up the data warehouse service, the cloud data warehouse that Amazon offers. So it's called Amazon Redshift. And this is really targeted to run and host petabytes of data and run complex analytical queries. So let's see how we can leverage this. And one question might come up with, what's the approach? So when do I ingest the data into a data lake, and when do I ingest it in a data warehouse? So generally speaking, the data lake is more of the raw data that you ingest, right? And it's more targeted really at raw, unprocessed, and huge amounts of the data that you might be collecting, right? And huge obviously always depends on your specific use case. But if you have real-time applications, just, you know, writing log files that you want to capture, if you have tons of like maybe streaming information to write into an S3 bucket or something. So data lakes should be suited to take any amount of raw unprocessed data. And then in the next step, you're processing the data and you would decide what subset is relevant for you to maybe ingest or keep in a data warehouse. So in a data warehouse, which is more targeted for business analytics, you would then have a more structured approach, and you would run analytical queries, and you would maybe generate business dashboards, etc., to receive more the business insight. Versus the data lake is suited for, you know, storing those large amounts of data. And then as a machine learning engineer, data scientist, you can explore the data and then decide which, maybe a subset or which parts of that data is suited for any specific machine learning use case you're currently working on. So what does it mean in our use case here, working with the customer reviews? So we would set up really the live ingest of the reviews being dropped into our S3 bucket. And for the data warehouse, we might want to pull in a subset, let's say the most recent data. And we could do this like for the current month, for the last couple of months, or maybe for the current and last year, right? So what we're doing in this example here, we're gonna copy in the past 2 years of the customer reviews data set and then analyze that. And this is obviously a sliding window. So once you're coming into the next year, you would probably drop one of the older data out of the data warehouse. So this is kind of how we set it up here. So again, to deploy the Redshift cluster, there's a couple of steps needed. And with everything, again, we need to have the privilege, their permissions. So the next couple of cells is really, again, setting up IAM policies and creating policy documents, creating the role, etc. So this is really needed because we're working in fresh, clean AWS accounts, right? So we need to set up everything in the beginning. If you're operating in an environment, you would probably set up those roles like once and then keep reusing them, right? And adding and removing privileges as needed. As we're working here with a fresh vanilla AWS account, we have to create those policies, creating the roles and attaching those. So that's what we're doing here. Again, those, if you're interested, have a look, but it's really just programmatically creating the permissions that we need to actually deploy a Redshift cluster from our SageMaker Jupyter notebook, which is pretty unusual. All right, so also storing the login credentials for the data warehouse in a service called Secrets Manager. So this is a service that enables you to store secrets, rotate and manage them. And we can programmatically then call and receive the secrets to use in other API calls. So we're storing the login credentials in here and retrieving them again. And also defining a couple of Redshift parameters. Let's call the cluster DSO AWS. Let's create a database name. We set this up as a multi-node. So our Redshift cluster will have 2 EC2 instances, so the DC2 large that are specific to Redshift. And let's spin up 2 nodes. And with that, we can create the cluster. So we're pulling in the Redshift client from the Bodo 3 Python SDK. And then with Redshift, we can call create cluster. We're passing in the database name, the cluster identifier that we defined, cluster type, node type. So basically all of the settings that we set up, the username, the password, the role, security group in which we're operating, port. And yeah, so here's the response. So in the background, we started this Redshift cluster creation. And we can check this again if you want, if you go to the console and you're typing in Redshift. And this takes us to the Redshift service. And it also directly shows us here the cluster dashboard. So one cluster here, and you can see if you click here, it's currently in creation. So this will take a couple of minutes for it to spin up the physical EC2 instances and then launch the Redshift service. So in the course of the workshop today, you see that we're touching a lot of different AWS services, really just to give you a sneak peek which services you could maybe interact with depending on the roles and the goals for your machine learning and data science projects. All right, so this cluster will take a little bit of time. So we can actually close this notebook. So we split this notebook into two. This one is just firing up the creation. And then we can open up the next one, the 07. And what we want to show you here, so we're actually showing you some neat tricks. The data warehouse obviously needs to have the data stored locally. That's the idea of the data warehouse, right? So you ingest data in a structured way to the data warehouse, and then you leverage all of the data warehouse features to run those optimized queries, right? So the Redshift comes with caching, with different really layers to optimize and give you the performance and resiliency for a cloud-based data warehouse. But then there might be a case where, as I said, not all of the data is in Redshift, right? So let's assume we're pulling in the last 2 years of reviews. And now you want to run a query and you want to maybe detect if there has been a longer historical trend in maybe happiness or customer satisfaction dropping. And you noticed it's dropping for the last 2 years, but you want to make sure pulling in maybe historical data, if this is a longer trend or if it's just appeared in this current year, something, right? So what you could do is you could leverage a service called Redshift Spectrum. And this is just basically another capability of Redshift itself, which lets you query data again that is stored in S3 to enrich your SQL queries. So it's a little bit confusing because we appear to be doing the same thing again, right? We have data and we're also using a service to query data in S3, which we did with Athena before. But here, really keep in mind that we're coming from a different job role perspective, right? Let's assume our day job is working with data warehouse, with Redshift. We're creating business insights, we're creating dashboards, we're trying to figure out if there's anything in the data which we need to act on, like a customer satisfaction dropping. And maybe like once in a while, you need to enrich those queries with a broader data set, which is not inside of the data warehouse. So let's do a run all, and this notebook will wait for the cluster to be deployed. So if I check here, my cluster in the meantime became available. So let's see. So I run this notebook here. So we're setting up the environment. And what we're doing here is to interact with Redshift. We're pip installing another tool, which is called SQL Alchemy. And this gives us the capabilities. It's a SQL Python toolkit, which we use to connect to Redshift. Similar on how we use PyAthena to connect to Athena. So with SQL Alchemy, we can pull in objects called Create Engine and SageMaker, which are really just used to create this database connection. We're pulling in the secret and the credentials and the username and the password to connect to the data warehouse. We have the configuration parameters here, so the cluster name, the Redshift database name, and Athena name. So we're basically creating two schemas to show you those capabilities. The port and some table name. All right. So if your cluster is still deploying, you will see here in creation. So once the cluster is available, it will jump here to available. So this cell is just really looping and making sure you're waiting for the cluster to become available. So if that cell is still running for you, just give it another minute. So I think mine took now 3-4 minutes to deploy the Redshift cluster. Then when we have the cluster available, we're pulling in the endpoint address. So an endpoint where we can actually reach Redshift and the role that we created. And then using SQL Alchemy, we can create this engine And it's basically a PostgreSQL link to our data warehouse. So we're passing in the username, the password, and connecting to this endpoint address on the specified port. And we're using the database name that we created. And then we can open up a session with this SageMaker and configure it with our engine that we have. All right, so let's see how we can use Spectrum to actually query data that is in S3, because until now we don't have any data loaded in Redshift, right? We just created the cluster, so it's clear of any data. So let's use Spectrum to actually run some queries on the data in S3. And we can do this by using our Glue data catalog service. So in the previous step, we created all this data catalog information about the data set. And with Spectrum, we can leverage that and connect from Redshift also to S3. So let's see how we can do this. So we're creating a SQL query, create external schema if it doesn't exist. And I just call this database schema Athena to remind us it's actually the connection through the data catalog into the data in S3. And here you can see I'm passing from data catalog, so it knows where to find it. And give it a database name here, it's DSO AWS, the IAM role, the region, and create this external database if it doesn't exist yet. We execute the statement here with our session that we opened and commit. And then we can run another SQL command to query data. So let's do a SQL, select product category, count the star ratings from Athena. And then here we're using the table name that we predefined, Amazon reviews TSV, group by category and order by count star rating descending. We fire it up and here we go. So we don't have yet any data in Redshift, but we're using the data catalog service and the capability of Spectrum to query the data still through Redshift, but in the place of S3 here. So pretty neat. And we can use this also to kind of pull the data in now to Redshift. So as a next step, let's actually move data physically, copy it over into Redshift. And let's do this for the years 2014 and 15. So the last year of reviews in the data set is 2015. So let's just assume that's the recent data we have, which is the case in our data set. And let's create a new schema. So this one we call Redshift. So this is really the data that we copy physically over. So let's create this schema called Redshift. And here I have some helper functions. So I created some helper function to give us the possibility to define the start year and the end year for this copy command, basically. And what we're doing is we're creating a table, if it doesn't exist yet, in the Redshift schema, and the table name will have 2014 or 15. So basically, for each year, we're creating a separate table and pulling in the data. So marketplace, customer ID, etc. All the columns we know exist. All right, so if I call this function now here and pass in 2014 and 15, this is what's happening. So we're creating two tables, one for each year with this information. Now, we do have the tables, so we have to insert the data. So in the next step here, again, I've written a little helper function here to automate this, again, for start year and end year. And we're basically running an insert into command into this Redshift and then the corresponding table for each year. We're selecting those fields, so marketplace, customer ID, you name it, from, and this is the important part, from Athena Amazon Reviews TSV. So this is the schema information that we have that is pointing to S3. So through this integration, we're pulling in now physically, we're creating and copying and inserting into. So this insert into means we're physically moving the data now into Redshift. All right, so running this for 2014 and 15, and it should say done once it's finished. And now we've pulled in the data into Redshift. So there's a little bit of text you might want to read through, or you have read already. So the way we're doing this, and this is kind of a best practice here. So if you're working with time-based data, let's say reviews ordered by years, by month, etc. One way to do it is really kind of have separate tables in the granularity that you think you might drop them once they age out. So if you just construct in comparison one large table, and I'm loading 14 and 15 reviews inside one single table, and we suddenly have 2016 and I want to get rid of the 2014 data, I would have to delete those rows from a single table, which creates those holes basically. And over time, it just makes the queries longer and longer to execute. And there's different ways to optimize, and you have to run those vacuum processes to reclaim the space, etc., and resort the rows. So a way to avoid this is, if you know you're gonna age out the data maybe by year, create a table per year. If you wanna drop it by month, so maybe you're iterating on a weekly basis, daily basis, monthly basis, then it might be easier to, you know, have tables for each month, for each week, etc. And then if you're dropping them, it's just a drop table statement, and you don't have to run those vacuum processes to reclaim the space inside a single table. All right, so this is just a quick background here on Redshift table optimization. All right, so let's do the next one here and actually query the data. So let's open the 08. And in this notebook here, we're querying now both Athena, so meaning the data in S3, and Redshift, and using the spectrum here. So, and here's a quick visualization that shows you what might be the use case, right? And this is what I said before. So maybe we detect that there's a drift in customer satisfaction, right? Maybe customer satisfaction is going down for certain product categories in the year 2014 and 15. And you want to see if that has been a longer trend. So for this query, you might want to enrich the data with data from the years before, which you don't have in Redshift. So we're using the Spectrum query engine now to combine in a single query the results from Redshift and from S3. So for all of the data that is 2014 and more recent, we query the Redshift data. And for anything that is older, we query S3. And this is really kind of the power where Spectrum comes in. So setting up the information here, the SDKs, connection strings, this is pretty much the same, checking if the cluster is available, and I should do a cell run all. So we actually see the results here. Setting up those, checking if the cluster is available. So again, if yours is still spinning up, you might see this cell iterating here. Then just give it a minute. Also again, polling here the endpoint where we can reach Redshift and our role that has the permissions, connecting through the SQL Alchemy connection, which gives us this PostgreSQL connection through Python here. And then let's first do a Redshift query. So because we split the data in 2014 and 15 in two different tables, if you want to combine the query across those 2 years, you have to do a combination. And you can do this, for example, with the union all. So what we're doing here, and I'm just going to this print statement, we're doing a select year product category. We're counting the star rating from Redshift, Amazon Reviews, TSV 2015, and group. And then we do a union all, and we run the same query, but on the table of TSV for 2014. And we pull the result here in a pandas data frame. And you can see again here, we have the results listed for each year. So in this case, we're doing the count star rating. So what you can also do is like the average star rating to actually see if the customer satisfaction is actually going down or something. So here you can see results for each year. But yeah, we're limited to those 2 years, right? So how do I see if the count star ratings spiked at one point or whatever is happening in the years before? So actually, let's do the same query on the data in S3 just to see we have the matching data. So I'm doing the exact same command here, but here I'm calling Athena. So that's the different schema. Athena, Amazon Reviews TSV, which has all of the years. And then we have to pass only 15 and 14. And this is really just double checking on the numbers. This is kind of a proof query that actually the data sets are the same. So those numbers should actually match, obviously, those here. Otherwise, we have a data issue. So our import actually worked. So those numbers are fine. And now let's combine. Let's actually split the queries. And let's do 15 and 14 from Redshift. So this is the block that we had before. And let's union this also again with Athena. But here we are filtering on year older than 2013, right? Because we want to basically enrich the data. And yeah, pulling this in data frame and looking into this. And here we go. So we have now, through Redshift, queried the data 15 and 14, and also enriched it with the information that is coming from our data lake. And you might wonder because why it's only going back to 2008. So the first customer review from digital software was in 2008. So there's just no older reviews. And similar digital video games, they started in 2006. So here we go. So we can now query like Redshift data warehouse information together with data in the S3 data lake. And you can prove this if you want to make sure it's actually happening. You can run this explain before the SQL command. And this will give you the execution plan. So here you can see the SQL query plan. And if you scroll down at one point here, it says it jumps to an S3 sequence scan. And here's the location, which is our S3 bucket. All right, so this is pretty much the Redshift example. And another question we often get at this point is, okay, now I'm slightly confused because you showed how to do it with Athena and you showed kind of the similar way with Redshift, right? So what's the difference? When should I use which? And the answer might be just given the team you're operating in, right? If you're business analytics, you might work more with data warehouses. If you're more on the data science, machine learning side, you don't want to spin up a data warehouse service for that part, right? So you want to more like explore the data quickly. So you would probably use a service maybe like Athena. And another difference is with Athena, you're basically defining what is called this schema on read. And Redshift is the schema on write, right? So for Redshift to ingest the data, you have to predefine the schema. And then this table just has to stick to that schema, right? This is how databases and data warehouses work. With Athena, you're basically defining this schema on read. So when you want to read data and you want to use the queries, you're defining this metadata and the schema as we've done pretty much on the fly. So you're defining which sections, which columns you want to have in the query, etc., defining the schema and then operating. So really the way to do the ad hoc queries on data in S3 is probably more suited with Athena. And if you're operating more in a business BI environment where you might already have data warehouse services, or you want to have like more the business insights and create dashboarding and complex analytical queries, then it's definitely more suited with Redshift, which again has a lot of capabilities built into to really perform on those heavy aggregate and joins and all those analytical complex queries you might be operating. All right, so this was a small jump into the data warehouse world. And there's another one that is, I would say, an optional notebook, just quickly if you want to see how that works. So if you're working in the Redshift world, you can also write out the data. So let's say you're mainly working in data warehouses and your data science team is knocking on your door and says, I need data, right, dumped into the data lake. I want to operate here. I don't want to interact with Redshift. So there's another functionality in Redshift next to Spectrum, which is called the data lake export, which is basically kind of the reverse. So this one writes out the data in Redshift to your S3 data lake. So you can unload the data in Parquet to S3. So if you're interested, you can run this, do a run all. So it's basically just showing you after the setup here, a lot of setup to unload the data. And the unload actually happens with actually exactly that command. So unload, and then you're selecting the columns from whichever table you want to write out. And you're specifying the destination, giving an IAM role, and giving it the information Parquet, partition by. So in this case, product category. And with that, it's writing out the data into your S3 bucket in Parquet. So here you can see we're creating a separate folder structure here, Parquet from Redshift. And again, you have Parquet data written from the Redshift environment. So hopefully it didn't confuse you too much. What we wanted to show you here in this ingest is really depending on the tools you might already be working with, depending on your team, depending on your job role and your background, you might be using separate tools in AWS. And really the right one to pick is really have a look where you're coming, what is your goal, quick ad hoc queries, go with Athena, more structured business analytics and heavy analytical queries, go with Redshift. And there's many ways using data wrangler in between to, if you have to wrangle data. So a lot of ways, it's kind of a toolbox really, right? For you to pick and choose whatever suits your requirements the best. All right, so I would jump now to Explore. Maybe quickly checking with Chris, do we need another break?
Yes, everyone needs to go to the bathroom, including myself. It's 11 o'clock. Let's take a quick 4-minute break, and we're actually going to take a break. Yeah, no, let's take a 10-minute break. Is that good?
Let's do 10 minutes, yeah.
Okay, 10-minute break.
All right, coming back from the 10-minute break. So let me resume my share. All right, so we spend a good amount of time now with the data ingest. So let's actually have a look here at the exploration of the data. So let's go to the 05 Explore. And what we're going to do in this section here is using basically Athena in this use case to show how you, if you would come from more the machine learning data science world, would use Athena to query your data and get some interesting insights. And also what we're doing is creating some visualizations now in the notebook using Matplotlib and Seaborn libraries. And then as a next step, we also introduce you to SageMaker processing jobs, which you can use to, for example, run data quality checks at scale on the data set. All right, so again, we're using the Amazon Customer Reviews data set, so we should be familiar with that by now. So let's start the first notebook, 01 Visualize Reviews data set. And again, I'm gonna run a cell run all, not to forget one cell here. It's many cells in this notebook, so here it's really coming in handy. So the idea here is once you have the data in AWS land in S3, you might wanna quickly see and query the data, see if there's what information is there. And we do this now here using our Athena integration. So pulling in Athena, setting up the environment here. And what I'm doing here in the beginning is also defining a set of Seaborn parameters. So Seaborn is just a visualization library sitting on top of pandas and also using Matplotlib here. And we're defining here just some layout variables, which we're going to use. And I also have a couple of helper functions, some helper code here to display values on bar plots, etc. All right, so let's start. So let's actually see if we can have some nice insights into this data set. So we could ask questions like, for example, which product categories are highest rated by average rating? And we're doing this by simply building a SQL query. So select product category, creating the average from the star rating, and grouping it by product category and ordering it by the average star rating descending. So pretty obvious, I think, pretty straightforward. We're executing the query as we've done earlier with Athena. So cursor execute statement, pulling it in a pandas data frame, and here we go. So what we see is that the digital video games have an average star rating of 3.8 and digital software of 3.5. So yeah, it's not the most popular categories. But what we can do now is let's visualize this. So here I create a quick bar plot, and the first one is always exploding in size. I don't know why, with the two charts. So that is not too interesting in itself. It's more interesting if you run this across the whole data set of 130 million reviews or 150 million reviews. And what we've done here is we basically run this before and copied a screenshot here for you. So here you can see running this query on the whole data set. The highest rated category is gift cards with 4.73. So yeah, I guess everyone is happy about receiving a gift card, right? Not much to complain, I hope. And you can see how the average star rating per category drops. And yeah, the digital software, no surprise, is actually the lowest rated on average here of all of the categories on Amazon.com. Digital software. All right, let's do another couple of queries here. Which product categories have the most reviews? So also a pretty straightforward, select product category, count star rating, and group by product category and order by count star rating descending. And fire it up, and we can see out of our two categories, the digital video games have 145,000 ratings and digital software 102,000. All right, so let's plot this. So another plot here. The size is now again back to normal. And fair enough, but how does it look like if we plot this across all of the data set categories? Again, so we've pre-executed this for you, and here's the visualization. And what we can see is books are clearly the category with the most reviews. So if I scroll down, those are close to 20 million reviews, followed closely actually by the digital ebooks by now. And then, yeah, wireless PC, home, apparel, and then it's dropping dramatically. And the lowest major appliances and the digital software which we are using here. So those are around 100,000 reviews. And yeah, I guess it's also pretty obvious. Books have been the first category on Amazon.com, right? And all the other categories got introduced one after the other. So throughout the years, so yeah, books are still, I guess, still a favorite for everyone to review. Probably less on personal care appliances. So we could actually ask another follow-up question, and this is not science, but you could roughly estimate when each product category became available on Amazon.com based on the date of the first review we have. And this could be true, could not be true, depending on the data that we have, but it's a rough estimate. So let's actually run this. So let's fire up another SQL query that is looking for the first review date. And let's see, so digital video games, first review date in 2006, and digital software in 2008. So let's just assume it's probably around the time when the category got introduced. And we can plot this again. And let's do kind of a time chart here. And yeah, the two ones are not too exciting. But again, if we run this across all categories, what we see is that in 1999, for some reason, there are like 13 first reviews in the category. So we could assume that those 13 categories got introduced in 1999. As I said, it's not scientific research. I would actually have to double check if that really was the case, or if it's just, you know, based on the data that we have. All right, so we could do a breakdown of ratings per product category. So let's pull in this. Now scroll down, it's a lot of code actually to set it up. If someone has simpler code, feel free to text me. So here I'm doing just a horizontal bar plot that actually shows the stacked percentages of each star rating category. And yeah, not too exciting with the two, but again, if you run this across the whole data set, you get a really nice visualization here to see what percentage here the 5, 4, and where the 1-star rating is maybe growing tremendously. Again, digital software. All right. You could do queries, how many reviews per star rating. So if you're interested in the SQL code, have a look. Basically, we're doing here the counts per star rating. And we visualize, and similar, yeah, to what we've seen earlier is that the majority of reviews really come in for 5 stars. And then in the previous one, we saw 4 stars, second tier. It's like the first 1-star rating, second. But yeah, it's pretty unbalanced, right? So there's always a lot more people giving 5-star ratings than there is, let's say, for 3-star ratings. And if you run this across all the categories, it's even more visible that 5 stars definitely the majority of ratings. Actually, across the whole data set, again, the 4-star rating is second place. But yeah, it's a big difference here too. So that's definitely something you want to look out to optimize data. You want to make sure that you're not biasing any model with that drift towards the 5-star ratings. All right, so you could do how did star ratings change over time? So if you run this and calculate the average star rating, you could run this, for example, across a subset of product categories, and you can see here that there was a decrease in 2008. So as a business, you would obviously want to double check for the reasons, especially if it's a kind of a recent trend. But yeah, here definitely something happened in 2008. And if you visualize across all the product categories, you can see the downward trend. And it recovered a little bit, went down and recovered a little bit. So yeah, I mean, with the introduction of many, many, many more product categories, apparently that had some influence on the overall average star ratings. All right. Yeah, you can do this over time. So plot here again, categories compared to each other. So here, digital video games went down in 2008, and digital software got introduced in 2008. That's why there's no earlier data point. And that actually, for those years, went up. All right. And yeah, if you go crazy and plot this over all the categories, this is how it looks like. And which ratings are most helpful? So you can do all the different slicing here, right? And actually, many people say that a star rating of 1 is more helpful than the star rating of 5. So obviously, if 1 million people say this product is great, yeah, well, good. But I think people appreciate more that they find out about the ones that might have some flaws. So the 1-star rating received more on the helpful votes. All right, so same across the whole data set actually. So a couple of more questions here. And what is the ratio positive to negative review? So you could do slice and dice everything. Let's maybe just highlight the last question. This is kind of a fun question here. So we kind of thought about, okay, let's see if there's something weird in the data set. Is there any anomaly, something? And we've been looking for unique customer IDs, and we're checking how many times they're reviewing the same product and what was the average star rating. So normally, I mean, if you buy a product and you decide to give it a review, you give it a review once. Maybe you change your opinion if you repurchase it 2 years later and might give another star rating. But definitely what we found is something that a little bit disturbing. So in the 2 product categories we have, we could figure out, so again, we're filtering for a unique customer ID. So it's like one customer, right? One customer in the category of digital video games reviewed Call of Duty Black Ops 2 10 times, and every time gave a rating of 5. So there's a big fan of Call of Duty apparently. And it's getting more bizarre if you're running this query against the whole data set. So the top performing reviewers here, a single customer ID has reviewed the video of Pearl Harbor apparently 130 times and still giving an average star rating of 4.2. So a big Pearl Harbor fan. And I think I watched the movie maybe 3 times, maybe 4 times. So big credit to the person who watched it 130 times. Good job there. And the second one here, I'm still not sure who that is. So unique customer who watched Shania Twain live in Chicago 110 times. And I always think about, I don't know, Chris, you mentioned you're a big country fan, aren't you?
Yes. I love Shania Twain, and I'm from Chicago, so I was probably at that concert.
Yeah, and apparently 110 times.
I've never given a single Amazon review, so I'm not in that database.
We'll talk offline, Chris. We'll talk offline. All right, perfect. So yeah, that's just a fun query here to see if there's any anomalies in the data set. We also seem to have a huge fan of Frankenstein, the book. All right, so this was really a quick one on how you can explore data, find some insights in the data, plot it. Obviously, this is something you encounter a couple of times working with data, how to quickly visualize and see if there's any anomalies. All right, so we can close this notebook. And we do have a second one. So for all of you that have an up and running Redshift cluster, This is the requirement for this notebook. It's basically just executing a couple of similar questions. So you can do a run all. And here we're basically just querying the data through Redshift. And we're running a couple of simple and same queries, like which product categories had the most reviews in 2015. So you can see how you run the code here with Redshift, basically. All right, so I'm not going to spend too much time on this as it's kind of the similar questions we're doing here, but feel free to see if you want to look at how you run this through the Redshift integration. And obviously, we're limiting the queries here to 2015 pretty much and 14 for the sake of having the trends here in the data that is stored in Redshift locally. All right, so yeah, I'm not going to go too deep into this. Those are pretty much the same insights. And with that, we're coming to the 03 notebook, which is showing you how you can analyze data quality using a service and a capability of SageMaker called the processing jobs. And I saw in the chat that a couple of you have asked about Spark. So obviously Spark is also very popular, especially for some ETL jobs, batch transformations. And I'm handing over here at this point to Chris, who will show you how you can use a tool called DQ to run data quality checks at scale using those processing jobs on SageMaker, and also gonna start talking about Spark. All right, Chris, are you ready?
Yeah, give me 1 sec here. I'm switching over to my AirPods.
Sure.
Turn on my camera. Okay, find my Zoom window here. Yeah, by the way, a lot of great questions. A lot of really, really good questions. Yeah, Ancha, there's a few people over on the Zoom chat that are hanging out there. Might want to move them over. So check on that. Let me grab the screen.
Look here in a sec.
Okay, move my thing out of the way. Okay, and okay, coming here in a sec. Switch it over to AirPods. Yeah, 10 more seconds here. Okay, sharing the screen. Yeah, so a lot of great questions. Folks are hitting some edge cases. Ancha, someone pointed out, do you remember that when we had to do the insert into for Redshift, instead of using the load from S3, we're like doing it row by row, which is not efficient. So someone pointed that out, that that's not efficient. And I seem to remember, I have to talk to you offline about it, but when we were designing this a few months ago, putting it in the book and creating these examples, we knew that that was not optimal. Obviously, you would want to use Redshift's load capabilities. It could do things in batch much more quickly, but there was a reason. I think it was related to the date field, maybe. There was something going on with the date field.
Yeah, and the point that we're inserting from a whole table, I think there was discussions like which one is better to use. And yeah, there's definitely an important point to consider. I think the insert into works well in this case because we're loading in a complete kind of loading up like the full table, basically.
Okay, cool. All right, so, and I think I've answered everything on that in Slack. All right, so right now, so yeah, Ancha covered like visualizing the data, and now we are actually going to do a step in the machine learning pipeline that I feel is probably the most critical, which is data quality. And if you don't pay attention to data quality, you will have issues downstream. So upstream is kind of data coming from the applications coming in to the data pipeline. And so data quality issues could be, things like we start seeing star ratings of 0 that we're not expecting. Someone actually suggested that we do star rating 0. So hopefully not to give this workshop a 0. But so if you start getting fields that your machine learning models are not expecting, you want to know this, because if suddenly you start making building and training models with strange distributions of data, then your models will end up being skewed. So data quality checks can also look for duplicates. It can look for missing fields. All of the stuff that we saw in the autopilot section, you can actually do that plus quite a bit more with DQ here. And give me one sec here. Apologize. I have to turn off the Slack notifications because they're going to drive me nuts for the next few minutes. So give me one second. Okay. So let's just take a quick look again at our schema. So, this is the data that we're expecting, product IDs, of course, helpful votes, the total votes. So with each review, there are other reviewers that could say whether or not that review was helpful, thumbs up, thumbs down. So helpful votes and total votes are typically correlated. Obviously, one goes up, the other one goes up. So we'll take a look at correlations as well too, statistical correlations. The other ones, so because this is the beginning of our pipeline, the review body, yes, I want to point out that the review body is the field that we're going to use to predict the star rating. So we've already done this with Autopilot and with Comprehend. We fed in reviews, the text, and we got back a star rating. And so that's exactly what we're going to do. So this is the start of our pipeline to create a custom BERT model. Okay, so before we were using Autopilot, which has its own NLP techniques. Then we use Comprehend, which has its own way of doing NLP. And now, so maybe those two don't necessarily work for us. And again, we have small data today. We have the potential of the 150 million reviews, but to keep the processing down and to keep this workshop moving ahead and to keep people's interests, we chose a small subset. But just know that for the book, for example, we've run training on the entire data set. It takes a couple hours, but we get 97% for star rating text classification. So yeah, pretty powerful stuff. So let's say those two particularly, so let's say Autopilot maybe doesn't work well with our data, or Comprehend doesn't work as well, and we're want to do something a little bit more accurate or a little bit more custom. Maybe we do have a German corpus or something that those other two can't do right now. So we would want to build our own BERT model, and that's what we're going to do. So this particular section, let me introduce this concept here. So these data quality checks, and this is based on this open source project DQ. So we had already shown the open source project AWS Data Wrangler. There's this second open source project I really like that's called DQ that actually uses Spark beneath the covers. And so we are actually going to spin up a serverless Spark cluster, pay-as-you-go cluster. That's what serverless means to me, is I'm going to spin this up, I'm going to run the job, and then tear it down. And this is actually going to take a look at our data and tell us if there's quality issues. And quality issues, there's some standard ones. So DQ can figure out that all of the columns, all of the star ratings are between 1 and 5, and so it'll tell you if things go beyond that range. We can also define our own custom constraints as well too. So think of these like unit tests for your data coming in, for new data. If those unit tests don't pass. If you come from a development background, this makes sense. You know, think of just kind of isolating the rest of the world and just looking at this data. If this data doesn't pass my quality checks, then stop the pipeline and figure it out. At Netflix, I was part of the streaming team, which was feeding the machine learning pipeline. So every time that like you press play or fast forward or skip, that's all being recorded, and we use that to then create recommendations, right? This is what like Netflix did. And being on the streaming team early, we were still developing what was called the video or the viewing history service, or VHS was kind of the fun name for it. So the viewing history service was changing on a like bi-weekly basis. We had 2-week iterations, 2-week sprints, and we were always adding new fields into our data pipeline. We would accidentally, you know, like null out certain fields and have empty strings. And so downstream, the BI folks, the data scientists, data engineers were like always getting mad at us because we were the sort of upstream application folks that were screwing everything up. So if we had something like this, which Netflix actually ended up building, something to do this kind of detection up front, this would have helped quite a bit. And we, you know, in like my experience in this big data and data science world, this is the biggest issue with like data pipelines, is these data quality checks, or the need for like data quality checks. Okay, so, and I keep scrolling right by it. I'm going to introduce this concept called a SageMaker processing job. So these processing jobs are super simple. You provide a script or your own Docker image. So this is Python script or your own Docker image that maybe has some more complex code in there. You hand it to SageMaker, and SageMaker does everything for you. So SageMaker will map an S3 bucket so that you can get data into the Docker container. Because keep in mind, SageMaker is all Docker-based, basically. So, you know, while we might be specifying probably different instance types, like we want a GPU instance with, you know, 16 GPUs and, you know, 64 gigs of RAM, something like that. All of SageMaker runs on Docker. So you can actually provide your own Docker image also. But the simplest way is to just provide a simple Python script, which we'll actually show in the next section, I believe. In like this case, because processing jobs are fairly new, and they came out in December, they don't quite yet support Spark as a first-class citizen. We are adding Spark support right here today. And by showing you how to use this Docker image. So we are actually bringing our own container with Spark, and it's Spark 246, and can talk to like S3 natively, all the good stuff. So you don't need like Databricks for this. You don't need EMR for this right now. This is just SageMaker. We are inside of SageMaker. And so processing jobs are super flexible. You would map an S3 bucket for the input, and then inside the container, all you do is just reference opt ML processing input. That's a directory that is mapped to the S3 bucket. And when you're done processing, you would then map it and place the output into the /output directory. Then that gets mapped to an S3 bucket, which you can then feed into the next piece of your pipeline. So this is the very, very, very beginning of our machine learning pipeline. We'll explore the whole rest of it in the next couple hours here. So we've got the inputs, the outputs. Now, the input for us is the raw TSV files, which we could feed in Parquet, by the way. And Spark loves Parquet. For this example, to kind of anchor it to the examples we were showing before, we're going to stick with the TSVs. Spark can work with TSV and like Parquet with just one line of code difference. So it doesn't really matter, but for this purpose, just to keep things simple, we're sticking with TSV. There's times when we do this workshop and not talk about Parquet. That's why we stick to TSV. But this is a case, and we didn't want to couple the quality checks with Parquet. So we wanted to keep this simple. So raw data comes in from an application, lands in S3, and now we can run this data quality check. There's no reason to port it or to like convert it to Parquet. So that was the other reason why we're using CSV. So do a run all up here. Run through this. It's going to create this Docker image. Now, processing jobs, I have a feeling will get first-class Spark support soon. I don't know when. I don't have a roadmap, but I asked for it on a weekly basis from the SageMaker engineering team. Until then, it's very easy just to use this exact Docker image. And yeah, so you can grab this off of the open source or GitHub repo. Building the Docker image, pushing it into this, into these temporary Amazon accounts have this service called the Elastic Container Registry, which is basically Docker Hub, but private. And so pushing it in, these are our details. Data scientists typically don't really, need to know about this stuff or want to know about this stuff. Some people do, so we're showing it here. But at the end of the day, what we get to is, so here's our script. Now there's a slight problem here also, a slight speed bump with this narrative of DQ. DQ right now supports Scala Spark. And I know all of you PySpark fans out there, we just talked to the team on Friday, and they are supposed to be releasing something very, very soon. Can't say when, but PySpark support is coming for DQ. So for right now, we have to create this little shim that goes from Python and calls out to the Scala code. So this is actually going to change before the next workshop. I can yes, give that away, that this will change to be using PySpark here. But for now, if you're not familiar with Scala, don't worry about it. I'm just going to explain the code here. These are the DQ imports. So keep in mind that DQ is like a domain-specific language, DSL, that sits on top of Spark. So we're not necessarily doing the Spark jobs ourselves. We're using the DQ API to specify these constraints, the min and max on star rating. We can also use this DQ to recommend new constraints. So yeah, which I'll show here in a bit. But let's get this started here. So here's the Scala code. Here we're just defining the schema. Here is the Spark code to read in the data. I mentioned before, with one line of code change, you can change this to Parquet and maybe simplify some of these options. Don't necessarily apply to Parquet like the separator. But with one or two lines of code, yes, you could read from the Parquet files. And here we go, setting up some of the things that we're looking for. We're looking for correlations. We're looking to make sure that, or we want this to calculate the mean star rating, the average star rating. We want to count the number of our reviews. And here we're actually using hyperloglog, which is an approximation technique to get you a count within 2% error. And so sometimes this is fine, and it's much, much faster than doing a full distinct count, by the way. But if you're trying to count pennies in a financial situation and make numbers add up, certainly don't use approximations. But for this kind of stuff, social data, right, like video stream data, it's pretty good to just have an approximation, especially if this query comes back in seconds versus hours or minutes. So size is a distinct count, by the way, and approximate counts, size is actually all the records. If there are duplicates, they would feed into that size. The approximate count distinct is going to use hyperloglog. Correlation, so we'll look at correlation between total votes and star rating, as well as total votes and helpful votes. All right, we're just, and so at that point, we would run this. So this actually runs right here, runs the Spark job for us. We then get the data, we save it out to S3. That's going to go to that output S3 bucket for our processing job. Next, we're also going to, so this is actually generating metrics about our data set. Now we're actually setting up constraints. And so checking that star rating min, star rating max, like I said, checking to make sure that the review ID is unique. Sometimes upstream application teams have a bug in their code where they might be logging the same unique ID. This could screw up lots and lots of downstream tasks like machine learning. Also checking to make sure that there's not nulls. That's what the is complete means. Also checking that the marketplace falls within these 1, 2, 3, 4, 5. At the time, between the years 1995 and 2015, these were the primary marketplaces. And so these are the only 5 fields we should ever see in that particular data set. We could also specify minimum size. This is good when we already know approximately what the size of our data set is. If it ends up where this comes in, at 0, or let's say comes in at 10, and we're expecting 2 million, we would want to know, and that would trigger an error, and this could potentially halt the pipeline. We could wire it up to like an SNS notification, which is the notification service by Amazon. You could page the data scientist on call at 2 in the morning. All right, here we are writing out more data to S3. That's the output of our constraint checks. And so this is what actually sets up the processing job. So that Docker image that we created up above, that's called bring your own container. That's the sort of informal, loose term for what the container that we are bringing to SageMaker. Now, in the next section, we'll show an even easier way, which is just provide a script. And the container is provided by SageMaker. These containers are all open source, by the way, so we can certainly go and look at what's inside those containers, or even extend the SageMaker containers and add your own stuff in there, and gives you a little bit of a nice balance there. Instance count 2, so again, we are specifying instances. That's more so to give it a profile, but these are running as containers on these instances. Small, like little detail, but Spark likes RAM, and so we give it the R series, which is RAM optimized, meaning it has more RAM for similar CPU that are in the other instance types. Okay, the input data is our TSVs, like I said, and we're just kind of doing some naming of these things so we can find them later and look at them in S3. And this is what's actually running the processing job. So here's that Python script that actually calls into the Scala script, a little bit of a speed bump, I know. And we are actually, we're specifying the inputs and the outputs. And this is the S3. If you go back up to the top, I don't want to scroll all the way up to the top too quickly, but if you do go up to the top and see, for processing jobs, they all have an input and they all have an output. And we're telling it where to put the input in S3, or where the data comes from in S3, and where to place the data in S3 on the output. That way we could deterministically find that data later once the processing job is complete. This is actually to get around a bug. We're actually passing everything in. Here, I think this bug has been fixed, so I could probably remove that. I have to remember to do that. All right, we put in these deep links. So I've already run this, and we could go look at the Spark job. But before I dive into that, I just want to show you the output. Okay, so this processing job shows as in progress. If you rerun the cell again, it'll say complete. So I would do run all here, like I said, and let's just go down and then take a look. So while we're in the context and I showed you the code, I want to show you the output, and then we can go back and look at the actual details of the Spark job as it ran on those containers. Okay, so looks like all of our constraints that we specified, everything looks good. Completeness constraint, minimum, maximum of star rating, all these are good. Marketplace, successful, no error messages, so all that's okay. And then this is some of the metrics. So completeness, 1.0 means it's fully complete, meaning there are no nulls in the review ID. The hyperlog approximation is 238,000. We also see that the actual count is 247,000. If you figure out the difference, which I know some of you are dying to do, pop open your calculator, figure out the difference, that will be 2% or less, meaning, and you didn't really see this in action because it was inside the Spark job, but this approximate count distinct happens way faster than this size full scan here because of the way hyperlog works and the mathematics behind it. We see total votes and star rating are not correlated, even a tiny bit negative, and we see total votes and helpful votes are very highly coordinated. So, correlated. So if if suddenly we start seeing, negative correlation where we're expecting positive, or correlation going down towards 0 when we expect it to be closer to 1, something that could be wrong with our data, stop the pipeline. And if you've, so I'm sure most of us on like this call have experienced data quality issues, even just inside of your notebook looking through pandas at a CSV. There's like always quality issues. This is at scale how you would detect these issues. All right, just some more here, some more checks. Now, this is the cool part. So I had mentioned before that DQ, one of its like unique features is that it can actually suggest new constraints that you didn't think of when you first put together this Spark job and this DQ job. So things like, so some of these are probably, like pretty straightforward. Let me get to the one that's pretty interesting here, which would be verified purchase. So verified purchase is a field where, yes, Amazon can make sure that you actually did purchase the product, that you didn't return it maybe, or something. I don't actually know the exact rules, but the value of verified purchase can either be Y or N. And that's something that we did not put in our Spark job, our DQ job. So I could literally copy this code exactly. Yes, I don't have the data frame showing the full code, but I could copy this code and put it right into that Spark job, that like DQ job, and all of a sudden I now have yes or no checks. So these are things maybe that we didn't catch. Didn't think that the review body has less than like 1% missing values. This is the current state. So this is the ground truth. This is the baseline. And then things from here you would add, more and more constraints as more of these assumptions are found. Okay, so, and then real quick, I promised I was gonna go into follow these deep links here. So I'm gonna click that. It's gonna pull up the CloudWatch logs. This gets me right to the Spark job. I'm a big fan of deep links because when I'm looking at somebody's code or working on something, I want to go right to the next thing that I'm thinking, which is, okay, show me what the Spark job actually did. Maybe I have to debug something. So those of you familiar with Spark are gonna probably cringe when you see all this, but DAG scheduler and block manager info, that's always my favorite. And here's my Spark code. I was actually dumping out. I was like dumping these data frames. These data frames are small because keep in mind, Spark is doing the heavy lifting in the SageMaker processing job cluster. And all that I want back is the summary statistics and the summary constraint checks. So you could drill into that all day long if you want. The context cleaner. Okay, and we could click on the S3 output data. This will take us right to S3 where that data was written. Click the output and we see all 4 of these, and these are just CSVs. They're called part files. That's just in big data land when there's lots of instances. Each instance makes up a part of the final result. And that's just what this is called. I actually, because these data frames are so small, because they're just summary statistics, I actually merge them into one before writing it out to S3, just to keep things simple. So I could actually have 10 nodes here, but one of the lines of code in my Spark job is to coalesce and get them down to one file. That's typically not recommended when you are, the output is very large, but for small outputs, it's fine. And keeps things down to a single file. All right, and I think I want to jump right in. Now, people were asking about lunch, and we've been going for about 4 hours. I do want to cover this. So, okay, we've done the quality checks. So congratulations, our data is clean. We can continue on with our pipeline. At this point, we need to convert our raw text into something that BERT can actually do something with, which is numeric values, vectors in BERT's vector space. So we haven't talked too much about BERT, but just know that BERT has been trained on millions and millions of documents. It's been trained on Wikipedia. Some BERT models have been trained on yes, like Reddit, like LinkedIn information. This particular BERT model that we're using is the public. It's like the open source one that has been trained on public Wikipedia data. It's been trained on Google Books corpus, so millions or thousands of books. And BERT has created a vocabulary and a vector space that we need to now project our data, our Amazon customer reviews, into this vector space. And so just like any vector space, or just like any learned representation, right? We're going from one representation, which is text that makes sense to a human, we're converting it into this alternate representation, which makes sense to BERT and the machine. So to do that, we are going to use BERT as a tokenizer. So BERT can be used in 3 main ways. And one way is to just tokenize. So BERT's already been pre-trained. Now we could use BERT to take our raw text and transform it into BERT's vocabulary, BERT's feature space. And so again, we will rely on processing jobs. We're going to use scikit-learn to balance the data. We're going to use scikit-learn also to do sampling, all kinds of fun stuff. But the heart of it will be TensorFlow. And then we're going to use this project, it's a very, very popular project, 30,000 like GitHub stars, called Transformers by a company called Hugging Face, which we will cover extensively very, very soon. So the goal here, like you can see, so star rating stays the same. Star rating is our label, so we're not doing anything with that. It's fine the way it is. Star rating 1 through 5, categorical. But we do need to convert the strings into these vectors. And I just have sample like numbers here, but so BERT's vector space has 30,000 dimensions. Some of you might be familiar with Word2Vec that actually had 300 dimensions. BERT has 30,000, and so so that's the total vocabulary also. And some of you might think, okay, 30,000 is maybe not enough to learn language, and yeah, so check it out. Yeah, so we'll show you here in a bit how BERT actually does this. And okay, so that's the overview. Now, the way I operate is I like to do ad hoc sort of in notebook sampling, and I want to just make sure that I understand these libraries. For example, transformers. Yeah, TensorFlow, some of us probably know. You don't have to know too much about TensorFlow here, by the way. It's like pretty minimal. Transformers does quite a bit for us, and we'll use Keras, which is a higher level API that's part of TensorFlow that makes things a little bit simpler. Okay, so we will rely on transformers. This is the tokenizer. Now you'll see this term distill BERT. We are using a slight variant of the base BERT model that's called distill BERT. This is called distill BERT because it was trained using distillation, which is a teacher-student type of model. So the short of it, separate from all the academic stuff, which you could look up, is that distill BERT retains 97% of the core accuracy of base BERT, but is much smaller and much faster than base BERT. So pretty cool technique. I definitely recommend the paper. Just go Google distill BERT, you'll find it. But let's focus right now on just tokenizing, or just converting into this feature space. So this part here. So that's what we're focused on right now. Okay, so I'm going to introduce this hyperparameter called maximum sequence length. Maximum sequence length is the number of words, or technically tokens, and I'll explain the difference here in a bit. We have to tell BERT. So this is something that is just standard with BERT. This is just how BERT was designed. You have to tell BERT what is the maximum sequence length, the maximum number of words that you want BERT to focus on, basically. So you would choose the value based on your word counts from all of your reviews. So from each review. So you would run some query to split your to split your data set and look at the number of words. And you'll see some sort of distribution and then a long tail, right? So maybe pick 80% of that, 75% of that. And we've chosen 128, so we typically like to stick with binary numbers. BERT likes binary numbers, all systems level things like binary numbers, the way the hardware works. So we've chosen maximum sequence length. This is a hyperparameter. This is something you have to test on your own data set. Our data set that we're using today works well with 128. Just know that if you do have a sentence or a review that is longer than 128, it will get truncated as far as BERT is concerned. If you have one that's less than 128, BERT will pad. Okay, and I'll show some of those details here in a bit. Probably lots of questions on the chat about this on Slack. Just know, just like any other hyperparameter with machine learning, this number may not work for you. This is something that does need to be tuned. The reason we bring it up here specifically is because this is a hyperparameter that needs to be set during feature engineering. You can't create project your reviews into BERT's vector space with 128 and then go and train using 256. These numbers have to match. So we're choosing 128 right here and now. We're telling it which fields of our data frame that we're interested in, which is review body. We're just skipping the review title and the review headline for now. All we want is just a review body. It's just a decision that we made to keep things simple. We say what the label column is. We give it these potential label values 1 through 5. And now there's a bunch of code here to get this into a format that TensorFlow wants and BERT wants. So first thing that we'll do is use that Hugging Face, that DistilBERT tokenizer that we pulled in there. If you are using a different variant of BERT, which there's many, many variants of BERT. There's one called German BERT. There's one called BERTje for Dutch BERT, similar to Antje's name. You just add a JE onto everything, I guess. If you are using different variants, you need to use a different tokenizer and use the tokenizer specific to that variant. Because certain variants, like German BERT, does not have the same vocabulary as the English BERT, for obvious reasons, different root, so different roots for the words, different, so physically different characters, things like that. Okay, so we're going to use this tokenizer and transform our text, and we have to specify the max sequence length. We have to tell it to pad, yes, and we're going to end up creating. So this is the feature engineering part. We're taking one human readable string and we need to create 4 vectors. And these 4 vectors get passed into BERT, and BERT knows what to do with the vectors. Our job is to get our raw text into these 4 vectors. And so that's what we're doing here. Just real quick, the input IDs are those numbers that I had shown on the overview. These numbers are these represent the token or the word in the BERT vocabulary. Okay, so these aren't really, they're human readable because they're digits, but they don't really make sense unless you have the 30,000 word vocabulary in a monitor next to you. Not really that important, just know that that's what we'll see here in a bit. Input mask, this helps us determine when padding. So yes, I'll show you here in a bit, but when we do pad, all the rest, so we'll put 1s for all of the values that BERT is going to pay attention to, up to 128. If there are less, then the input mask will have 0s. I'll show you. This will be much easier to show you here in a bit. Segment IDs does not apply to our task. We're doing classification. Segment IDs is used when we're doing question answer or sort of FAQ tasks with BERT, which we are not doing today. So yeah, it's very interesting research, very interesting use case, but for today, segment IDs just all are 0 right here. And then label ID is going to be the index of our labels. So our labels are 1 through 5. If you put that into an array, they're 0 indexed. So the 0th index is 1. The 4th index, 0, 1, 2, 3, 4 is, the 4th index is going to be 5. Okay, so that's our little helper function. One other part of the feature engineering. So we're first going to get convert raw text into these arrays. The next section is to convert the arrays into TF records. TF record is kind of like Parquet. It's not readable. You know, once the data is converted into Parquet, I can't open it up in my file explorer and read it. It's binary. The implementation is using protocol buffers. That's an implementation detail. Just know that these are still rows of data. That's unlike Parquet, which is columns of data stored next to each other. These are still rows of data. And because and I mentioned this on the chat, machine learning workloads operate row by row. Whereas with analytics, we're looking at columns and we're summing columns, we're averaging columns, doing standard deviations on columns. This is still storing everything row-wise, but it's just compacting it. It's doing some possible compression, run length encoding, things like that. Okay, so here's some sample reviews. And all we're doing here is just converting it into a format that we will then use as training data to train our BERT model here in a bit. So here's all of our tokens. Here's those numbers. And if you notice, these numbers end at a certain point. And that is reaffirmed by the input mask. This tells BERT to pay attention to everything for the first, I don't know, whatever this is, 50, 60, or let's see, 20, 30, maybe 30, maybe 35 words. And then all the rest are zeros. So here down to here, and then here down to here is all zeros. So it's just an optimization that seems not like an optimization, but does help BERT when BERT is doing its processing. The other thing I want to point out is this sentence actually ended up, while it has a certain number of words, the number of tokens actually differs slightly. So BERT's vocabulary has the word anti and the word virus as separate words. And this parsing, or some people possibly call it stemming. It's not really stemming, but think of it where BERT BERT knows about fundamental, or portions of words, or potentially full words. But this is an example where it's anti and it's virus, and the combination of these two obviously means something else. But the pound shows when the tokenizer actually split the word into two things that BERT will know about. The details of this, there's a project called Sentence Piece, or I think Word Piece. I think they're related, but if you Google Sentence Piece, this is a very, very hot topic. There's probably lots of questions right now. How is the parsing being done? I know about stemming and different types of phonetics and so where does all this linguistic information live? And it's in a project called Sentence Piece. And Sentence Piece, I believe, comes out of Google Research. It's used by BERT. And so just know that this is a very key part of BERT's processing. And terms like no-brainer, which might have been, see, 2 words here, actually end up as 3 tokens. So this is the difference between a word and a token. Okay, and sometimes, I would have expected need to be split into need and then ED. I don't know why it isn't, but just as long as the same parsing is used for feature engineering that was used when BERT was pre-trained. So BERT has been pre-trained. We, in the next section, will actually fine-tune BERT and give it our data and then make predictions that way. So we can fine-tune models much, much quicker and with really good accuracy with a small set of data from our domain. Okay, so, and there's our label ID. So again, 5 like ended up being the 4th index. So that's why it says 4. That confuses me almost every time I look at this. Let's see. Yeah, so you can take a look at that. So this, oh, and then this is TF record. So once we've created those 4 vectors, now we have this binary blob of TF record. It's a little bit readable in some cases. You could see segment ID is the word, but just know that this is the format that TensorFlow prefers. PyTorch does not have this. PyTorch, as far as I know, does not read TF record. Yeah, so there might be some community project that ties them together, but last I spoke with the folks from Facebook and PyTorch community, they do not have the equivalent of TF record. You would just point it to the CSV files. And okay, let's go to the next one here. So I did this ad hoc with a tiny amount of data. I did a couple small feature engineering tasks here on these 3. And just to make sure that my code works. The next step is to scale this, because we have lots of data. We want to run this in parallel across multiple instances. So I'm going to scroll to the top here. So once again, we go back to processing jobs, our old friend processing jobs here. Processing jobs, again, super simple. My inputs here are going to be the raw data, just like I did in my ad hoc notebook. The output is going to be TF record. And all of that, I'll pass in where I want the input to come from, which is the same TSV we've been using this whole time, the same path. And then output is going to be someplace. The other thing that we do in this processing job, by the way, this feature engineering, is we'll split the data. So we could balance the data, we could split the data, and we're going to convert raw text into BERT tokens. Okay, so here's the input data, same thing that we've used everywhere to keep things moving along. We just use the 2 files there. And here's our script. And I keep meaning to change this to pigmentize. Makes it a little bit more readable. Oop. Do that. Okay. But yeah, did I mess this up here? Do a refresh here. So let's take a look at the code. Okay, so I'm just going to keep it for @cat for right now. It's not, well, actually, for your purposes, I'm going to change this to pigmentize. Okay, so a bunch of imports. So this code should all look familiar. This is the same code or similar code to what we did in the ad hoc in that notebook. So the exact same thing, pulling in the same tokenizer, data column, review body, label values, all the good stuff, input features. Here I have a little bit more notes here for myself, basically. We're doing the exact same thing, tokenizing it, converting it into these tokens, doing the padding. This is the exact same thing here. Converting it into TF record. So the only difference here is because we're doing this at scale, and each instance will be operating on multiple files. So I have to iterate through all the files. I could do this in parallel. And the other thing too, that's when we run this in SageMaker, SageMaker gives us things like, so how many hosts are in this cluster. So this is sort of SageMaker service. When I spin up this cluster and say I want 2 instances, I will get the list of those 2 instances inside of my script. I can do whatever I want with that. Typically, probably don't do much with it unless I'm doing some something very low level, very specific to a full cluster. But yeah, so this is fine. This is just doing stateless operation of doing transformation. So input data, here's my split percentage, validation and test. I'm balancing true or false. Here I'm actually specifying false for the default. That's because I needed more data. So keep in mind that while we did balance the data earlier, we are not balancing the data here. And it's because we have a small amount of data. If we do balance, like we saw with the AutoML, we get So not so good results. We would ideally be using all of the data, but again, it takes too long. So a little bit of a speed bump in the like narrative there, but and then max sequence length. So again, this has to come through in the feature engineering, which is what we're focused on here. So here's just another little function here to read in the data. If we're balancing, we're combining information Ansha showed earlier, where we have 5 stars through 1 star, getting the minority counts. I just lifted this code directly from all that. Resampling, downsampling, and splitting the data. So first we balance, then we split. Now, in our code, I'm going to show you here in a sec, that's false. So we're actually using all the data, but we're still splitting. So the input is a single path to all of our files, so our like TSVs. On the output, it's going to be train, validation, and test will be 3 subdirectories that will contain TF records that will then pass on to the next. So in the previous DQ section, we showed Spark processor, a sort of generic bring your own container processor, and pass the Docker image. In this, because we aren't doing anything special like Spark, it's just scikit-learn, these processing jobs support scikit-learn natively and have their own Docker image, which is all open source. And you just specify framework version. So I would specify, 0.20, 0.23. Give it, the role. This is just normal Amazon stuff. And then instance type, which is going to be a C5 series, being CPU optimized. R series is RAM optimized. M is generic. And what's the other one? P is GPU for some reason. I guess the P in GPU. And I'm saying use 2 instances. And I'll get to that here in a sec, why we're using 2. Okay, so I'm giving it 90% I want to use for training, 5% for validation, 5% for test. Maximum sequence length, 128. This is what we're going to use for the whole rest of the workshop, basically. Balanced data set, again, I'm setting to false. If we set this to true, it gets downsampled so low that the performance, the accuracy looks really bad. The downside, of course, is that we will have a potentially skewed model that is artificially predicting 5s for everything. And in fact, some of you might have already run this and jumped ahead, and you'll see that we are always predicting 5. It's exactly because we're not balancing the data set. So just sort of proving in this particular case how you shouldn't do things, but still showing you how, but also telling you where you could improve. Okay, or where we all could improve. So again, a single input goes to the input data for the raw TSVs, and then 3 output directories. So this will create 3 separate directories: BERT train, BERT validation, and BERT test in our S3 bucket. Passing in arguments. Now notice I'm actually giving this hint to SageMaker for the inputs to say shard the data. So we have 2 files. Yes, if you remember, we have 2 files, these 2, and I have 2 instances. And so in this configuration, SageMaker, because I've told SageMaker to shard the data, will take each file and place it on a separate onto each instance. So each instance gets 1 single file. And this is all happening in parallel using all the cores on each C5 2XL. Okay, all that data then ends up, so here's these deep links. Let's get to that in a sec. And when all is said and done, we have our 3 directories. We have train, validation, and test. So notice the file size. These are pretty small. Once they're converted to TF record, they become much smaller. And these, because they're only 5% each, are much smaller. Now, we use training data set to train. We use validation data set to try out different hyperparameters. For example, we could try 256 for the max sequence length, or try things that are specific to our classification, which we'll show here in a bit when we add Keras on top of the BERT pre-trained model. So yeah, not quite there yet. And I'm going to store all of these variables here because we're going to track this all in a complete end-to-end experiment. Okay, and I could show you, one thing I like to do is have these deep links. So I'm going to click on these. And I go right to CloudWatch. This is going to take me to my cluster logs. I'm going to pull up the first node. And these are actually print statements that I put in my script, my scikit-learn script. And here's my splits. This is just debugging information for me to go in. I'm dumping out the max sequence length. I see the number of CPUs. I see all the environment variables that have been given to me. I see the file that SageMaker has sharded, or sorry, the file that SageMaker has decided goes on to this instance because of the sharding. Now, SageMaker won't shard within a file. So yes, most of you probably are thinking, well, can it look at the file sizes and split the files? And no. Yeah, SageMaker is not doing that. SageMaker is looking at the file count and just round robin putting them onto different instances. That's currently not something that you can override, but helps quite a bit. Okay, and then I just list out things so that I know that things are working here inside of the Docker container that kind of left over from development, but keep it in because, okay, and then, oop, I'm in the wrong one there. All right, and then I could look at the output data. So let me actually jump right over. The output data here, train, so this is the exact same data. When we look at it here, I had pulled it down locally and looked at it from, so when the processing job completes, it tells you where the S3 location is for the output data, and that's where it ended up. And that's really where we told it to put it, so shouldn't be any surprise there. Let me see, where do we specify that? Yeah, somewhere we specify that, and it's placed it there for us. Okay, so yeah, and then this is just pulling down that data down to the local notebook. Okay, and then logging everything. I'm going to skip the Spark version of this, but you can do this with Spark. Spark can generate TF records, and I've actually, in this code, created a user-defined function, Spark UDF with PySpark. This is full PySpark, no Scala. And the UDF uses the Hugging Face Transformers library, just like you would use any library in a UDF, and takes raw text and creates TF records, and then writes out TF records. So pretty cool. I'm going to skip it for now and go directly to the, oh, and then I could show you, oh, yeah, so, yes, I already showed you the code. That was the pigmentize. Let's jump into train. We'll start the training and then take lunch break. So, okay, congratulations. We've created TF records. We can now actually start the model training, right? Okay, so there are many options within SageMaker. We've already looked at autopilot. We've looked at autopilot notebooks that are generated. We're currently using SageMaker notebooks. This is kind of the like overall or part of the SageMaker sort of ecosystem here. We could also use built-in algorithms. We have pre-tuned, pre-optimized algorithms for things like XGBoost and linear regression. We've got things that could do forecasting, right? And like the ARIMA models, something called Deep AR. Yes, all that stuff's built into SageMaker. We are actually opting for bring your own script because we are bringing our own BERT model that we want to try out and compare to comprehend and to compare to autopilot. Or maybe we just built our own algorithm and want to run it on SageMaker. And so that's exactly the focus of our book. The focus of this workshop is bring your own script. Sometimes we had to bring our own container. I see this, so we saw this with Spark, and that's because processing jobs are so new that they don't yet support Spark. So we just bring our own Spark container. You saw how simple that was. We do see customers that have their own Docker pipeline where they're building custom Docker images that have to go through their security folks and get scanned and have their own requirements. And all they want to do is just run those Docker images on SageMaker. That's totally doable. All SageMaker does is just wire up then the like S3 buckets, does the sharding. There's also something called pipe mode that we'll talk about in a sec that can move data between S3 and SageMaker super fast. Like really cool TensorFlow specific like implementation that we use here today that plugs right into TensorFlow as through the like TensorFlow dataset like API to pull in training records. And then also we'll show later where we'll automate this as a step function. So end to end, we'll do all of these steps. So here we're just showing you the basic building blocks and then tie everything together. You can also use Kubeflow pipelines. You could use Airflow. We just choose to use step functions here because we were curious how it worked, and we're like writing a book about SageMaker, so yeah, we put it in there. For the book, though, we also do have Kubeflow. For today, we also do have Kubeflow as well too. We have to move pretty quick and then get to that right after lunch, hopefully. Okay, I'm going to skip this. This is a scikit-learn cheat sheet. If you're just starting out with machine learning, really good. Follow this flow chart. We are ending up in this classification upper left area. We are classifying our reviews with a star rating category, and categories 1, 2, 3, 4, 5. These categories happen to be ordinal and they happen to be numeric, where 5 is greater than 1, but we're still treating them as categories. This is not a regression problem. We're not trying to predict 3.2, 2.1, and that's because the data that we are given is only 5 numbers, 5 categories. A user, when they're giving a review, can't do 2.2. They can do 1, 2, 3, 4, 5, right? Okay, so let's keep going here. Similar, okay, so now we're in training land. We are using a pre-trained model. So BERT has been pre-trained by the researchers, by the people who created BERT. We've done feature engineering, where we now express our domain, so our data in BERT's like vocabulary and feature space. Now we're going to combine the two and train a super thin classification layer that's specific to our 5 categories. And with that, we'll use Keras and TensorFlow. So we see TensorFlows coming in here, transformers, of course. So what we're doing here at a really high level is we're building a neural network where the first layer, so this is kind of the bottom first layer, the first layer is BERT, and BERT has a whole ton of layers beneath it. But we're treating this pre-trained BERT just like a black box. We will open up the black box just a tiny bit to let some of the layers train. But for the most part, we just want to slap on a thin classifier and pass our data through and train that classifier. And we're reusing all the knowledge that BERT has gained about language from like Wikipedia and from Google Books corpus. But we still need to tell BERT and fine tune it to our specific domain and our star ratings. Okay, so that's the gist of what we're doing here. Now, we're doing this ad hoc. That's why the word ad hoc is here. This is not yet on a cluster. We start ad hoc. Here in the notebook, I'm choosing a small batch size. These are hyperparameters that will be tuned later. Yeah, Ansha, after lunch, we'll talk about hyperparameter tuning. Epochs, number of passes through the data set. I'm choosing small numbers here because I just want to make sure that my code doesn't break. That's kind of the purpose of this ad hoc exploration. Make sure that the code compiles. Well, this is Python, so this is just making sure that it the syntax is correct and that I'm getting some type of trained model. And then I'll let the cluster take over and then train on the larger data set. So here's some code here that's decoding TF record. See that down here as well too, decoding. I think here's some of the details. Here's a reference to pipe mode. We're not using pipe mode in the notebook. We will use it in the next notebook that launches on the cluster. This notebook runs within the notebook. And for those of you asking, why would I do all this when I could just use pandas? Pandas can only scale so far. Pandas can only scale to your notebook and the resources that are designed for your notebook. Going to the cloud is because we have large amounts of data. We want to get things done more quickly. We want to do things in parallel across a cluster. So just ignore pipe mode for a second. We will talk about that. That's what can get data to and from our SageMaker instances, our SageMaker cluster, between that and S3 quickly. In the notebook, we're just going to use TF record dataset, which is part of core TensorFlow. Pipe mode is something that Amazon brings that is open source. It's just, it is a TensorFlow extension that's optimized for S3 and for SageMaker. So here, this is just saying prefetch some of the data. Always want to do prefetching. We'll auto-tune the amount of prefetching. Prefetching is, especially for GPUs, very useful. Pulling data, getting data ready, pulling it off of disk or from S3, and then getting it ready to be piped in to your Keras job or your TensorFlow training job. Okay, I'm going to skip through some of this. Here, we're shuffling the data. Shuffling is very important. You don't want the model to learn data in which it's written on disk or presented to the training job. You want that data to be shuffled. If it's time series, don't shuffle the data. The network should actually learn the series that the data was written. But we are not doing time series here. We are doing classification. And classification, all you want to do is present the data to the model and have the model learn. You don't want the model to learn strange patterns about the order in which you are passing it in. So if, for example, I grouped all of my product or all my data by product category and was presenting it, the model always sees all product categories coming in together, the model will start to learn that that's a pattern, and that's not good. So in machine learning, randomization is celebrated, and in most cases, except for time series. Okay, so keep going here, different test or train validation test. So now we're setting up our neural network. So the very first layer of our model, of our network, is pulling in the pre-trained model. This is that this is that first layer in our network. And I'll print out the network here. In fact, let me run this. The first layer is the pre-trained BERT. On top of that is our classification layer that we're adding. And we're using this optimizer called Atom, which is a variant of stochastic gradient descent. There's some, with stochastic gradient descent, there are hyperparameters. These optimizers have certain hyperparameters that you will want to tune. And in fact, Ancha in the next section after lunch will be tuning learning rates. And that's something that we are just choosing because we happen to have some prior knowledge maybe from a previous project that we worked on, or we read an academic paper that said try learning rates of 3e-5 and try this epsilon. That's a good baseline. It's not going to work for everybody. That's why hyperparameter tuning is such a hot field, and we'll show that next. So the optimizer, with any sort of numerical optimization, which is all machine learning is really, we have to define a loss function. We have to say what the goal is. So loss function here is categorical cross entropy. Cross entropy is how you compare two distributions. We have a distribution of the confidence, for example, between 1 and 5. That's not the exact terms to use, but we have two distributions that we're comparing. So we use categorical cross entropy. And then we are trying to optimize the accuracy metric. And so we have an optimizer, we have a loss function, and we have the metric. And here we're just choosing accuracy. There's many different metrics you can choose, F1, so things like, like AUC. And here we tie everything together. So this is Keras here. This is just TensorFlow stuff, basically. Tying it all together, telling it to compile the model is the term. When it compiles it, this is what it looks like. And this actually tells us how many parameters. Now, BERT itself is like 1 billion parameters, whereas DistilBERT is only 66 million, which seems high, maybe to some, probably seems low to like others, depending on your background. This is actually pretty low. And also note that we are actually going to freeze that base layer. And I do that by saying the first layer, make trainable false. And I'm doing that, you can turn it to true. Training takes a little bit longer. This is that black box, basically. This is the ability, by saying false, I'm treating that base DistilBERT layer as a complete black box, and nothing changes inside of that black box. If I do set it to true, parts and certain layers of that base, like DistilBERT model, or that layer will get tuned, and those parameters could change. I'm purposely setting it to false here because I'm running in a notebook. I don't have huge resources here. That's what these clusters are for. And I want to just freeze that base layer and only train the top classification layer, which is used with this atom optimizer up here. And that's a much smaller number of parameters. That's on the order of 600,000. We see trainable parameters. If I change this to true, I would see all of the parameters can be trained. And that's not what we want to do right here. This is a hyperparameter. This is something we will pass in as a hyperparameter. It's something you can change. We do see pretty good accuracy without having to train the base BERT model, which is incredible. Okay, so here's where everything comes together. I'm going to skip some of this. It's just TensorBoard. Let's just talk about this here. This is fitting the model to our data set. Now, Keras lets us train and validate on the same data, or in the same run. Okay, so the same training job can do both training and validation. And so like I said before, validation is designed to test the hyperparameters, or to validate, I should use the term validate the hyperparameters. These hyperparameters are, of course, freezing the BERT base model, the learning rate, and this other hyperparameter. These hyperparameters are specific to that optimizer. So different optimizers have different hyperparameters depending on how they were designed and the mathematics behind it. So that's why you typically always train and validate together. And so this is expressed through the TensorFlow API, which actually lets you do them at the same time. Okay, and then separate, once we've found the best hyperparameters, we have this third holdout. These are called holdout data sets, held out relative to the training data set. This third test data set is used after we've done all the hyperparameter tuning. Now we can test the final product. And so this test data set is very important and should not be leaked into the training or the validation step. Otherwise this model will take into consideration this test data, and then we're kind of cheating. The result there would be you have an artificially high, artificially highly accurate model. And in the real world, when that model goes into production, you will actually have pretty poor performance, or could have poor performance. Now, I will point out the accuracy here is 64%. This is not coincidentally. This is this is related to the fact that we have an unbalanced data set. And so essentially this model, because the data, and yes, I know this is going to drive people crazy, and this drives me crazy, yes, every time I explain it, When you have an unbalanced data set, you have more 5s than you do 1 through 4, the model will always learn to predict 5. And if we scroll down and we see some of our sample predictions, just kind of jumping ahead, we'll see it is always like predicting, or seems to always be predicting 5. Just trust me, when you use more data and balance the data set. So once you have more data, if we actually open this up to all 45 product categories, and which is what we do for the book, we get really good accuracy. It's like 97%. All these numbers line up. The like labels are very highly like accurate. So just trust me. I know I'm like losing some trust with people by having this, by having to re-explain this, but you know, keep in mind that the goal for today is to get us through and show you how you can create highly accurate models, not necessarily how we can use this small data set to create highly accurate. Okay, so hopefully that makes sense and you can get past that. So this is the trained model. And once we have the trained model, I should point out here, we're saving the model. So save the model, we're saving it. This is what it looks like. It's you know, pretty big model, has a lot of weights that have been learned and parameters that have been learned. So what is that? 268 megabytes. Now let's load up the model. And this is some boilerplate here to convert the 0 index into a label. If I wanted to, I could actually change this to be star rating 1. I could change it to a string. I could change it to whatever. The flexibility of this transformers library lets me actually reuse this now pre-trained. So we have now created what could be considered a pre-trained model on the Amazon customer reviews data set. And we could like public, or yes, make this model public. We could post it onto the Hugging Face, their like model zoo that they have, their sort of marketplace. We could sell this model, yes, if we wanted to, or not. But now this model becomes the model that we saved now can be somebody else's pre-trained model. So let's simulate that. So let's pretend that we're somebody else. We've been handed this model. Maybe we're a different team within the organization. We're on like the application side. We like want to make predictions. The data scientists hand over this model, and I can map it to my domain. So maybe 1, 2, 3, 4, 5 doesn't make sense for me. You know, maybe I want to call it, you know, bad, you know, okay, and good, or something like that. So that's the cool thing. That's why this looks sort of overly complicated, because it's actually giving us flexibility. In Spark, some of you that might be familiar with Spark ML, this would be index to string and string to index in Spark ML. Okay, so when we're making predictions, we have to convert the raw text again into the tokens. And so we have to use the exact same tokenizer from up above. And this text classification pipeline, don't get too bogged down in the term pipeline. All this means is it's something that's relatively new out of transformers. It's a way to make a prediction. And this will actually do that tokenizing and some of that like ugly work that we did during training. I could actually do that here. Okay, so I'm giving it that loaded model from up above that's been given these new labels. And I'm giving it the tokenizer. I'm telling it it's from TensorFlow. It could probably detect that, but for some reason we have to pass it in. And then there's a way to specify if it's a CPU or GPU, just a slight little optimization. The notebook does not use GPUs. We can spin up a cluster of GPUs, and we could have spun up this notebook as a GPU, but we're trying to keep costs down. We want to be conscious of that. There's really no reason in an ad hoc notebook to use a GPU because we're not going to utilize it all the time. We would want our cluster to use GPUs because we're going to pound it with data. But right now, I would be using a GPU, and if I'm not running anything, I'm not using the GPU, but I'd still be paying for it. So keep the GPUs to the cluster, keep your notebooks to the CPU. And here's just some sample predictions. Again, this is a skewed data set, so but this is showing you the plumbing and the techniques to get the data into this format. Okay, and here we're just taking it one step further, where we load in a pandas data set, one of the files that we've been using. And these are the actual these are the actual labels. And now we're going to run our model, and lo and behold, we see all 5s, which we expected. So not going to dwell on that too much. And so now we're going to compare the predicted to the true to the actuals. And for this, we're just going to use familiar scikit-learn. So scikit-learn can generate classification reports, tell us, this is a pretty bad model. It's actually worse than if you just randomly guessed. Yeah, so, and here, let's generate confusion matrix. Of course, everything's being predicted as 5, so not very useful here. The confusion matrix is skewed. We can very easily see that things are imbalanced. Okay, we've gone through ad hoc mode. We're going to launch the training job and then take a break. I think we'll do probably 20 minutes maybe for lunch. I'll have to talk to Ansha about that. Okay, I'm going to just run this. I've already explained all the fundamentals. All that's happening here is, so this is the same as before. We're using TensorFlow with BERT, specifically distill BERT. There's one new concept that I'm going to introduce here, which is the experiments API. So experiments is part of SageMaker. This is how you track all the things that you're doing for your model, including what we just did with feature engineering in the previous section, training, which is what we're doing now, and then optimize, which is what Ansha's going to do, and then deploy is something Ansha's also going to do. So experiments, we actually could have introduced in the previous section. Actually, in reality, or now that I think about it, we could have actually introduced experiments during data quality checks. That's probably maybe one of the better places to put it, because we want data quality checks to be part of this whole experiment. Because this experiment is will be training multiple models using different hyperparameters. We want to see what were the characteristics of our data set, and that comes from DQ. So, but for right now, we are introducing it here. We stored all of the relevant values like maximum sequence length, the train test split, train validation test split. All that's been stored in the session in the Jupyter notebook, and we can pull it in now and then track it all. So I'm not going to dwell too much on this because we have to get moving, but just know experiments are made up of trials. Trials are made up of one-to-many components. Tracker is something you'll see in the API, so it's here. It's a little bit of a wonky API. Hoping to see some changes there, but talking to the experiments team about this. And one thing to note is that we're actually reusing the same features across all 3 training runs. So the first training run, we actually just used manual hyperparameters. So I chose the epsilon, I chose the learning rate. I chose whether or not to freeze or not freeze. Ansha is going to do a hyperparameter run giving ranges and say, here's a range I want you, SageMaker, to explore. Maybe 1e or 3e -5 was not the best for learning rate. That was my human intuition. Maybe it's not the best for this data set. So let's let SageMaker decide. Ansha will then do one more hyperparameter run that builds upon what was learned during the first hyperparameter run. And this, by the way, was all done during AutoML, with autopilot from O2. We're just now diving deeper and showing what actually was happening there. So we made a conscious decision to show you the easy things up front. For those of you that might suffice. Now and then the tail end is getting deeper and deeper, and so we know this is lots of information here, but just hang with us. And once we actually decide which model is best, we can deploy that model. So just note that the same feature preparation, feature engineering is used, so we don't have to run that multiple times. Once that data, those TF records have been built, we then feed those into the training runs with different hyperparameters. we choose the most accurate model or whichever metric that we're trying to optimize, and that's what's being deployed. Okay, here's some boilerplate code to create the experiment, give it a name. I'm gonna skip through some of this. This is the preparation trial component here. So we're setting up, this is the goofy part of the API. To create a trial component, yeah, you actually have to create it with a tracker. Not the most intuitive, but here we're associating a trial with a trial component for the preparation. And why we're doing this is we're actually backing up and capturing all the data that we did during feature engineering. All of the metadata, where the data started from, where it ended up, what was the max sequence length used, what was the train validation test split. Here we go, whether or not we balanced. All of this gets saved to the experiment. Okay, and setting up where, so this is still the preparation. This is just doing the sort of lineage tracking of when we actually do deploy this model, we can go back and look at all the steps that were involved in this. All right, let's get ready to train. So again, we have TF records that we're gonna feed into our model for model training. We're gonna shard that data. So similar to how we sharded during feature engineering, we have two files, two TF records, and we have two instances that we will use here in a bit. We're using sharded by S3. Key is just the name that you pass to turn on sharding. And here's our actual training code. I'm not gonna spend too much time here because we already did it during ad hoc. This should look very familiar. Here's that pipe mode. This actually will get used. Pipe mode creates on each SageMaker node, or yes, instance that's in our SageMaker cluster. Every, each instance opens up a channel back to S3 that's prefetching and doing all kinds of optimizations to get the data to that instance, on demand and when needed only, right? So as data is needed, it will pull it in. This lets the training job start up much quicker. So because if you don't use pipe mode, all of the data has to get copied into the so those instances. So with pipe mode, it's just streaming that data as needed. These instances start up and training starts immediately. So pipe mode does support TF record, knows about it natively, which is nice. You know, prefetching, so SageMaker and TensorFlow work together here to pull that data in. Shuffling the data, all this should look familiar. One other concept to introduce is checkpointing. So checkpointing is very important when you're doing distributed training. If you lose a node for some reason, maybe you have some kind of network glitch. This doesn't happen often in the cloud, but if, for example, say that you're using spot instances. So spot instances are are priced lower during off-peak times. You can actually get your cluster instances for 90% savings, 70% savings. The risk there is that you might lose that instance. I think you're given 10 minutes or something like that before you actually lose the instance. Checkpointing safeguards you from that happening. So let's take the example. We've got 10 nodes. We lose 2 of them, or 10 spot instances. We lose 2, and they get replaced with higher priced instances. That's in the cloud. That's the more common scenario. And at like Netflix, for example, so we had EC2 instances up for years that just never went down. So just keep that in mind, that with checkpointing has to be supported by the underlying framework. So TensorFlow has to support it, which it does. PyTorch supports it. MXNet supports it. All of these sort of large scale, like big data, Spark supports like checkpointing. So we are going to turn on checkpointing. We do some of the accounting for that so the cluster can recover. And at the end of the day, we'll see, the other thing too for a cluster is we have to specify a distributed strategy. This is specific to whatever framework that you're using. Let's see, mixed precision is something for GPUs that you want to pay attention to. You can combine 32-bit and 16-bit processing, give you some better performance on specific hardware. And then all of this should actually look familiar. We're just wrapping in some retries to make it production hardened. Oh, and because keep in mind, this is actually pulling it down from, so this is pulling it down from Hugging Face. So Hugging Face uses Amazon. They have an S3 bucket. Every time I call from pre-trained, this is actually calling out to the Hugging Face service, which pulls from S3 and then returns it. If for some reason, like Hugging Face is down, or there's some kind of issue with your network where you can't get outbound, this could affect your training run. This is a fairly serious problem. This is something Netflix dealt with quite a bit. We always burned everything into our Docker images so that we had no dependencies on the outside world. If we did get into some trouble, or if some region went down, or an availability zone went down, or something catastrophic, we could still auto scale up and add more nodes or shift nodes. And we broke those external dependencies, which is good. Like, you don't want external. So something to keep in mind, we are not doing that here. It's called network isolation mode. It is supported by SageMaker. It's there for security purposes, to make sure no one can get into your stuff either. But like, just know that you do need to be able to specify like some sort of S3 bucket here, or local disk. This is also, so this is the other reason why people bring their own Docker containers. Sometimes that's the best way to isolate from the outside world, is to burn everything in, run as a bring your own container. So something to keep in mind. Don't want to get too bogged down in that. And so here we go, setting up the base model, the base layer, setting up checkpointing. Yeah, so as you can see, this code gets quite a bit more complicated when we go to the cluster. And this is, not really a SageMaker issue. This is how these frameworks are built, right? I mean, TensorFlow is very popular. Distributed TensorFlow used very, very heavily. And this is just the state of things here. And so, short of creating layers on top of these frameworks and trying to abstract all this out, we like to keep things as pure, and just extend where we can make performance gains, talking to S3 or other Amazon specific things. So this is all purely open source TensorFlow with just a couple optimizations for the Amazon infrastructure. So people have been trying to crack this space for many years. The company before I joined Amazon that I built was trying to tackle this as well. And so we ended up building layers on top of these frameworks, and it becomes a technical debt nightmare. And no one wants to just use this other layer. They want to use raw TensorFlow or raw Keras or raw PyTorch. So this is just the current state of things when you do go from single node. And so one thing Spark is actually pretty good at is the local mode or single node mode is the same as it is on a cluster. And that was something that the Spark folks got right from the very beginning. As wonky as the original Spark API was, all I had to do was change the number of instances, and suddenly I had a cluster, and I would operate in parallel. And TensorFlow tries to be that way. It's not quite there. There's distribution strategies and hardware specific things that you have to worry about. Okay, here's that familiar fit that we saw before, where we're doing training data set, validation data set. Here we're doing the evaluation here separate. And I'm actually passing in a flag to run sample predictions. I like to run sample predictions and just get essentially a quick smoke test to make sure that my predictions are what I'm expecting or similar, and that nothing catastrophic has gone wrong. The other cool thing I do here is I actually generate all of those same metrics that we did, and I generate the confusion matrix, the same metrics that we generated in the notebook. I actually put these right in and save them inside of the same bundle. So every training run, I could crack open and go to that S3 bucket and go look at the confusion matrix with my own eyes and not have to run another notebook. since I'm right here and I have all the data and I've uploaded a small little sample data set with this model, my test data set, I can run all those metrics right here, use the power of the cluster, and then just go analyze it. Okay, and so that was defining the script, so script mode. Now we're actually setting up all the hyperparameters. Here we see a lot more hyperparameters for the production case. Freezing the BERT layer, specifying we want C5-9XL, a lot of CPUs here. We could certainly use GPUs. GPUs would definitely make things faster. Once again, our goal is to keep the cost below $25. This is a lot of compute still, and this is 8, 9, 10 hours, and it's still $25, which is really good. And it's because of some of these changes that we made where we dropped the instance profile. The performance is still pretty good though with these C5-9s. The other thing to point out is that you can define your own metrics or set up. So the goal here is to be able to chart and compare performance between training runs. And one of the ways that you could do that is you can scrape logs or add your own print statements from Python, add them into your code, and convert log lines. So this is a sample log line. This actually comes out of Keras and TensorFlow. And this is useful data. And I actually want to convert this log line into something that I could chart. And so this is a really cool feature of SageMaker where I could scrape this log line using, kind of goofy regex. Here, I just copy and paste this from somebody else's work. And this now ends up in CloudWatch. And I could actually chart these all together. I could look at all the runs, look at the validation loss, validation accuracy is what I'm paying attention to here. All of these things end up in CloudWatch, which is really nice. And they, of course, also end up inside of SageMaker experiments, which is ideally where we want everything to come together. One other really cool feature of SageMaker is there's something called SageMaker Debugger. Quite a lot of work going on in this area. Hopefully see some stuff by the end of the year with being able to look inside of the training run. And, so TensorBoard gives you the ability to do this, and Debugger supports TensorBoard, of course. So one cool thing about Debugger is it works across frameworks. So it's not TensorFlow specific. TensorBoard, for the most part, is TensorFlow specific. We can actually set up rules and say, check if I'm overtraining, check if my loss is not decreasing, which we always want loss to be decreasing. Yeah, otherwise we plateaued. And we could set up rules. And if you are familiar with rules and rules engines, when a rule is triggered, you can fire off an event that notifies the data scientist at 2 in the morning that this particular training job has plateaued. You want to stop the pipeline. There's no reason to continue training if one of these rules is fired. So you could set up rules. You could set up things like SNS alerts. You can call Lambda functions. Okay, let's get right to it. So we're actually not using spot instances, but we're still going to pass in checkpointing. Actually, yeah. And the reason I'm not using spot instances, I typically always would. With a large scale workshop like this, I need everything to be on Rails and to run exactly like we expect it to. Spot instances, because of their nature, the spot market, the pricing can go up and down. These instances sometimes can be available, sometimes difficult to get, depending on how heavily they're being utilized, throughout the day, throughout the evening. So in reality, you should pretty much always use spot instances to save money. But for here, we've chosen to actually choose a deterministic path for the overall benefit of the workshop. Okay, here's our script that I was showing you earlier. That's why this is called script mode. Source, this is a directory. If you look back here, there's a source directory that has a requirements txt. So you can bring your own dependencies. Here's training instance count, instance type. So I believe we're using, was it 1 or 2 of the C5-9s. And here's all of our hyperparameters. Now, hyperparameter is a special field here that contains this dictionary. And this is something Ansha is going to play with later on yes, after lunch. And we'll actually tune some of these. Input mode, this is pipe mode. Non-pipe mode, metrics definitions is our regex. Debugger rules, and let's get going. Here's, when we call fit, this is what's actually gonna trigger the training run. We have our train validation test split. These are S3 locations. This is for our TF records. We pass in the experiments config, which comes from here. And this particular part of our experiment is called train. The part we were registering up above was called prepare. That was previous section. The next section, it's called optimize. The section after that is called deploy. So we could do a deep link to our training run here. Let's take a look, see what we got. 390 seconds. We could look at our metrics. So there's our instance type. Here's our metrics here. So that's the regex that was used. Here's all of our hyperparameters. Let's get right. We did not use network isolation mode. I would highly recommend this, like I was saying earlier, but you have to make sure that you have pulled in all of your dependencies. Inter-container traffic encryption, I would always recommend that as well too. It'll affect performance a tiny bit, but you get encryption between all of the nodes. Yes, even though this is all inside of your VPC, inside of your like virtual private cloud, there's no one else that can come in and see this. It's still nice to know that traffic between nodes inside of your private cloud, your like VPC still has the encryption. So something you should definitely turn on. And here we could see now, we only ran one epoch just to keep it down. We should probably increase this to 2 or 3 to get some more data. But here we see CPU utilization right alongside memory system. These are system metrics. And then we see validation loss, validation accuracy, training accuracy, and training loss here. So yeah, obviously we have room for improvement. And okay, so that's that. We can look at our training logs. I'm gonna skip that, training output, any checkpoint data. Here's so far what we've done for our lineage. That's commonly what this is called. We've done a prepare that we registered. This is for the experiment. And how did we get here? So maximum sequence length, as I mentioned earlier, has to be the same between prepare and train. Now we have this different splits. And the training run ended up with pretty poor performance here, actually really bad performance, lower than I've seen in a long while. Also has the hyperparameters that were used. There's a bunch of stuff missing here that's not being shown in this data frame view, but all of those metrics that we logged up above are there. And finally, we track everything here just to stuff it away. These like Jupyter, this Jupyter server, this Jupyter notebook instance that we're using shares data between notebooks. That's why we keep using %store everywhere. All right, and I think I'm gonna skip debugger. You could run it, it just shows things that TensorBoard would show, accuracy, things like that. And this is simulating, this is copying the trained model that was trained by SageMaker and doing the exact same thing that we did as though we were a user of this newly pre-trained model that's specific to our domain. So I'm gonna skip that, probably just do a run all on both of these, check them out over lunch. And I think we're done there, Ancha.
Yes, perfect. That was a lot of good insights there. I think everyone is super ready for whatever you're up to now, breakfast, lunch, dinner, midnight snack. I tried to answer as many questions as I could in the Slack channel, so I think we're doing good there. Maybe you can scan through and maybe add a couple of comments if you like. Why don't we take, how much time do we want to do? Like a 30-minute break?
15-minute break? Somewhere between 15 and 30? Let's say 20-minute break. I think we got to keep going.
Yeah, so we have a lot of content to cover and it's getting late and early depending on the time zones. Let's do a good 20 minutes.
All right, so what time is that here time? Okay. Yeah, let's return in 20 minutes at 1:36 p.m. PT. It's bad when I have to think if it's AM or PM. Okay, see you in 20 minutes.
All right. I hope everyone had time to grab some snack and is coming back from the break right now. So let me quickly set up my screen share here. And let me arrange my windows here. All right, so we've been through a lot of content so far. So thanks for everyone. Thanks everyone for sticking around. So we've been through a lot of the machine learning workflow already. So we've seen the data ingest, explore, preparation, and Chris also showed you how to train models with Amazon SageMaker. So I'm going to cover next the parts of optimizing the models and deploying them into production. And then we'll also see how to create an automated pipeline to perform those tasks. And before I jump into the optimize, I just want to quickly show you something in the training section. So if you're still in the 7 train, we have one more notebook in here, which Chris didn't touch on yet, the 05, and we started incorporating also some PyTorch examples. So if we have some PyTorch fans here in the workshop today, there's actually a notebook here in the workshop which introduces some PyTorch. And I just want to quickly show you this. So what we're doing here, and yeah, for the record, you can ignore those pip install version conflicts. Some of you got confused here. It's really just, we're working with so many different versions and SDKs that at least in one notebook, there's always some version conflict. So they don't keep you from running the notebook, just ignore those for now. So what we're showing here is actually how we can use the TensorFlow trained BERT model and convert that into a PyTorch model. So yeah, Chris and I were both big fans of Hugging Faces, as you've probably noticed. And if you run this notebook here, what we're doing is taking the BERT TensorFlow model and then using the Hugging Face capabilities to convert that model into PyTorch. And it's pretty simple, actually. So if you run this notebook, just watch out. There's one step which restarts the notebook kernel to pick up the newly installed libraries. So a run cell all stops at this kernel restart. So you have to restart after that cell. So what we're doing here is we're downloading our TensorFlow trained model, which we trained before. And we can have a look, so you can actually untar and see what's happening here. So you can see it's the model tar, it's some TensorFlow information, transformers information, and config.json files, etc. So what we're doing here to actually transform it, we're using the PyTorch model from Hugging Face. So if you, not sure if you noticed, but if you're using the Hugging Faces transformers, they have the name and some of them have TF in front. So until now, we've used the TF version, the TensorFlow version. And what we're doing in this step, it's pretty sleek, actually. We're using the PyTorch version without the TF. And here we're calling from pre-trained, and we're loading our model. And down here, we're saying from TF equals true. So we're loading from TensorFlow into a PyTorch version of this model. So that's actually the step to convert them, and it's pretty sleek. So here you can double check, so you can do a type on this loaded PyTorch model, and we can see now that we have the fully functional PyTorch pre-trained BERT model here. All right, we can also double check that and run some predictions. So we can also pull in the tokenizer here and set the inference for CPU. And then we're calling here a text classification pipeline, pointing it to that loaded PyTorch model, passing the tokenizer. And here we're saying it's framework PyTorch. And then we can actually run some sample reviews here. And we can see it's predicting on those sample texts. So super easy to convert. We can also then save this model with either the save pre-trained. So we can just call on the loaded PyTorch save pre-trained, dump that out so we get the PyTorch model bin here. I'm just doing a quick load and predict to make sure it's working throughout all of those conversions, and uploading that to F3. So in the deploy section later, we do have also another notebook which introduces TorchServe. And not sure if you heard of that. So TorchServe is a new open source project that AWS developed together with Facebook to host PyTorch models. So TorchServe, we do have a sample notebook in here in the workshop as well. And for that purpose, we're uploading these PyTorch models here into S3. And we're also saving it in the vanilla PyTorch, so torch save, which is the PyTorch model PT file, and just uploading that to S3 as well. Future use. So yeah, we just started to incorporate more and more PyTorch here as well. So yeah, so this was the last notebook actually in the train. I just wanted to quickly highlight that. And while we're here, let's actually revisit the notebooks I have still pending here, because I always like to close the loops. So for example, I still have here the training notebook for Comprehend. And in the meantime, obviously this finished. So if you remember, Comprehend is the fully managed NLP service from AWS, which you can leverage by really just integrating the API. And what we did in this notebook right in the beginning of the workshop here is we started a custom classifier. So we took the built-in Comprehend model and we fine-tuned it to our reviews, and then also deployed this as an endpoint. So once this notebook completes, we can run some sample queries here, and we do this programmatically in the notebook, and we can see predictions coming back. And also even more impressive is if you go to Amazon Comprehend in the AWS console. Remember, we had the real-time analysis here, and we just used the built-in API basically in the built-in model to give us here some sample, for example, entity recognition, key phrases, etc. If you click here in the custom classification in the left menu, this is where we started submitting our custom classifier. So if I click here, this one in the meantime is fully trained. And we also deployed a prediction endpoint. So it actually serves predictions. And you can see this here if you scroll down. And this one also says ready. So we can test this now. So I go back to the real-time analysis here just to do it from the UI. And I'm choosing here for the input custom. And I'm selecting my custom Comprehend inference endpoint. And now I'm passing in a sample review text. Let's say, I love this product. And hit analyze. And you can see, in contrast to the previous prediction that Comprehend gave us, like entity recognition, language, it is now adopted to and fine-tuned to those reviews and also the results. So it now does a multi-class classification here. So it says it's 88% confident this is a 5-star rating. So actually, Comprehend actually delivers really, really good results. If I write, let me see up here, this is okay. Let's see. Yeah, look at this. It says, yeah, this is a 3-star rating. So Comprehend actually performs pretty well. All right, so this was a way to show you how you can also use the fully managed services and just fine tune them really to your need. And we had somebody asking about entity recognition earlier in the chat. So here's also the capability to actually fine tune a custom entity recognition model to your data set and needs. So yeah, this was just a quick catch up on those pending notebooks we had. Now I can close off my Comprehend. And in the meantime, also my autopilot finished. And I think some of you had some errors there. So if you rerun that notebook, I think a couple of us hit the API at the same second. So there might have been some back off there to just level out the load. But yeah, so if you rerun or you had it completed, what you will see is if you go to SageMaker, that you have a model endpoint deployed. And if I click here in endpoints, let's see. Yep, so I do have here this AutoML endpoint deployed, which is the result of our autopilot model pipeline. And you can also see the training jobs, which now gets a little bit busier with a lot of things we've done here. But you see the AutoML jobs showing up here. And yeah, you can also see the tuning job here in the hyperparameter section. And we will also use the autopilot model in just a sec here. All right, so this was really just to closing the loop to those notebooks that I kept pending here in the background. And let's move on now. So let's jump into the optimize 0.8 optimize section. And let's open the 0.1 notebook hyperparameter optimization here. And I've pre-run this notebook here just to get some results. So what we've done so far is really manually training our model. And part of the whole development process for models is also finding the right hyperparameters, right? So hyperparameters could be the number of epochs, could be the number of layers, number of hidden units, could be in the NLP space, for example, the max sequence length. So a couple of different settings that you need to tune really to kind of optimize the model. And there's a couple of strategies how you can do this. I mean, obviously we can try to manually find the right settings, and over time we will build intuition to come up with a good, experience to decide which ones we should maybe choose. But I guess none of us really has all of the experience to know every single use case and every single model. So why not leverage a service that is finding the optimal hyperparameters for us? And SageMaker also has this capability built in with hyperparameter tuning. And the way it works is we're basically defining an objective metric. So we're saying we want to maximize validation accuracy, for example, and we're deciding on a tuning strategy. And the tuning strategy, there's a couple of ways to do this. So obviously we want to move ahead from the manual step. And the next step would be if you have just a few number of hyperparameters, what you could do is just map them out in a grid, which is called the grid search. And then we would basically test every possible combination. With a few parameters, this might be feasible, right? But imagine we have a lot of parameters and a lot of ranges. So testing every single combination, it's taking too much time, right? So a way to address this is to random search. And with random search, we really just, as the name suggests, we pick up random values and test them. And funnily enough, this actually works pretty decent. So I would think, yeah, random search, it's just randomly picking something, but it actually performs pretty well. Then if you really want to kind of have a more scientific approach to finding the right set, a very popular strategy is Bayesian. And with Bayesian optimization, we're actually treating the problem of optimizing, for example, the validation accuracy as a regression problem. So we're applying machine learning to a machine learning problem, which I think makes a lot of sense. And the capabilities here from SageMaker hyperparameter tuning, they support random and Bayesian search. So we would pick one strategy, define the job, point it to the training script, and hyperparameter tuning would then run a couple of training jobs and try to optimize. So let's see how we do this. So let's run this notebook. I pre-executed, but feel free here to do a cell run all to get this going. And I'll walk you through what's happening here. So as a first step, we're also including here the SageMaker experience. So we want to keep track in this lineage what we're doing. And the different steps we're performing. So again, we're pulling in the experiments, we're setting up the environment here. We're also, and this is a lot of store retrieve, we're retrieving all of the locations of the training, validation, and test data set. So a lot of imports here. And we're also defining our F3 input channels. So you've seen this before in the training steps. So we're pointing here to those locations. And we're also reusing the same training script. So Chris walked you through this TensorFlow BERT reviews Python script. And this is basically the same script we're reusing here as well. All right, so how can we get started with a hyperparameter optimization? So first of all, you probably have a mix of static parameters, which you just want to keep, and another set of parameters which you want to search for the best setting. So let's first define the static hyperparameters. And here we just say we stay to this maximum sequence length because we already prepared everything around that number. So let's take this as a static hyperparameter. And let's also fix the number of epochs here to 1 because we want to see the results throughout the workshop, and a bunch of other parameters here, epsilon value, training batch sizes, test steps, which instance types, for example. So let's just keep those all fixed. And we also want to track, as I said, the optimization in the experiment. So we're retrieving our experiment name and the trial name. And we're adding another trial component for this optimization. So let's call this optimize1 and add it to our trial component. All right. So now the fun starts. So let's now define the dynamic hyperparameter ranges to explore. And we do this by pulling in the SageMaker tuner object. So this is basically taking care of this tuning job. And we now define the ranges and the values we want to find the perfect value or a good performing value at least. And for our example, we just take the learning rate as an example. And as you can see here, there's different types of parameters which you can choose. So learning rate is a continuous parameter. So we want to explore the range, and this is the minimum and the maximum of the range, between 0.00001 and 5. And scaling in between in a linear scale. We could also define integer parameters like number of epochs. We could say, well, test between maybe 10 and 100. We could have categorical parameters, which could be, for example, an optimizer, so Atom, SGD, anything that is more of a category. So those are the possibilities you have to define here your hyperparameter ranges to optimize. Then we're also still keeping track of the metrics from our CloudWatch logs. So we're keeping track of the training loss, the accuracy, and the validation loss and accuracy. All right, so what's next? Next, we define our TensorFlow estimator. And this is pretty much the same setup as we've done before with training. So we're giving it an entry point, which is the training script, pointing to a source directory for any requirements txt, passing our role with the permissions, passing in here the training instance count and type, Python version, framework version, etc. And in this hyperparameter range, we're passing in the static ones. So the ones we don't want to dynamically optimize, we just pass in the estimator setup. And the input mode and metrics definition we want to keep track of. All right, so to also add this estimator now to this hyperparameter tuning job, we create an object here, in hyperparameter tuning object. And here we're passing this estimator, which we just defined. And we're also defining this objective metric. In our case, let's optimize the validation accuracy. And this is a problem to maximize. If you have loss, obviously you want to put in a minimize, but accuracy, obviously, let's shoot for the best. All right, then we're passing in here our range of dynamic hyperparameters, which in our case here is just the learning rate, the metrics definition, and then you would define how many jobs you want to run in total and how many in parallel. And this really depends on the strategy. So if you're doing a random search, every tuning job doesn't really depend on the previous one, right? So you could do like 10 jobs in parallel and a total of 10. So just run them all in parallel. If you work with Bayesian, because we're treating the results from one training run to optimize hyperparameters for the next one, it makes sense that we have a couple of steps in sequence. So for this use case, let's set up 2 maximum jobs and just do one in parallel. So do one job, check the results, optimize the parameters for the next one, and run one more. Again, in your production use case, you would definitely do more than just one, but we just want to keep the time here to a limit. So we just do one and one after that. All right, so and then we can just call fit on this tuner object. And we're passing in here the channels, so the input training data, validation, and test data set. And this is it. So this starts the hyperparameter tuning job. And the next cell here will again loop. So the training job probably takes 10 minutes to run. So we just keep looping and check for the progress here. And you can also see if you're jumping to the SageMaker console here, you will see that there's one training job popping up here. And you can see mine ran for 22 minutes. So I just started it just before to see. So yours will show up and be in progress, but you can basically click in and see all of the settings again. And just to give you the sneak peek here, so once this is finished, you will then have also the information about the best training job. And you can see, in this case, we could increase the validation accuracy to 57%. So still not the best, but at least. And you can see the hyperparameters. So in this case, we really just looked for the learning rate. So here's the learning rate that led to this best performing training run. So yeah, you could have those hyperparameter jobs running and helping you with the task to find the optimal model settings. All right, keep the notebook running. That will run for 20 minutes. There's a second notebook in here, which only runs once the first job is completed. So I'll just show you quickly. You don't necessarily have to run it because your hyperparameter job will take a little bit of time. But just to note, there's also a second way to pick up from previous tuning jobs. So let's assume you have those hyperparameter jobs running, and at one point they stop and you evaluate, and you want to run a second batch of tuning jobs. What you could do is do a warm start. And a warm start means that I'm picking up from the previous job. So I'm taking the learnings from the first tuning job and starting from there. And this could help in a couple of different ways, right? So it helps to increase the accuracy, and you don't have to learn everything from scratch. And depending on how many things you want to change in between. So there's 2 different ways you could try to improve the second run of tuning jobs. So you could either just, change the ranges. So you saw that the learning rate was performing well in this specific range. So maybe in the second run, you want to tune that range and change it. So this is an example for this identical data and algorithm mode that this warm start can run in. So in this one, you can basically just change a couple of parameters, like change the ranges or flip one from the static into the dynamic. But the rest is pretty much the same as the parent job. Then there's another mode, and it's kind of called weird. It's called transfer learning. But what it means is really that you have more freedom to change the settings in between those tuning jobs. So in this case, if you're choosing transfer learning, you could also change the input training data. So let's assume between those tuning jobs, you have collected more training data, which you think might help to increase the accuracy of the model again, or find the better hyperparameters. And you want to actually retune with different data. So that would be the transfer learning then. All right, so this notebook, as I said, only works if the previous one has finished. So maybe let's just have a quick look how you would start this warm start job. So the setup is pretty much the same in the beginning. We're pulling in all of the parameters. We're setting the static hyperparameters here. We're heading it to our experiment. So this one we're calling optimize 2. And here in the dynamic range, we're still using the learning rate. So we're not going to do the transfer learning. We're going to stick to the same data and algorithm. But we want to change this range. So before I had like the 0.0001. So now let's change this range and do a 1.5 and a 7.5 in here. So let's fine tune this range. And this is basically our second job now. We set up the estimator object exactly the same as before. And what we're doing different now is we're configuring this warm start config. So what we need to do is we need to have a completed job before. Gonna say this once more. And we're retrieving this tuning job name, which is the parent now. And we're adding a warm start configuration to this tuner object. And in the warm start config, we're saying which type. So in this case, I want to do an identical data and algorithm type. And I'm passing the parent tuning job name. And when we then create this hyperparameter tuner object in here, we're again passing estimator. We want to maximize the accuracy. We're passing the new learning rate range in the hyperparameter section. Metrics we want to keep track of, still doing Bayesian, etc. And we're adding one parameter, which is optional, but here we're going to use it, and passing the warm start configuration. And this calling fit on the tuner then basically receives the previous learnings from the parent job and then starts another batch of tuning runs to further improve with the learnings and the weights, everything learned from the previous job. All right, so as I said, this one will only work if the first one has completed. So if you want to run it, feel free to run the first one, and once that is completed, start the second. And let's keep those in the background. We don't need them to be completed for the model deployments. So yeah, just keep them running there, and then we can revisit them in a later point. All right, so this was quickly on how to use hyperparameter optimization in SageMaker as well. All right, let's move on. Let's go to 09 deploy. And I'm gonna open here the overview here and give a quick introduction. So we've been through the whole process of building our model training. It's now tuning. And the next step is we wanna deploy that model into production, right? We want to have actually the model serving predictions. And generally speaking, there's two ways to do this. You could deploy the model as a real-time endpoint. And this basically makes sense if you have applications that are hitting an API and you need to serve inferences 24/7. So you want to have an instance, an API serving your predictions. The second option you have is to do a batch transformation, a batch prediction. So in this case, you might want to just have an input data set and you need to run inference on the data set, run predictions, and it's more like a one-off, right? You're passing in input data files, you want to do a batch prediction, want to capture the output, but it doesn't have to be a 24/7 deployed instance serving predictions. And this is also something you can do built in with SageMaker. So we have a functionality called the batch transform, which offers you exactly this setup. All right, so let's see how we do this. So let's open the first notebook here in deploy. And before we deploy a real-time endpoint, I actually want to show you a really nice preview feature that we have calling the autopilot model that is already deployed. So the autopilot model is one example of a real-time endpoint we have running in our account right now. And again, this only works if you've executed the autopilot notebook and if that's successfully finished. You can double check if you go to the console, the AWS console, go to SageMaker and scroll down to endpoints on the left. You should see one endpoint that is called automl-dm-ep and then a timestamp and shows in service. If that doesn't show up, you don't have that endpoint, so the notebook would not run. So in that case, don't worry, just keep watching what I'm doing. If you have that endpoint running, feel free to execute the notebook. So, and I'll actually do it. So I do a cell run all. So what I want to quickly show you is actually a pretty cool feature here, which is currently in preview. And what we're doing here is we're going to use Athena. If you remember, Athena is the interactive SQL query service where we're querying data in S3. And Athena comes with support to invoke a SageMaker model from within the SQL query. Really cool. So how can we test this? And because it's preview, it's only running in a couple of regions, but as we're in US West 2, this should work. So we're again pulling in PyAthena, as we've seen in the beginning of the workshop. And what I'm doing here is basically I'm creating a new table. So let's simulate reviews coming in, and I want to have a SQL query on those reviews, serving them from a table and running predictions. So what I'm doing here is I'm creating a table from my data set. So I do a create table, call it product reviews, and I'm just giving the review ID and the review body text. So if I quickly show this here, so the table now has a review ID and a review body, so the review text. And I want to run now a SQL command calling the autopilot model that is deployed and giving me inferences for each of those rows. So giving me the star rating. All right, so the first thing I have to do is retrieve the name of this endpoint. So again, this model endpoint has to run in your account, otherwise this will not work. So if the endpoint is running, you will receive the name here. And also I have to join a work group that is enabled for the preview. So this is what we're doing here. Just joining a specific preview functionality work group. And then we can start writing our SQL query. And I start by writing a function. So using function, and I call the function predict star rating. And as an input, we pass in review text characters. And the function also returns a character, which is our class. And then Athena gives us this new feature. So SageMaker invoke endpoint with. And here we're passing the name of our model endpoint. And what I can do now is I can use this function as part of my SQL query. So I'm doing a select review ID, review body. So this is coming from my product reviews table. And I'm calling this function now. So I'm calling this predict star rating, which I just defined here 3 lines above. I'm doing some in-query, inline cleaning of the data. So I'm getting rid of all the commas. So I'm removing the commas from the review body. And I'm running this predict star rating on this cleaned review body text. And I'm saving this as a new column, predicted star rating, in my table. And I'm reading here from this product reviews. So this is it. So I execute the statement, and I'm pulling in the cursor results in the pandas data frame. And here we go. So I have the review ID, I have the review text, and we now called from a SQL query through Athena a deployed endpoint from the autopilot model to give us star ratings on this review text. And this is stored again in my table. So pretty neat. And yeah, I think the matching is pretty okay. So I found this product easier. It's a 3-star rating. This is the best text software. It's 5-star rating. So yeah, good job. So this was kind of a reuse of our autopilot model, and also showing you some nice previews from Athena where you can run this in a SQL query. As a last step here, we're deleting this endpoint to make resources free for the next notebooks. So let's close this one. And you can also open up the 02 notebook now, perform A/B testing. And what we're gonna do in here is actually combine a couple of concepts to make it a little bit more interesting. I know we're coming a couple of hours here in the workshop, so to keep you curious, we're not only showing how to deploy the model as a real-time endpoint, we're also showing you in this notebook how you can do A/B testing. So we're gonna roll out a model A and a model B, and we're gonna shift traffic in between the models. So what we're gonna do here, let me run all, and then I'll walk you through. All right, so again, we're pulling in a couple of pip installs here, setting up the environment. We're actually also updating the SageMaker SDK version. So there's another kernel restart, so just look out for that. After that kernel restart, you have to click in the cell below and do another cell run all below. So we're picking up the new pip installs, making sure we pick up the new versions here from the SageMaker SDK and experiments. And we're setting up the environment here. We are retrieving our autopilot name in case we haven't executed a notebook before. Just make sure this is cleaned up. And then we're retrieving our training job name. So the idea here is to leverage our training job, and from this training job, create the model to deploy. And with the model, I mean the model object, right? So we have the trained tar file, but we need to create a model registered in SageMaker to deploy. So how can we do this now? So let's see. So first of all, the model tar file, that one we have. So after training, the model artifacts are stored in S3. So we can pull this down. So here we just download that model, and we can again have a look. So we can have a look in the tar, and we can see the transform is fine-tuned. Information is in here, this TensorFlow saved model PB metrics, even the confusion metrics is saved in here. So everything looks good. We can also use the TensorFlow saved model CLI to look into the signature, prediction signature of the model. So if you want to double check here how the inputs need to look like, we can see here inputs, input IDs, input mask, segment IDs. So this should look familiar from the training job that we run. All right, it's the right model. So let's now create the models. And for the A/B testing, we're gonna create two models, but based off the same trained artifact. So we're not actually using a totally different one, just really to illustrate how you would roll that out. And the way we do this is we're creating a model from this training job. So on the SageMaker session here, we call create model from job. We're giving it a name. So one we're calling model A and timestamp. And we're passing this training job name. We're passing a role. And we're also passing in here the container image, which you can hardly see here now with the scrolling. Let me see. Better. Here we're passing in this container image for inference to deploy this on. All right, so this is basically the model A definition. And we're doing the exact same thing for model B. So we're just calling again, we're just creating a model B name now and a timestamp and doing the same thing. So create model from job. It's gonna be the same training job. So the model will not behave much different. But again, we're calling this model B, passing the role and a Docker image for the inference. And we're using the built-in inference Docker image here for TensorFlow. All right, so as a next step, we need to define an endpoint configuration. So how it works in SageMaker is before you create those endpoints, you're creating an endpoint configuration, which has basically all the settings for this endpoint. And part of this endpoint configuration is a list of production variants. And a production variant is the combination of a model together with the resources needed to run it. So in this case, we're gonna have two variants. One is our variant A, which will host model A, and it will host it on a particular instance type. So here we're picking an M5L large, one instance, and we're calling it our variant A. And we can also specify the initial weight. So this is going to be the traffic weighting. And we're setting this model to 50 and the second one also to 50. So the production variant B takes the model B, has again a setting of instance and instance count to host the model, and we'll do another 50 of the weighting. So we have basically half of the traffic being routed to model A and half of the traffic being routed to model B. And this is basically our endpoint configuration. So here as the next step on SageMaker, we call create endpoint configuration. We pass a name and we pass the list of those variants. And here's a deep link, so you can follow that to the SageMaker UI. And this will show you this configuration. So this is not yet an endpoint. This is really just the settings for the endpoint. But here's basically all we just defined. So you can see we do have two production variants here, A and B, each one with those resources to host the model and the traffic weighting. All right, so this looks good. And as a next step, we then can call create endpoint on the SageMaker client, giving it an endpoint name, which we're just building here above again, and giving it the endpoint configuration. And this will then create the endpoint. We're also gonna make sure we're noting down the endpoint name here. So we're storing that again. And we're also adding this to our lineage. So again, we're retrieving our experiment here. We're retrieving the trial name, and we're adding this again as a component. So we're calling this the deploy and adding this to our experiments. We're adding a couple of parameters we want to log. So here we want to keep track of the endpoint name, etc. All right, so if we do a quick show on this lineage, so it's building up, as you can see, over the course of this workshop. So we added the prepare section in the beginning, we added the train. If you've run those hyperparameter optimization notebooks, you will see optimize 1. If you executed the second one, it will show up as optimize 2. And this one will now also add the deploy section. So we can keep track of what happened to our model over the time and can also store some of the parameters here that are important for us. All right, so let's see what's happening to the endpoint here. So there's another deep link. So you can click on that and that takes you to the UI again. And if you wait long enough, you will see that the endpoint is jumping to in service. So let me see timing here. Yeah, the second one here should be my endpoint. All right, so let me see. If yours is still in creation, so again, the endpoint also takes a couple of minutes to spin up. It has to start the instance types, has to load the model, etc. So this will take a couple of minutes. We do have another waiter here, another loop to check once the endpoint is in service. And once this happens, we're running some sample predictions just to see how it's performing. So we've seen this before in the ad hoc training, I think. We're creating a class here called the request handler. And this one is really helper code which transforms the raw text into tokens because our model expects BERT tokens as input, word embeddings. And this one is basically, again, calling the tokenizer, running the review input text against, and passing those tokens to our model. And then we have the response handler, which takes the output from the model and converts the response to our predicted classes. All right, so let's run this. So here we initiate the request handler, pass our token, max sequence length, and we pass our classes to the response handler. And then we want to have a prediction from our endpoint. And there's a couple of ways to do it. I mean, obviously, as it's deployed as a real-time endpoint, you can also grab this URL here. So you can use the API to include in your applications to call this invocations method here and receive the inference. What we're doing in here is we're calling it here from the notebook, and we can leverage a predictor object from SageMaker TensorFlow serving. We're passing the endpoint name, the SageMaker session. And this one has a feature here, a parameter where we can pass a serializer and deserializer, which is basically our input transformation and the output transformations. So we're passing the request handler and the response handler, saying it's JSON, pointing it to the model name, saved model, giving a model version. And now we have a predictor object. And on this one, we can actually just call the function predict. So let's test this with samples from our TSV data. So we're reading in samples from digital software. And let's limit those to actually 50. So we don't want to run 100,000. That may take a little bit. Let's just downsample it to 50 and run those 50 against this endpoint. So here we're calling the predict on this predictor and passing the review body in. So let's have a look here. And here we can see that the review text is coming in, and we do have predicted star rating class next to it. All right, so this worked. It's still predicting a lot of 5s, but yeah, it served the predictions. And we can also do ad hoc. So whenever we say ad hoc, it's just really, quick code. So here we're just constructing 2 sample review texts and passing them in. And yeah, we also get a review here. All right, so what we can do next is actually see the performance metrics from the endpoint. So here's another deep link, which takes us again to the deployed endpoint. And you can see mine is already updating. So we do have a couple of more cells that update the endpoint currently. And basically, once you've hit the model endpoint with prediction requests, you can see here the results showing up. So a little point here, CPU utilization, memory, disk. And we can also click here on the invocation metrics, which takes us to CloudWatch. And in CloudWatch, then we have more specific variables here showing invocations, model latency, invocations per instance, for example. So once we start creating more traffic, you can see here the points showing up. So we just ran a single one, so it's just really a little tiny point. So if you want to zoom into the range here, just create here a little bit of a range so it gets a little bit more centered. So here's where you can check for those metrics. So going back here to my notebook, we can also pull in those metrics if you don't want to jump into CloudWatch and we want to run it in the notebook. Here are just a couple of helper functions really to pull down the metrics from CloudWatch into our notebook. So get the invocation notebooks, pulling those down, and then we have another function here to plot them. So this one is doing the plotting here. And if we run those, so again, we're doing some matplotlib plotting here in the notebook with those metrics. We're calling the plot endpoint metrics here, passing the endpoint. And here we're doing the CPU utilization, and you can see variant A, variant B pretty much behave the same. And the metrics take a couple of minutes to show up. So if you do a run all on this, some of them might be empty. If you rerun those individual cells in a bit, they show up. All right, so just scroll down here. So what we want to do next is, let's assume the model B is performing well. And we want to shift the traffic from a 50-50 to 100% to variant B now. The way you do this is we just update the model endpoint configuration. So we're creating a new updated config and saying variant A, desired weight 0, and variant B, desired weight 100. And you can guess what's next. We're calling again the SageMaker, and there's a call to update the endpoint weights and capacities for a given endpoint, and we're passing this updated endpoint config. And this was the little spinning wheel you saw on my endpoint that said updating endpoint. So once your endpoint is deployed, it keeps serving predictions, and in the background, it will update the model endpoint to any new given endpoint configuration while it's still serving predictions. So let's actually see. Yeah, mine is still updating, as you can see here. So let's refresh. Yeah, it's still making the changes. So we do run a couple of changes here, but you can see here that, yeah, this one already updated the weight. So variant A has now 0 and variant B has now 100% of the traffic. So yeah, let's see. And let's run some more predictions to actually see the different behavior. So we're just running another round of predictions against the data set here. Looking good. And we're plotting the metrics again. So here you can see the initial metrics. So variant A and variant B were serving the traffic. And let me rerun this here in a little bit to see where it picked up. And as a next step, you want to then maybe remove the variant A to reduce your cost because it is deployed on a separate instance, right? So again, we create a new endpoint configuration. And in this configuration, we remove the variant A. So we only have a configuration that contains variant B with 100% of the weight. And again, we're updating endpoint. So we're calling update endpoint, endpoint name, and passing this configuration. And this is basically the second update you will see on this endpoint. So first it switched the traffic over, and the second update cycle will basically then remove variant A completely. So this will take a little bit of time, and then you can see the endpoint, and at one time it will then complete this update, and then the variant A should be removed. So this one is still working in the background here, making sure it still serves predictions. So let's give it a little bit of time here. So this is basically an example how you can deploy models to a real-time endpoint and also do some A/B testing and model traffic shifting here between. All right, so this one is really just running a couple of more visualizations and waiting for this endpoint here to update. Takes a little bit of time. So this, I think now it completed. So the notebook probably takes a couple of seconds to pick up. Yep, here we go. Let's run a couple of more predictions here. And let's see. All right, taking its time right now. So basically, yeah, this shows how to deploy the model in real-time endpoints. So while this is still considering here to execute or not, let's see the next example here. And the 03 is actually, yeah, this is cool. This is showing the torch serve example. So in case you've converted the TensorFlow model to PyTorch, you can run this. Otherwise, just, yeah, keep watching for a minute here and follow what I'm doing. So let me actually run this. Let me see if there's a kernel restart. I don't think so in this one. No, I think that looks good. So again, AWS has developed this open source project TorchServe together with Facebook to help serving PyTorch models, which has really not been that easy so far. Who would guess, right? And in this project, and here's the link to the GitHub repo, we're introducing this TorchServe architecture. And TorchServe has two APIs, one for the management, where we set up everything and register the models, and one for the real-time inferences. And there's a couple of steps actually involved. So it also has this model store here on the back end where the models, yeah, are registered, the ones that you want to serve. So how we do this is here, again, we're pulling in our libraries, we're installing Torch, and we're also installing Torch Model Archiver. So part of the Torch Surf architecture, we have to convert the PyTorch model yet to another format. So first of all, retrieve our model here again from S3. So we copy the PyTorch model here from S3 to local, and make sure we have that here. And then we have to create a model archive file. So this is just the way Torch Surf works. So it works with those MAR files. And you can use this Torch Model Archiver tool to basically create those. So let's define a name, reviews distilled word PyTorch, and let's create a local model store where we drop this MAR file. And you can call this model archiver, which we pip installed before, pass in the model name, give it this export path where to drop the MAR file. So this is going to be this model store folder. Give it a version, and pointing here to the PyTorch model. So this is a serialized file. And then you need a handler, and the handler is basically the code how to handle this model. So for the Hugging Face models, BERT models, they actually contributed here this handler already. So we're using this Python script here, which knows how to work with those Hugging Face models. And we're passing in some extra files, the configuration JSON, setup configs, etc. So in these, you can, for example, specify how this index to name conversion, so index 0 is star rating class 1, etc., gets handled. Pretty much what we had previously in this request response handler setup. All right, so once you've executed this in the model store, you see a model.mar file. And we now want to deploy this on SageMaker. So to do this, we're doing a bring your own container. And so we're looking here again, the model MAR file. You can unzip, it's basically zipping. So you can see there's the PyTorch model bin, this index name, JSON, setup config JSON, the handler, etc. All right, so everything always is in S3. So let's upload this Torch Surf model archive file to S3. And for the SageMaker container to pick it up, let's actually tar the model. So we have a model tar file. So it's a lot of zipping going on here. And then we're uploading the model tar to S3. And we've seen this before. So when you bring your own container, we have to create our image. So here we're creating another container registry called Torch Surf. And we're building the Torch Surf container and then push it to the Amazon Elastic Container Service registry. So let's just call this Torch 1.50.1.0.0, and let's do the Docker build. So we're using the Torch Surf container here and push the image to our ECR. And then we can create the SageMaker endpoint and deploy this model container. So here we're just calling a generic SageMaker model. And we're creating the model here with this Torch Surf tar. So that's the model tar file. The image URI that we just created, giving it a role. It's a real-time predictor. And we just call it Torch Surf model name. All right, so next I'm typing in here. Next, we're creating this endpoint configuration. So here's the endpoint. And on the Torch Surf model, we call deploy. So this is another way to just deploy it without specifically creating the config. So on the model itself, call deploy, passing the instance type and count, and an endpoint name. And now you can see that this endpoint is starting to get deployed, which again will take a little bit of time. but let's see if I click here in the endpoints, you can see this PyTorch endpoint is now getting created. And this is really just to quickly show you, actually, if you're curious to get started with TorchSurf, really cool project, how you can also deploy this on SageMaker. All right, so let me see. Yeah, this was the real-time endpoints. There is one more notebook here, which shows the batch predictions. So as I said, the second way to serve predictions is doing it in a batch job. And this notebook will show you how to do this. So you can also do a cell run all, I think, on this one here. Yep. So, and this one is similar to the concept we've seen before. So we have the training input data, or in general, the data in S3, which we want to run a batch prediction on. And we're creating this batch transform job and passing in a model to use for those predictions. And SageMaker will spin up the model container and environment to serve those predictions and write them out again in a file into S3, and then close down this instance. So pretty similar to the concept of the processing job. So again, we're pulling in the environment here. We're retrieving our training job name. And we can look again into the model here. It's the same BERT model we're using. We do have our inference.py. So here's the inference code with the input handler, which basically tokenizes, again, the raw text, and the output handler, which creates the predicted classes out of the results. All right, so a couple of configurations for batch inference. Obviously, you can do a couple of more settings here. So one is obviously to enable batching. That makes sense for batch transform. We have a default model name, so let's just assume it's saved model. You can set some batch timeouts here. You can set the batch size. And this basically corresponds to the max batch size also in TensorFlow serving. You can set here the number of seconds for the SageMaker web server timeout and number of batches to be enqueued. So a couple of parameters for this batch transform job. Then in the next step, you can do maximum concurrent transformations. And we just set this here to 1, and also the maximum payload size in megabytes. Then you define the instance types to run this on. So let's do an M5 X large, 1 instance. And a couple of more configurations. For the strategy, you can say, if you want to pass in single record by record, or if you do a multi-record. So in this case, we do a multi-record here, and the source is, again, gzip, text CSV, and we want to split by line. We're pointing it to our TSV bucket here, which has all of our data. And with that, we can run the batch transform job. So we're creating a model, pointing it to the inference py, to the source directory, pointing it to the model artifact, role framework, and passing in as environment variables those batch environment settings that we set. And once we have this model object, now the batch model that we called, we can call transformer with a strategy that we defined, instance types, assemble, concurrent transformations, etc. So we're passing in this information here. And then we can call the transform on this predictor with, again, pointers to the input data, splitting by line, any compression we have here on the data source, content type, etc. And this starts the batch transformation. So there's another deep link, which takes us to the SageMaker UI. And there's another section here. If you look up in the inference on the left, there is a section called batch transform. And this is where they show up. And you can actually see, so in my screen at least, I do have a couple of more that have run throughout the workshop. So actually, Autopilot also uses batch transform jobs to run those pre-processing pipelines here, for example. So it runs some batch predictions during that phase. All right, and the current job here is in progress. All right, so again, batch transformations also take a little bit of time. So if you want to keep that notebook up and running. And let me see. So yeah, in the meantime, just revisiting here my A/B testing that decided to finish. So just quickly here, I guess, to show you one of the visualizations. That was the one I was waiting for. So you can see here with the timestamp. And again, this is the model A/B, which we've done 2 or 3 notebooks ago. The first invocation, we had variant A and variant B deployed. So you see both spiking here for that prediction request. And after that, we updated the model to 100% of the traffic to variant B. And we had another round of inferences. And you see the second spike, only orange, the variant B responded. And variant A is here at 0. So this was the traffic weight shift from 50-50 to 0-100. And then after that, we completely removed the variant A. And this is here where the blue line disappears and then orange just keeps waiting for inference. So yeah, so this notebook also completed. There's a couple of more visualizations. And yeah, so let's close this one here, just clean up a little bit here on my browser. The hyperparameters should have finished in the meantime. So if you have the hyperparameter jobs still open, have a look. So you should see the results in here. They should have finished now. And you can see the optimized one being added to the lineage. And yeah, so I close mine as well. I had the warm start job running, so I guess that one finished as well. Let me see. So actually the second run didn't improve the accuracy too much. So apparently learning rate isn't really having that much impact, at least those little changes that we did. All right. Yeah, a couple of experiment lineage tracking checks here. So we see optimized 1 and 2 showing up. And yep, so I'll close down mine. And feel free to have a check in those notebooks that were still open. All right, so I keep that one. Oh, the batch transform. Yeah, the batch transform needs a little bit more resource. I think we've scaled it down to a small instance type. Actually, with the batching enabled, this one needs a little bit more resources, so that might fail. That is really basically just resource hungry and needs a larger instance. All right, so this was the example for the deployments. So let me close this one here. And this takes us to, I guess, one of the last steps here. And then after another break, Chris will take over and show the Kubeflow part. So maybe just a quick check-in. Shall I do quickly the pipelines, or do we need a quick break? So checking in with Chris here.
Let's do pipelines.
I do pipelines, all right. So let's keep rolling, and then we do a quick, I guess, handover and start the Kubeflow setup.
Yeah.
And let's take it there. All right. So this is kind of really kind of the peak of this model deployment. So we've really went through a lot of steps today, right? So we ingested, prepared the data, trained, tuned, deployed. And the natural question is, how can I automate this, right? How can I build a pipeline which performs these steps for me and then just automates and deploys the model in production? Yeah, I just probably need to refresh here a little bit. Let me reload. So, yeah, I'm not sure what's going on here. It's my console session, I think. We've been working long here in this console. All right. So the next step is to have this automated pipeline. And AWS offers a service called the Step Functions. And Step Functions is a general service to build workflows. So really all kind of different types. And they also launched a data science SDK which comes with predefined templates specifically for data science machine learning workflows. And this is really pretty easy to use. So in what we show you in I think 2 notebooks from here is how we can pull in this data science SDK from step functions. And we're gonna use a predefined training workflow, which performs these steps. So training of the model, creating of the model, configuring the endpoint, and the deployment as an SageMaker endpoint. So let's not waste too much time here. Let me just quickly make sure I have refreshed everything. Let's jump in 0.1, which is the create training pipeline with the step functions data science SDK. And let's do cell run all. Let me see. Always crazy scrolling going on, sorry for that. So what we're gonna do here, again, pulling in the SDKs. In here, we're pulling in the step functions Python SDK. So that's the pip install here. And importing step functions and the training pipeline. So this is the template that I mentioned, which is specifically for the SageMaker pipelines. All right, and setting up again some IAM policies and roles. So I'm going quickly through those. Again, it's giving permission for SageMaker to call step functions and step functions to deploy SageMaker endpoints. Everything has to have the permission. So we're making sure of this one here, creating roles, attaching the policies, etc. Again, we're pulling in all of the data locations, and here's the training script. So this is also a familiar one. So we're using, again, our BERT reviews Python script that we've been using the whole workshop. We're setting some hyperparameters. So those are pretty much also the same. We do one little hack to this training pipeline. So the template that is shipping out of the box assumes that we're using the same instance for training as we do for the deployment of the model endpoint. And we actually wanted to give different instance types. We didn't want to assume we're using the same, because for training, we use a little larger one here, and we wanted to host the model on a smaller one here, or different specification at least. So we're doing a little bit of extra work, which you wouldn't have to do if you're sticking to the template. But just to really show you. So also scraping again the metrics from CloudWatch and setting up the estimator. And this one is, again, we've seen this probably like 6-8 times today. TensorFlow estimator pointing to the training script here. Source directory, requirements, txt, role, instances, hyperparameters, boom. Now comes the setup pipeline with step function section. So we want to automate the 4 steps, right? Training the model, creating the model on SageMaker, creating the endpoint config, and deploying the model to a configured endpoint. And as I said, we're tweaking a little bit. So let's create a pipeline name here and also pull in step functions as a client. So this is the SFN, which I'm calling here. So what we're doing to do this little hack, we've copied the code from this training template or from the pipeline template. And we're kind of changing the code a little bit here. So we're pulling in training pipeline with different deployment instance types. So that's our name. And this is the code from the normal template. And we're adding some steps here. So I don't explain the whole code. It's basically setting up all of those steps from the training to, you can see here, training step, it's taking the estimator, setting up the inputs. Here's the step for creating the model. Here's the step for creating the endpoint config. And here's the step for the deploy. And we're basically tweaking here and passing in, when I find it, here it is. So also the deploy instance count and type. So we added a couple of parameters here so it understands those new inputs that we're passing in. Right, and then here in the endpoint config, we're basically setting the instance count and type to those 2 new parameters which we introduced. So this is the little hack. If you're sticking to the template and you just reuse the same instance type, you don't have to do it, but this is really just a little bit of extra coding for our own sake. All right, and then we can create a pipeline. So we're calling now our own code, so the training pipeline with different deploy instance type. We're passing the estimator. We're passing the step functions execution role. We're passing the input channels to the data, and a free location to dump out all of the information, client information. So this is the step functions client. And again, this is the customization. We're also giving the deploy instance count and type. If you're sticking with a normal template, this is just without those 2. All right, then we can visualize the pipeline. So we can print on the pipeline workflow definition to JSON. So this is the JSON code, and we can also render this. So make sure this might not work in Jupyter Lab. If you're currently in Jupyter Lab, you don't see that. That's why we put in a screenshot below. In Jupyter, it actually renders the graph. So this is the live graph. Looks pretty much like our training pipeline. So good. And so let's execute this. So let's call the create on the pipeline. And that one basically creates the step function workflow. And then we need to run execute, and execute kicks off one execution of this basically state machine or pipeline definition. And for the execute, we give a name, and we can pass in any hyperparameters if we have some additional ones. But we actually included them in the estimator, so we're good. All right, and then we can actually also render the progress on the execution. And you can see here that we're currently in the progress, in the training phase. So here's another deep link. So if you open up that link, that one takes you to the console, and we're now in the step function service. And you can see here is our training pipeline, and we see the live visual workflow. So currently we're in the training step, and you can see here in progress. It also shows you here the link to SageMaker. So this one starts the SageMaker training job. And if we go here, we should see that one, yep, is currently in training. So if you go to the overview here, you see the estimator training pipeline in progress right now. All right, let me close this, save and renew my sessions. I think the notebooks keep asking me here. Let me close this down. All right, so back to my create pipeline. So the pipeline is now executing, and this will also run for a little bit of time. It's again retraining, so a couple of minutes, and I'll just quickly show you what's happening below here. So this will run, it's currently training, and then once it trained and finished the whole pipeline, we're basically storing this information. And in the next notebook, I just opened the next one here while this one is still executing. In the next one, we're testing the pipeline. So here, basically, we're once the first pipeline is deployed, we have an endpoint ready at the end. So we're calling in the endpoint here, checking if it's deployed or not, and then we're invoking it. So we have the exact same request handler and response handler code here, doing the exact same thing as we've done before, and just run some sample predictions. So this is really just hitting the endpoint that gets deployed at the end of the pipeline. All right, we do have one more notebook. I'm just gonna quickly give you a sneak peek here. You can also now think of automating the trigger to that pipeline. So the pipeline is automating model training and deployment. And what we could do next is also think about what triggers this model training pipeline, right? And one example that we built here is, remember the use case initially when I said, we assume we have an application that is writing data into an S3 bucket into our data lake. So what we could do is watch this S3 bucket, and whenever data gets written into this bucket, we trigger the retraining of the model. And you would probably not do it on every single file that is written. So you would maybe schedule it maybe once an hour, or on a specific number of input dataset files, etc. And the way you do this is you enable logging on the S3 bucket. And by logging, it starts logging all the API calls, which you will see in a service called AWS CloudTrail. And we have another service, Amazon Event Bridge, which is basically an event bus, which you can use to receive those or watching for those API calls, and you define rules that match. And when a rule is matching, it triggers something. So in our case, we define a rule whenever I see a put object coming in this specific S3 bucket, which might be my ingest bucket, then I trigger a step function and I do the model training pipeline. So this is a simple way to automate this, right, and to trigger this. This notebook, once the pipeline is deployed, so obviously this also needs the pipeline to be ready and deployed and running. You can execute this or have a look after the workshop here. The code is available in the Git repo, how to set this up. So basically what we're doing here is we're creating a new S3 bucket for our data upload, which is watched. So all the API calls are sent and stored in CloudTrail. And we're also creating a CloudTrail specific, I think, here for this. Yeah, we're creating a separate CloudTrail, which just, you know, filters on those messages basically. And then we're creating a rule on this event bridge bus. So there's a little bit of setup involved here, pulling in the default event bridge that we have in all the accounts and creating a rule. And here you can see the rule. Source is Amazon AWS S3, and we're looking for API calls via CloudTrail. Here again, event source S3, and we're looking for specifically for API calls that are put object or complete multi-part upload or copy object. So this is just how the API calls are named. So put object is when you initially upload a file. Complete multi-part upload is a feature of S3. When you're uploading a large file, it basically starts a couple of parallel threads to do this multi-part upload to speed up the process. So the API call is different. So that's why we're also looking for this one. And also if you just copy an object, we want to keep it tracked here. And yeah, so this is kind of a rule. And when this triggers, so when a put object on this S3 bucket fires, we can set up a target. And this is the action that happens on the trigger. And here we're basically telling it to start our step function. So defining the policy here, event bridge, and telling it to a role here to invoke step functions, setting up everything here, and then we basically test it. So down here, we're passing in a couple of like the model parameters, which the pipeline kind of automates for us. So when we trigger an execution run, SageMaker basically pulls in all of that estimator and settings information. And because we're triggering it here like on demand from a notebook cell, we're passing in the model information here for the run to execute. So there's a lot of code here which just simulates what SageMaker already wraps up in those calls. And yeah, we're creating the rule target here. And then basically, yeah, we check the number of invocations before, and then we're uploading a file to the bucket and wait a little bit for the whole pipeline and events to trigger. And then we'll see that it starts another pipeline. So yeah, I haven't run this notebook here. I'm waiting on the pipeline actually to complete. So yeah, we can see here. So I think my pipeline looks like it succeeded. Let me scroll down. Execution progress completed. Looking good. So let me quickly run the second one here. See if that works. Pip install warnings we can ignore. Getting the training pipeline name. Yeah, it's probably still deploying the endpoint. Yeah, the endpoint takes a couple of minutes, so I guess it's in that phase right now. Let me see. Yeah, and here's the endpoint in creating. So yeah, the notebook checks. So once that one is deployed, we can run the prediction. And let me see if I can run this, automate the pipeline. This should work already, I guess. So setting up all the policies, attaching it. Yeah, I know it's a lot of code in here. Create the cloud trail. That looked good. Create event bridge. So I'm just making sure quickly that the code executed, and I show you this in the UI, which is a little bit nicer than following what's happening here. So just a bunch of really target settings and rules and locations and inputs. So I think that one looks good. Setting up number of invocation 1. Okay, so I'll quickly show you this in the UI. So if I go to F3, what we've done here is create a new F3 bucket, which is our, I think it's the test upload one, this one. And this one actually has, let me see, the object level logging enabled. So we're recording object level API activity here on this bucket, and you will see the data sent to CloudTrail. So let's see. So I quickly go to CloudTrail, and CloudTrail is a service that keeps logging all of the API calls when you enable that. So we've enabled it. So in this one here, let's see the trails. So we created a separate trail, which is just an entity here, DSO AWS. And you can see it's linked to a specific bucket as well here to store the logs, but just to keep things separate. And if I click into the configuration, we can see here that it's recording the F3 object level API activity for our test upload bucket, and specifically on writes. So we don't want to track all reads if you have a use case, obviously. For this one, we just want to trigger on writes. So we're just gonna log for those as of now. And this one basically does the logging. And with logging alone, nothing happens. So we've also included Event Bridge. So I'm quickly jumping over to Event Bridge, which is really kind of a general event bus you can use to connect application data from your applications. So a couple of input sources, if I zoom in here. So yeah, different AWS services, etc., can be an input source. And then you can set up rules, and the rules trigger something, right? So whenever the rule is basically invoked, you can spin up a Lambda function, you can call the step function as we're doing, etc. So this is really kind of a generic event bus, but really powerful. So event bus, there's a default one in all of the accounts. And this one we've just used. And what we've done is we added a rule, which we called an F3 trigger. And if you click that here, you can see this is basically the event pattern which we created programmatically. So looking for this bucket here and looking for the put commands. And we created a target. This is the action that fires up. And this one is our invoke step function state machine here. So that's the training pipeline. And we're passing in a bunch of input data. So that's the craziness that SageMaker makes for us when we do this, this normal training pipeline. Because we're invoking it here out of the context, we're passing in here all of the information, the settings, etc. All right, so this was kind of, I think, an easier way to understand that setup that went through the notebook here. And it takes a little bit of time, so we have some sleep timers in here, but basically we're uploading this file to the bucket, and we had one pipeline run before, and we check for the number of invocations, and we see 2. And we should actually also see this. Let me double check here in the step functions. I'm going in here and see, yeah. So here's our training pipeline. 1 succeeded, this was the initial one, and 1 is currently running. And this one was triggered by a file that we uploaded to this S3 bucket. So this is really a nice way if you want to play around to automate and to trigger such machine learning pipelines. All right, so this is pretty much what we have here in the pipelines section. So let me close down this, and yeah, so we do have one section here on streaming data. We're not going to cover this today. If you're interested, have a look. This is currently work in progress. So we started with sample notebooks here that create kinesis data streams, where we basically ingest our reviews to simulate the real-time data coming in, and we're reading it off the stream. We haven't yet completely integrated this in the use case. So this is currently work in progress. So I skip over that. And with that, it's time for Kubernetes. And I guess everyone needs a short break, but Chris will start, and we just kick off the creation of our Kubernetes cluster because that will take a couple of minutes. So I hand over to Chris. Let's get the cluster setup started, and then we can have a break. And after the break, we will then see Kubeflow in action and work with Kubeflow pipelines, deploy pipelines there, and see, yeah, what exciting things you can do on Kubeflow. So Chris, are you ready?
Yeah, okay. All right, let me share my screen. I posted in the Slack chat to please run that 00_00 setup EKS. Once you get that set up, that will run everything. There's going to be a couple more of these notebooks that we need to run, so let's get them started. Let me share my screen. Sharing. I'm going to switch to my headphones also. Okay, and last thing, I'm going to turn on my video. Okay, so if you should see my screen here, we should be run these. Oops, that's not the right one. Let's see. Okay, run 0000 setup EKS, and also run the 12.0001 configure environment. These two need to run for the next, run them one after another. After 0000 completes, please run the following. They have to run after one after another. Okay, so get to this point and then it should be smooth sailing. We're going to create the S3 bucket. We're going to launch Kubeflow, install Kubeflow onto EKS, and then eventually get to our link here that'll take us to the Kubeflow. So if you could actually do 00 all the way up to 00, try to get through 0005 launch Kubeflow one after another. Don't do run all, well, or sorry, do run all and then wait for it to complete and then go to the next one and do run all on that one. Wait for each to complete. And this actually will take probably 15, 20 minutes. So let's return at 3, let's see. Let's do 3:25. Let's do 15 minutes and try to get through this by about 4:30 today. So let's return at 3:25 PT. I know Ancha needs to go to bed, and I think a lot of folks on here need to go to bed. Okay, we will see you soon. Going to put it on pause here. Try to get up to this point. Okay. So we've got, thank you for all those that cast your feedback for the poll. So again, we did this a little bit out of order. We were supposed to do this poll at the beginning, but we got, we had to make sure that everyone got set up with an instance. So that took priority. Anja, if you get a sec, could you do the screenshots of the survey so we can capture that? Okay. So yeah, the F string and format. Yeah, people always talk about this. I don't know. I don't have a preference. I just write a lot of code, and the code always comes out with .format. Okay, so let's keep moving. Yeah, so let 0, run, and actually maybe we'll give it a couple more minutes because this next phase is critical. If we don't get to, and O2 is going to take about, or sorry, 0001 is going to take a couple minutes. So let's actually give it let's give it 3 more minutes and see where everyone's at. And then because we are running quite a bit late, I'm just going to go through and have you guys follow along. And yeah, so appreciate all your patience. Let's give it 3 more, or let's give it 5 more minutes. Let's return in 5 minutes. I'll put that in the chat. Okay, so at this point, we need to keep moving ahead. I know some of you are still trying to get EKS to come up. So yeah, a couple people, or yeah, actually one person is asking, and I should probably mention this, but the reason we're even looking at Kubeflow, turn on my camera here, make this a little more personal. The reason we are looking at Kubeflow is like open source. Kubeflow is a large community. The closest thing that you'll find, or yes, let me phrase this differently. Kubeflow pipelines is what most people talk about when they're talking about Kubeflow. And so today we'll actually focus on pipelines. That's probably the section that we'll spend the most time on. Kubeflow, it comes from the word Kubernetes and the word TensorFlow. Both these projects come out of Google. Google also created the Kubeflow project. Really, Kubeflow's initial use case, the solution, the problem it was trying to solve was doing distributed TensorFlow. So we spent quite a bit of time doing distributed TensorFlow earlier with SageMaker and BERT. We'll actually switch examples here, like we're not actually carrying through the BERT example into Kubeflow and Kubeflow pipelines. We'll do similar things, image classification, some other stuff. Yeah, so not so similar, I guess, but and in future generations, actually for the book, by the end of the year, we will have Kubeflow doing BERT. But for right now, we're sticking with some of the examples that we've used in the past and doing image classification and some other tabular type of like predictions. So the reason that we even consider Kubeflow is A, this is open source, B, it's Kubernetes native. And for those of you that come from a systems engineering or data engineering or sort of application development side, you'll like really geek out on the like Kubernetes aspect of this. Those of you coming from a data science background probably don't care about Kubernetes. And so our job here is to cater to like everyone, and we're going to show you how to do data science on Kubernetes. So you can pay attention to the Docker image stuff as much as you want, or you could just ignore it and focus on data science. We'll show it all. The benefit, and so typically what we see are for customers that are like currently using Kubernetes for pretty much everything, like we see lots of like workloads, microservices, Kafka clusters, Cassandra clusters, all kinds of stuff moving to Kubernetes. We are now seeing people want to take their data science workloads, machine learning workloads, and port them over to Kubernetes. So the cool thing about this workshop is we got to focus quite a bit early on you know, the like data science part, the BERT stuff. We didn't really have to deal with that much infrastructure. Like surprisingly, like depending on your background, you might have thought that was a lot of infrastructure. It's going to get even worse for Kubeflow. Meaning we have to pay way more attention now to Docker images. We have to pay attention to our clusters and monitor these clusters. We have to if these clusters die, there's things we have to do to spin them back up. Now, Kubernetes makes all of that easy, which is why people love Kubernetes. It's just one more layer that you have to think about, okay? So not only do you have to pay attention to distributed TensorFlow and checkpointing and all that kind of stuff, but you are actually managing your own clusters. So, and so versus having SageMaker do that for you. Some people like that flexibility. Some people don't care either way. So, and if you're not familiar with Kubernetes, think of it like a operating system for a data center or for huge clusters, right? So typically operating systems are a single machine, a single laptop. This is a like operating system for large scale clusters, can handle memory management, disk management, disk I/O bandwidth, network bandwidth. All of the typical single node system resources are now generalized across the cluster. Can handle GPUs, and we can schedule things on different nodes. So we can have heterogeneous nodes, and by node I mean instances, right? So we could have GPU instances mixed with CPU instances. We can label those instances, and when we want to run a particular training job on a GPU instance, we would label that instance as having a GPU. We would ask for this workload to find an instance that has a GPU and then run on that. So this is going to dive even deeper. We have this kind of sort of pear-shaped where, like bowling pin shaped, maybe, pear-shaped, where in the beginning we were looking kind of high level, and then we got deeper and deeper, and now we're exploding down into kind of lower level system stuff. So so hang in there and try to get as far as you can in the setup. At some point, you will hit this screen that says namespace. You want to use this word, right, the anonymous word. Name your namespace anonymous. If you change it, it's okay. We just basically hard code it to this just to make things, to keep things on Rails. And I think some of maybe 1 or 2 notebooks later, we actually do require it to be anonymous. Okay, so don't spend too much time, because I think we're only going to spend about maybe 30 minutes, 45 minutes in this area, just to be sensitive to people's time. If you want to, just focus on this and follow along with this narrative, okay? I'm going to shut down my Slack here because it keeps beeping in my ear and I don't know how to stop the madness. Okay, and I'm going to click through here. So I got to zoom out to click in. And also, I should mention too, anytime you have a question about Kubeflow, I guarantee 85% of the time, the answer is going to be because Kubernetes does this. So let me rephrase that. For example, someone will ask today, how do I do auto scaling with my TensorFlow cluster, or with my TensorFlow job on Kubeflow? And the answer will be, you use Kubernetes. And so Kubeflow's biggest strength is that it uses Kubernetes beneath the covers. Kubeflow's biggest weakness is that it uses Kubernetes beneath the covers. And I say that from 2 different audiences. So systems people love the Kubernetes part. Like I said, they like the flexibility. They like that it's open source. They like that there's tools to do the monitoring. The downside from a data scientist audience is that they have to think about Docker images. You can't just submit a script like we did with script mode with SageMaker. You have to actually create a Docker image when, if someone hands you a script that has, like MXNet or like PyTorch or TensorFlow, you can't just run it on Kubeflow. You have to build a Docker image. Now, some of the tooling's getting better. Some of you might be familiar. There's some projects called Kale, K-A-L-E, and some others that can automate this and take a notebook and then deploy it onto a cluster. That's kind of the holy grail of the Kubeflow ecosystem. But separate from notebooks, and we'll be in Kubeflow notebooks here for the rest of the day, and outside, we will move out of SageMaker notebooks and into Kubeflow, and that's that tricky transition point that I need to kind of guide you guys through. So please pay attention for at least the next few minutes here. So assuming that you get to, through all these steps here, 0001 takes longer than it should. I don't know why it takes that long. You'll see a bunch of scary retries. This will actually finish. You'll create the notebook, or sorry, the S3 bucket. That's pretty straightforward. And then, so the 00, we installed Kubernetes. And this is a screenshot, so don't be confused by this. You should see this word completed down here. 01, sets up some sort of Amazon-specific roles and things like that for security. And then we create the S3 bucket, which we've actually already created. So I'm running the exact same fresh environment that you all are, that like Ansha is as well. And these are all artifacts that we've created today. You should be pretty proud. So this is actually just going to recreate the S3 bucket. This is because sometimes we do the Kubeflow stuff separate, and we just want to have all the steps working. So there's no harm in trying to recreate it. So Kubeflow is the operating system, or sorry, Kubernetes is the operating system, which we set up in 0000. Now we're installing a application on top of this operating system That's called Kubeflow. And the fact that Kubeflow uses Kubernetes is just like using a library that you're building this application with, right? It's way more complex than that, but think of Kubeflow as an application on top of the operating system called Kubernetes, cluster operating system. And so once that's done, you'll see you can query the cluster here, and some of these things will be running. Terminating is actually okay. Let's see, I have to restart the kernel here to run this command. Just know that you'll see some things that appear to be broken with Kubeflow. The Kubeflow uses Kubernetes. Kubernetes self-heals. So if the application is written properly, it will take advantage of the fact that Kubeflow can restart pods and fix itself, basically. So that's exactly what we're relying on here. And you'll see before there were a bunch of error messages and things restarting. Things settle down. After a few minutes, things settle down. Okay, so assuming all the other stuff has been created and we're setting up roles, and all these are like best practices here to get these things locked down. And finally, you'll get to this, and this is going to be, you might have to run this once or twice just because it takes a little bit. Click this link, and this link, this is that awkward transition. Right now we're in SageMaker Notebook. I'm going to move that to one side, and when I click this link, I'm going to get to my Kubeflow dashboard. And you could tell it's the Kubeflow dashboard because it's going to have a bunch of garbly-goop. Whereas the SageMaker Notebook looks all nice and pretty and has a nice name that we specified earlier. So once you're here, you can pretty much forget about Kubernetes, or sorry, you can pretty much forget about SageMaker from this point on. Now we are entirely in Kubeflow land. Let's click finish, and here's our dashboard. So here we are. This is straight out of the box. This is Kubeflow. Nice, fancy UI here. And one thing that you want to keep an eye on is make sure that you're on the anonymous namespace here. That's the one that we created before. So, and this little hamburger in the upper left, some people call it hamburger, boom. You can kind of navigate around. We're going to go, so let me get back to, at the bottom of this is that weird transition point. And we've tried so many different ways to do this and make it less awkward, but it always ends up awkward. After you click the link, open it up in a separate window like we do here, and then keep following these instructions. So do the anonymous, click on finish. And this is here. I closed Slack, so I can't paste anything in there, but okay, get to this point. So create a notebook server. And follow these instructions. Make sure this says the anonymous up here. Call this notebook. Make sure anonymous is selected. We're actually going to use a custom image. And so put this in your copy buffer. Custom image right there. And please leave these settings or change them to 1.0 and leave that one 1.0 as well. So I think it's okay if you keep it the default. Don't go higher than this, otherwise it may not. We've seen people try to crank this up to 16 CPUs, and that cannot be found. We've spun up a cluster of 5 EC2 instances, and I believe they each have 4 CPUs or something. So you can't, just the way Kubernetes works, you cannot place a notebook server on a machine that's smaller than what you're requesting. So the short of it is keep this at 1.0. Okay, and then click launch. And this is actually pulling down this Docker image. Now we've customized this Docker image a bit just to keep things moving. Yeah, otherwise we have to do a bunch of installs and like do some other hacks. There's still a couple places where we do installs, but this isn't too far off from the stock. And this is actually using TensorFlow 1.13. We are waiting for Kubeflow 1.1, which should be coming out hopefully in the next month or two, and then we plan to go and then upgrade everything. We've already shown you TensorFlow 2.0, and we've pushed TensorFlow to the limit. So this section is just about Kubeflow and how to get things going, how to build pipelines with Kubeflow. And so I started to say earlier that Kubeflow pipeline is where we're going to focus. We finished the previous section with Ansha covered step functions, and step functions is a way similar to like Airflow where you can create a directed acyclic graph, and you can do execution of things in parallel, right? You could do like multiple work on yeah, just basically operate in parallel. So like one thing I could think of that we actually do with Kubeflow pipelines is we actually deploy a REST endpoint at the same time we're doing batch transformation. And so that's something that can be parallelized, right? Because while you're waiting for, so you shouldn't have to wait for the REST endpoint to be deployed before you start your batch transformation, if you have that kind of scenario. Okay, and let's connect here. So I'm just continuing, and similar to what we did in the SageMaker notebooks, we have to do new terminal. We're going to do this git clone. Okay, and let's see. Okay, so we've cloned it. Let's go back. Let's see, this says, yeah, do the git clone there, which we got. Now, similar, so this is the exact same repo, except instead of doing all the SageMaker stuff that we did up above, let's just jump down to 12 Kubeflow. Let's click on that. Scroll down. Let's follow the arrow here on the left, the instructions. 01 fairing intro. So let's start right here. And this note tells us right here to switch to the Kubeflow notebooks. So let's jump right in there. Okay, at this point, we can essentially minimize or get rid of SageMaker, and now we're exclusively in this land here. So maybe I'll wait, let me wait 2 minutes here to see if people will get caught up. Yeah, Ansha, how are we doing? Anything specific I could show?
Yeah, working with a couple of people here through the setup still, I guess. Yeah, want to make sure you're not creating the cluster twice maybe, or yeah, just double check that those setup notebooks all completed in sequence. So they're building on top of each other. So once the EKS cluster is there, make sure you're executing the next ones in sequence and they all finish. And for the load balancer, so the 05 notebook, which shows the link, the load balancer takes a couple of seconds to first to spin up and then to propagate the link. So also be a little bit, wait a little bit for that link to become online. Just you can rerun that cell that shows the HTTP link. And when that shows up, when you open it, just give the load balancer a little bit of time and the DNS to propagate.
Okay, and if you could grab the screenshots on the post-workshop survey too, please. Okay, let's keep cranking here. Just follow along with me. So I'm gonna do a run all. So fairing, oh, actually, yeah, so here's a good diagram. Let me zoom out here. So we've got Kubeflow is actually many different projects. Kubeflow is like more of an ecosystem. Primarily, people talk about pipelines. So lots of different components here. Operators is a term used by Kubernetes, which has been adopted by Kubeflow. You can create operators that know how to do PyTorch distributed, know how to do TensorFlow distributed, that's what TF job is, know how to distribute XGBoost. And so you could spread out all of the training across all the nodes, all the Kubernetes nodes. And that's all handled by these operators. So operators work in terms of Kubernetes primitives, which are like pods. Pod is basically a Docker container. One pod can contain multiple containers, but for the most part, pods you could just think of as a big Docker container. And so that's always what we're telling Kubernetes to do, is launch a pod. So for example, this notebook server, this Kubeflow dashboard is a pod. This notebook right here, the same way that we spun up a SageMaker instance in SageMaker, here we're spinning up a pod that has to be placed onto this Kubernetes cluster, onto this distributed, or this data center operating system, if you will. Okay, so Kubernetes supported by all the cloud vendors. Super happy to see this. The product I built before joining Amazon, Pipeline AI, was completely based on Kubernetes from day one. And I know so much about Kubernetes that I went and started working with SageMaker. Kubernetes is great, but will occupy a lot of your nights and weekends, and potentially distract you from your goal of learning data science. So keep that in mind. Okay, so Fairing is a particularly cool project. So I had mentioned earlier that there's this need by data scientists and by data analysts who want to take a notebook, from their notebook server and launch it on a cluster. And there's a couple different projects. Fairing is one of them. The other one was Kale, like I mentioned earlier. What we're doing here is we are taking a snippet of code from the notebook and creating a Docker image and launching that Docker image as a pod in our Kubernetes cluster. And all of that can be done with just 1 or 2 lines of code. So Fairing is the project that does that. One thing to note, this is a little tricky. In these Kubeflow notebooks, we have to install this. And then in some cases, we have to programmatically restart the kernel. And if you do run all, you'll see that everything stops, and then you have to kind of start from down here and run. So let me just run through this with you. Here, we're doing pretty low-level TensorFlow. This is kind of like if you're a Java person, this to me looks like writing bytecode. Like I'm not taking advantage of Keras and higher-level APIs. I'm just writing bytecode. But this is low-level TensorFlow. And I'm doing this right here in the notebook. Great, fine. What if I want to do this and actually deploy it onto a cluster? So this would be the scenario similar to before, where we're doing ad hoc, and then we want to move over to the cluster. So but to deploy onto a Kubernetes cluster, we need a Docker image. And so let's actually get this set up. So similar to how we built a Docker image for Spark earlier, and push it to ECR, the Elastic Container Registry, we want to do the same with our snippet of code. And so some of this is just boilerplate. This is all just kind of logging in and making sure that we have the right credentials and all that stuff. So we set up all the credentials in those 00 notebooks, 0000 through 0005. So everything can talk to each other within this private account. Okay, and we're going to run this. Now, this is essentially 3 lines of code. These 3 lines of code right here. Actually, I guess for maybe 5 lines if you include the if main. This here will actually take the train function. We're actually passing a handle to the train function that we defined up above, right here, that we called in the notebook just to show that it works in an ad hoc manner. Got some results here. We fit a line. This was just linear regression. and we go down here, we take this train function, pass it to Faring, and Faring can actually deploy this onto the cluster. So let's run it. This is pretty amazing. And it surprisingly works. You'll see lots of things here. This is as though you were creating the Docker image yourself, except it's doing it behind the scenes. It's calling the Docker API. It's packaging everything up and pushing it to the cluster. So this is Docker build kind of stuff and Docker push. All we have to do is give it a base image. And this is actually using TensorFlow 114. Yeah, not a big deal. Because keep in mind, no matter what version of TensorFlow we're using in the notebook, we can choose a different version and deploy it onto our cluster. So because everything is being isolated by Docker images, I could choose to do 2.1.0 here. I don't know if the code above works with TensorFlow 2.1. We will update that in a future iteration of the workshop before the book. But this is to show, this base image comes from Docker Hub, comes from the public Docker repository that TensorFlow has contributed this base Docker image. And this is Python 3 with TensorFlow 114 preloaded. You could point to your own base image. You could create your own yes, a base image that's passed all the security scans specific to your enterprise, startup, whatever you got going on. So at the end of this, we should see these are the actual pod logs. Now, again, a pod is a Docker container, essentially. And okay, so this actually ran so fast and completed that we don't even see the pod. The only pod that we see is the notebook, which is actually physically what we're like interacting with. So if we reran this and if we rerun it, it should actually run faster because the Docker image was already built, waiting for the job to start. We should be able to catch it in action here. Let's see if we can catch it. Right there. So there's the job. Don't be fooled by the term terminating, status of terminating. That can actually be okay. It should probably go to completed. At some point, I think we missed it again. But here, it actually fit a line to this data set and gave us an output. Now, this ran on the cluster, so we could scale this up as large as our Kubernetes cluster lets us go. Okay, let me see if I can actually, oh, yeah, I can't. Okay. So pod is what we are always deploying. So this notebook server that we are currently running doing shift enter is this pod right here, which is kind of cool. Very meta. All right, we could do one step further here. Let's just run this. This is XGBoost. This is a slightly different API to do the same thing. This API has gone through some changes, but wanted to show it to you in a couple different ways. This is actually launching. So this is doing, let's see, what is this doing? This is a housing data set. It's XGBoost, so it's classification, or this particular one is classifying, or no, I believe this might actually be regression. Predicting housing prices, something like that. So this is the same thing. We're doing it here in the notebook. And then, so actually, let me do run all here. Oh, I did run all, but I got hit by the thing I was describing. This restart kernel here gets in the way. So same thing, we're just running through this and pushing, building the Docker image. So this is running it here in the notebook. Okay, very exciting. And then let's run it on the cluster. So that's what's happening here. And this is train job submit. We give it some input files. We also can pass a requirements txt, which is super useful. And here it's actually building the Docker image, pulling in the requirements txt. And this is going to complete the same XGBoost. Let's let that run for a minute. Okay, so yeah, let's assume that that runs. I'm going to jump over to TFX. I'm going to cover this section briefly and more at a high level of what TFX is. TFX, if you think of TFX as a set of Python libraries, you're not too far off. Some people, maybe argue the other way, but the way that you would use TFX, so like TFX and Kubeflow are sort of orthogonal. They can be used separately. I don't need to use TFX with my Kubeflow pipelines, and TFX doesn't need Kubeflow. They're nice together, and they've been kind of, well, they were created separately actually within Google. They've tried to come together on certain layers like this metadata store down at the bottom. This is actually very hotly, or this is currently being actively worked on, is how to integrate TFX as a metadata store with Kubeflow's metadata store. They came from different groups and slightly different use cases, but the idea is, so think of TFX as a set of libraries that let you implement the whole pipeline. So feature loading, similar to the data ingest that we did with BERT, with the like Amazon customer like reviews data set. Statistics gen, so this is analyzing those features. This is doing data analysis and highlighting any anomalies, highlighting null fields, like data quality checks. So this would be DQ, for example. And so just like DQ is a Python library or Scala library, soon to be Python very soon, you can use these in your Python-based code pipeline, or sorry, so your Python-based data pipelines. So we've got data ingest, or feature loading. We have feature analysis, so like data quality checks. Feature transformation. So this is what we did when we converted raw data into BERT tokens. Schema generation, and then data validation kind of goes with the statistics gen. The term gen is just a suffix that's used by the TFX creators. It comes from Python generator. It's like generating things from one source to another, or from an input to an output. Feature transform, and so schema gen can actually look at all of the data and then recommend a schema. So similar to DQ, it could see, this field always looks like it's one character, Y or N, and you can then apply schemas to the input data. Feature transform, we used SageMaker processing jobs for this. Now, the way to scale TFX to large data sets, this will require you to use something, so something like Beam, right? The Apache Beam project is kind of similar to Spark streaming, I guess you could say. It's not really, but and there's like integrations. So Beam is kind of the Google way to stream through all your data, and to be able to stream through large data sets and do large like transformation. So I haven't used Beam much outside of TFX, but it's a fairly active project, more specifically like within Google, but seeing more and more of it recently. Model train, so this is the most boring part, of course, of the machine learning pipeline. This is the part that I've been committed to focusing on since I've joined Amazon, because I don't have to worry about like a lot of the other stuff. And then the evaluation. So after the model is trained, we want to look at those metrics, the evaluation metrics, look at the accuracy, look at the AUC, look at the F1 score, figure out which model is best. Do we want to retrain it? Do we want to try different hyperparameters? Once we actually choose the model, we then go to model deploy. So all of these in the orange boxes are the actual names of the Python class that you would use, and you can extend it. And right now TFX is laser focused on TensorFlow, and that's one of its strengths towards the TensorFlow community, but doesn't really help out much beyond TensorFlow. So for example, all of these components work really well with TF Record. However, if you're not using TF Record, you have to do some adapting and actually do some customization. So Possible limitation there if you're using some other format or not really willing to go down the pure TensorFlow route, but hasn't seemed to be too much of a problem for folks. TF record's pretty efficient. Okay, and all of this has to tie together with this metadata store. So think of each one of these as a node in a pipeline in a graph of execution, directed acyclic graph. And so we could see, where there's arrows kind of branching out or these dotted lines, that's where you would see two things happening in parallel because they don't depend on each other. So statistics gen, for example, can generate the schema at the same time it's doing the feature validation, right? Rows of data and figuring out if these are valid. So yeah. All right, and TensorFlow data validation. So TensorFlow data validation, TFDV, actually is a pip install. So we've already pip installed these. And TFX is actually going through quite a bit of improvement over the last year or so. There's newer versions coming out quite often. So hoping to pick up the latest once Kubeflow 1.1 hits. But it's been pretty stable for a while. Now, this particular, so if we do run all here, there is a bug, and actually someone pinged me offline and they fixed it, but it ended up breaking the whole rest of the workshop. So we are not going to fix the bug that we see here. It's a display bug. It's a like UI bug. So TFX data validation, TFDV, is similar to like DQ, where but has this really cool feature that works with Jupyter, or used to work with Jupyter, where you could actually have this like interactive, what's called sort of facets of your data and different slices of your data. So, for example, this is, I believe, the Chicago taxi data set. You could slice your inputs because, keep in mind, this is the data validation. This is data quality checking. So this is this is at the very beginning stages of the pipeline. So we would want to visually look at this data and look at the distributions and see different slices. Maybe a particular time of day, we have more data than we do other times of the day. For example, peak rush hour for taxis, for Ubers, things like that. They have way more data then than they do at 3 in the morning, 4 in the morning during a global pandemic, for example. So the ability to slice and dice here and take a look. But this kind of gives you an idea of how to generate the schema. So this was able to look at the pickup community area column or feature is an int, it appears, and so different ways to do things. This is what like Amazon's all about. We're showing you if you really do want to use Kubeflow, this is the recommended way to use Kubeflow with Amazon. Okay, so unfortunately, yeah, like I said, we've only got a few samples here that are rendering okay in this notebook, but this is saying it found a feature called company, and let's see, what is this? High length distance between serving feature. So this is a way actually to detect drift. Someone brought up drift on the Slack channel and skew. So skew would be you've trained your model one way with one particular set of data that had a particular distribution. And suddenly there's a global pandemic, and now you have way less data, or the data is all over the place, or what used to be peak time is like no longer peak time, and this could completely throw off all your models. And so, people aren't really talking about this, but folks at like Netflix and like Uber have to go and fix all of their models to not predict the same way that they did back in January or in 2019. And so while this doesn't happen that often, there are times when skew will cause problems in your pipeline. And specifically, it's typically around the way the model was trained, and now there's different data coming in during prediction time. So let's say we trained the model on 2019 like data, and we have the model deployed, and now 2020 hits, there's a whole different situation happening. That model just can't perform accurate predictions based on the new distributions of data that are coming in. So it's often called training serving skew. Training time, the model's trained one way, model serving and there's skew between model serving those predictions during serving time. Okay, so let's keep moving here. I'm going to skip TFX transform. It's actually kind of a boring notebook, but does talk about the Apache Beam stuff a little bit. So, transforms this middle box here. This is a really simple example. It's pretty heavy on TF record that we showed earlier. It shows some of the ugly Beam code here. Maybe it's not ugly, but I just haven't looked at it enough. I'm sure it's fine. Okay, TFX serving. So not a lot of people know this, but TensorFlow serving was actually the original TFX project. It was released along with TensorFlow back when TensorFlow was first launched back in, I believe, 2016, or yeah, 16. So TensorFlow serving, we were actually using. We were using it in the REST endpoints. We were using it in batch transform. And yeah, TensorFlow serving is pretty powerful. What's cool about TensorFlow serving is it's C++, and it can read the exact same graph that's generated from your Python code. So Python is really just an API that's letting us generate this graph that then can be picked up by the C++ binary for super fast predictions. And so you, for the most part, really want to be using TensorFlow serving when you can, when it's appropriate. I've seen some folks use TensorFlow serving in a batch context. Doesn't always work out. There's a lot of overhead with the sort of HTTP calls in and out of TensorFlow serving. TensorFlow serving does support gRPC. In fact, TensorFlow serving only supported like gRPC until relatively recently, maybe a year and a half, 2 years ago. So gRPC is way faster, performs way better, and should keep an eye on that. So I'm going to skip this for the sake of time, but this is essentially building and installing and starting TensorFlow serving. We've effectively done that by deploying those REST endpoints earlier. Okay, let's get to the good stuff. Kubeflow pipelines. So let's run this. I believe this might do. Does this do the restart? No. Okay. So let's do a quick pipeline just to get you familiar with the API. Very simple pipeline. Let me start from the top here. We have to do a pip install. I think we're picking up a newer version here than even was in the Docker image. Wanted to make sure we got a somewhat current version. Okay, Kubeflow pipeline. We're basically doing what we did in the step functions, but we're doing it all with Kubeflow. Very similar to Airflow as well too, if you're familiar with that. So with any directed acyclic graph based construct, we have to build up a graph. And here we're going to do something really simple and kind of silly, but we're purposely keeping it silly because it actually ends up getting complex with these Docker images. So all we're going to do is add two numbers. I think we make it slightly more complicated where we add two numbers in parallel. Yeah. So this is add two numbers, give it A and B. That's what we're going to add. We're going to give it this name, calculate sum, give it a base image. This doesn't need much. It just needs Python, because all we're going to do is call file.write. And let's see, file, yeah. And so this is the function. And and then notice, so we did pip install KFP, Kubeflow pipeline. KFP so KFP gives us this domain-specific language, so DSL, and the way that we build up a graph with Kubeflow pipelines is through these things called container ops. Now, container op is a horrible name. It comes from Docker container, basically. We are going to launch each of these add to number functions as a Docker image on our Kubernetes cluster. And some of you might be laughing. I laugh saying it. Seems kind of ridiculous, but we're showing building blocks, and you can make things, you know, more complex here in a bit. So we also have an op that does echo, and this, yeah, interestingly enough, doesn't even need Python. All it needs is bash. So very, very lightweight Docker containers. And all this is doing is, you know, up here, this is calling Python-C, and then giving it just a simple line of code here to add the two numbers. Echo is then writing out. And, you know, this is just simple, just showing how to get things in and out of these containers and how to write to the console. So now we're going to pull everything together. So this, yeah, so we were doing container op earlier. Now we have DSL pipeline. And pipelines you have to represent in terms of those container ops. So we have add two numbers A and B, add two numbers C and D, and then we're going to add the sum, those two sums to each other. And all of this builds up because of this this Python decorator here. So the DSL has been written so that you could decorate your Python functions, and that will then construct this pipeline for you. And then all we have to do is call compile to, you know, build all this. This puts it into the zip file. We can actually do, if we do unzip, I'll show you this. You don't have to do this, but calculate sum pipeline.zip. This is really simple. Oops, let me stop that. Oops. Oh, was a dash force. Anyway, I think it's actually already there. So pipeline.yaml is what gets generated from this compile. And this gets zipped up just to have one bundle that gets uploaded to Kubeflow. You can even see the misspelling there, so we know this is genuine. It's not, there's no trick up my sleeve here. And all it is, and so anytime someone gives you YAML, this is like a little inside tip. When it's in the context of Kubernetes or Kubeflow, always search for the word image. And this tells you the exact image that's being used. And you can work backwards from this image. Oftentimes we'll be looking at an example and it looks great. You can't wait to use it. You run it on your Kubernetes cluster or Kubeflow cluster, and you don't have access to the Docker image, and you have no idea how it got in there. So fortunately, this is a public Docker image. It's just Python 3.6.8. There's nothing fancy here. There's a lot of this kind of extra stuff that's added by Kubeflow during this compiler thing. Back before Kubeflow pipeline, Python API, we had to do these by hand, and it was horrible. And so there's also a way to do this command line as well too, if you want to make it part of your Jenkins run or whatever you got going on there. So, and then this is really cool. With just a couple lines of code, I'm creating an experiment. So we see that word experiment here. Create that and then run the pipeline on the cluster. So I'm going to follow this deep link, and I should see this took 30 seconds. Okay, probably most of it was just pulling down Docker image. I bet if we run it again, it would be a little bit faster. And here's the slick Kubeflow pipeline UI. People go crazy for this. I still love it. Every time I see it, I get excited. And I can inspect the inputs. 4 and 7, I see the sum. This one, I see the same. Calculate sum, the 11 and 17, the sum of the sums, and then an echo. Now, echo is the only one that actually prints anything to the log, so I can click log and see that it printed 28 at the end of that. So pretty basic, but shows you how you can go from Python to Kubeflow with all the Docker image and stuff hidden from you, for the most part. All right, that was pretty simple. Let's do, so let me show the SageMaker one, because I actually like this. I think it ties a lot of stuff together that we saw earlier. So I'm going to do run all, and see that the kernel got restarted here, so I have to go run these separately. What this is doing, this is a way to use the best of SageMaker, all the stuff that we showed earlier, with the flexibility and the portability of these Kubeflow pipelines. And so I can actually mix and match. I could use SageMaker when it makes sense to use SageMaker. I could call into other systems. I can even call out to like other clouds as well too. All of this can be coordinated through Kubeflow, which is pretty cool. So, so that's really why people love Kubeflow pipelines, and that's really what people talk about the most. Of course, Kubeflow includes Jupyter notebooks like we're using here, and has TensorFlow serving and has TFX and all kinds of other stuff that falls in there. And so this is creating this pipeline. Let me see. We should be able to pull it up here. I'm going to spare you some of these details, but just know that at like Amazon, we've actually implemented our own container ops that handle all of, so calling this training job, for example, and then deploying, doing a batch transform. All of this is hidden behind the Kubeflow pipeline API. And so you can define your own custom operations. And so that's exactly what Amazon has done. We have our own Kubeflow pipeline components, these like container ops, that you can then, here's the like metadata that's describing it. Now I can access it, and this operator, or this particular component knows how to talk to the SageMaker API. And all of the like IAM roles and everything is all locked down to this particular, to this notebook instance, to this Kubernetes cluster, calling out to SageMaker. So all of the credentials are handled behind the scenes, so you're not passing keys and all kinds of crazy stuff. Okay, so I'm gonna zip through this and just get to the cool part here. Here we go. I'm gonna click on the experiment, and we see we've got one in progress. And this is going to be, so this is going to train the model. It's going to prepare it for deployment. It's going to deploy a REST endpoint and also run a batch transformation. So all of this is going to happen behind the scenes. And this is going to take a few minutes because has to pull down all the Docker images and do all that stuff. So let's keep going. I'm going to launch, let's go to the next notebook, 0302, Pipeline Advanced. Get on the time here. And this actually should probably follow the intro, the pipeline intro, simple one. And then we would go to the more advanced one, but a little bit out of order, but it's pretty much the same thing. The net result is the same. So let me run through this. Just ignore all those warnings and stuff. We've learned that today the hard way. So let me show you what's going on here. So I showed you a simple Kubeflow pipeline before where we were adding 2 numbers and then 2 sums of sums. Now we're actually going to do something a little bit more complicated and stay with, and then I showed you how to mix and match Kubeflow pipelines with SageMaker, which is pretty cool. Now this is how to use the other parts of Kubeflow, including hyperparameter tuning, which is Katib here. And so again, the Kubeflow community has built their own container ops and Kubeflow components that run within Kubeflow pipeline, just like we've built them also for like Kubeflow pipelines here. Okay. So we've got Katib. This is doing hyperparameter tuning. We've got, what else do we have here? We've got TF job. This is actually launching a TensorFlow distributed job. And this is setting up which one is the chief, which is sort of the leader of, and then workers, and launching this on the cluster. So this is pretty crazy code. When I first saw this code, I was just like, oh man, this isn't even worth trying to figure out. But once you kind of stare at it for a while, it starts to make sense. There's a bunch of helper functions that are in here that try to simplify things. The end result, I'll just show you here. So the end result, oh, did I run 2 of them by accident? I think I might have run 2 by accident. Is going to be this graph where we do training, we do hyperparameter tuning, we deploy the model, and then launch a little sample UI, which is pretty slick. So yeah, let's let all that run. We're probably pushing the small little cluster we have a little bit too hard, but and then when we're done here, we're actually going to make a prediction. which it looks like it actually did. Or no, it didn't actually make it. So we have to wait for that endpoint to deploy first. So if you see a connection error, you need to wait for the pipeline to deploy. That's my own error message that we are, yeah, just to remind me that I have to wait. Okay, so I'm gonna keep going. We'll bounce back to the SageMaker and the advanced pipeline here in a bit. Distributed training. This was why Kubeflow was created. People have kind of forgotten about this, but like I said, Kubeflow is a combination of Kubernetes and TensorFlow. The idea here was to make TensorFlow be able to distribute across a cluster easily without having to hack a bunch of files together. Okay, so I'm gonna skip the fundamentals of distributed training. I'm just gonna get right into this and run it. Okay, so I think we do TensorFlow job. The first one, we launch a TensorFlow job with 2 parameter servers, which is handling the passing of parameters between the different workers. So there's 4 workers. One of the workers, the 0th worker, is typically the chief or the leader of this cluster. The parameter servers are stateful, and the workers are stateless. So parameter servers are storing all of the gradients that are being learned and the weights that are being learned by the network. These workers are looking at batches of data and then calculating and then sending that data to the stateful parameter servers. All of this was happening in TensorFlow on SageMaker. It's just that we didn't have to think about it. And so container creating typically means it's downloading the Docker image, and looks like a couple of these are still starting up. Some of these are starting to work. Now these workers will sit idle until the leader shows up and the parameter servers have been initialized. So now all of them are running. We could actually look at the logs on one of them. We choose the master. If you're familiar with Docker, with Docker logs or the Docker command line arguments, that's the kubectl is similar, but it's looking at the entire cluster. So this is saying, get me all the pods and filter only the ones that have distributed TensorFlow. Give me the logs, that's the actual container logs that are being spit out by the TensorFlow training job. And so all of this is coming out. I could keep hitting this for a while, or I could just kind of keep moving on here. We could do the same with PyTorch. Oh, and let me scroll up a tiny bit here, drive everyone crazy with the scrolling. This is all that you need to do to launch a TensorFlow job. Now, tooling is coming. Right now, the tooling means copy and paste this code. And so, like I said, whenever someone hands you YAML and the word kube is involved, Kubernetes Kubeflow, search for the word image. Okay, I see this as image GCR. I have no idea what this is. So what do? You go and you Google it. Type that into Google, and this should actually you can work backwards and get so this was created by Google, lives in a registry. I still don't quite know where it came from. You have to kind of Google around and just figure out, where did this thing come from? And at some point you will end up having to Google this word here, the name of the actual. You would end up just Googling this, basically, and then figure out which GitHub repo actually led to this. It's very likely that it is in the Kubeflow ecosystem somewhere. You're going to look for the Docker file. That's that's the starting point for all Docker images, and figure out what's inside of there. And there's going to be some hard-coded .py file, train.py file that's in there that knows how or that can do distributed TensorFlow. And all Kubeflow is doing is just spreading it out across the cluster. And you can, in TensorFlow terms, you could say, I want 2 parameter servers. I want 4 workers. These are all specific well, actually, they're not specific to TensorFlow, but they're used by TensorFlow. PyTorch calls them something different, as we'll see here in a sec. So let's look at the PyTorch equivalent. So PyTorch has what they call master and worker. You've got two replicas for the worker, one master. It's just what this particular job needs. This is the person who wrote this. Where did this come from? I have no idea. I have to go Google for this and work backwards. You could also tell it to use GPUs, and all of this gets passed down through Kubernetes, and Kubernetes works with Kubeflow, which is an application. Kubeflow, the application, works with Kubernetes to find the proper resources across the cluster. So we would run that. Let's go look at, we've got one master, two workers, just like we requested. Let's take a look at what's running in this master, and here we see the training job. Okay. We could also take a look at the workers too, if you'd like, and change this to, instead of master 0, I could change it to worker 1. Let's see what's going on that thing. Doing the same thing. Every worker that's involved in this cluster has pulled down the data and is operating on a different subset of the data and making suggestions back to the leader. Okay, metadata tracking. We talked about this a little bit earlier in terms of the experiments API with SageMaker. I mentioned TFX has a metadata layer that's required between all the nodes in our execution graph. And this is a little glimpse into it. This is the project called Kubeflow Metadata, KFMD. You would pip install this. Let's run this. Now, this is a little bit kind of, well, no, actually, I think this is real live working code. I think some of it's hard coded, like, you know, S3 paths and things. So what we're doing here is similar to what we did with the experiments API, where we logged the input, we logged the S3 bucket where the data came from, we logged the hyperparameters. All of this stuff, so this can all be logged, and this becomes part of the experiment lineage, of this model's lineage. So when this model gets deployed, we want to back up and figure out how is that model, how did that model get to where it is? And so some of this is just kind of made up data, but at the end of this, we can go into, let me see, sorry for scrolling here, I gotta complete. Okay, so we've got that there. And what we could do is click on the hamburger and go to artifact store. Some of the terms are, you know, a little bit all over the place, but we see with the artifact store, we see where data came from, and also the output. So, you know, this is just kind of sample data I've run through a couple times here, it looks like. But this is the start of a metadata tracking system for Kubeflow. Some of you might be familiar with a project called MLflow, which is from my old company, Databricks. And Kubeflow and MLflow actually right now tackle different things. Kubeflow, the strength of Kubeflow right now is the pipelines and the fact that it's using Kubernetes beneath the covers. The strength of MLflow is more on the model tracking and sort of metadata tracking and experiment tracking. So I've seen people that combine the two with MLflow, which we're not talking about today, but we do have some material on our YouTube channel. And you can actually, with very, very low code, small amounts of Python snippets, you can log experiments, log outputs, all the same stuff that we saw with the experiments API. Okay, so I think the final examples here will be hyperparameter tuning. I think I'll probably skip neural architecture search. We talked about hyperparameter tuning quite a bit. I do want to introduce you to some terms. Khatib is the name of this project. Khatib is sort of the umbrella project for hyperparameter optimization within Kubeflow. Khatib is based on the Google Vizier paper, B-I-Z-I-E-R. There's a link to it there, which really, was, sort of summarized hyperparameter tuning in sort of Google terms, right? And talked about various strategies that they use: random search, grid search, Bayesian optimization, a newer algorithm called Hyperband, pretty cool. All of these are trying to reduce the search space to explore and find the best hyperparameters. So yeah, obviously random search is random. This probably annoys some of us that are more OCD. We want to explore all the options. And so people would use grid search. You know, these days compute's relatively cheap. We could do things in parallel. Bayesian optimization can learn from training run to training run and can narrow the space. Maybe this learning rate and this epsilon and this trainable flag equals false or freezing the BERT layer, that particular combination doesn't work. So, and we can statistically rule out portions. And so that's what like Bayesian optimization does, and hyperband similar kind of concept. So grid search is the most brute force that checks all the different combinations. These are combinatorial combination, you know, sets of like combinations, sets of these hyperparameters. So these can get pretty large pretty quickly with each new hyperparameter that you add. So here's an example. Let me run this. This is how you would define the search space that you want to search. So feasible space right here. So LR is typically learning rate, number of layers. This is actually saying, I want to try a deeper neural network. And so if you think about it, your architecture for your neural network can actually be a hyperparameter. So maybe I want 5 layers, maybe I only want 2. Who knows? Yeah, let's let random search or grid search or Bayesian optimization figure it out. We can also alter the optimizer. So before we used specifically atom optimizer, but we could switch to just regular SGD, stochastic gradient descent. So we could actually try different optimizers, which is pretty cool, and starts to bleed into neural architecture search a little bit. There's some subtle differences, but for the most part, we are trying different ways to learn our data set and to fit a model to our data set. Okay, so here's how you would do grid search. I think random search was up above. See if we can get a glimpse. And then Bayesian. One thing about Bayesian is you want to do a small number of trials and then learn from that, and then add on more trials and add on more trials. And I think I might have missed it, but I'm sure that like Ancha mentioned it, that with like Bayesian optimization within SageMaker's hyperparameter tuning, you want to make sure that you give the Bayesian optimizer time to learn, and you don't want to do all 10 runs at the same time in parallel. You want to do, you know, maybe 4 runs, maybe, or yeah, let's take 12, for example. Don't do all 12 at once. Do 3 rounds of 4. So do 4, learn from that, make the changes. This is all built into the Bayesian optimization strategy, and then learn from that, do 4 more, and do 4 more. So you want a good balance of being parallel, but also being able to learn from previous runs. Okay, hyperbands, just another statistical way to narrow the search space and find the best hyperparameters. Skip neural architecture search, to me, it's kind of similar to this uses reinforcement learning, which, yeah, I know everyone gets excited about, but basically making small changes, seeing if it adds a reward or takes away a reward, or adds a loss, and tries to figure out what's the best architecture to use. So, but at the end of the day, we're checking different combinations, and it's just different strategies of the same thing. You might be seeing this particular diagram. Pay attention to these. These are called parallel coordinate plots. These are super valuable if you haven't seen them before, but gives you the ability. So let's see, on the left here on this, so left over here is the validation accuracy. And that's what we're trying to optimize, obviously, makes sense. I could start there and back up and look at all of the hyperparameters, the learning rate, the number of layers, the optimizer that were involved in this experiment. So that's pretty cool. And yeah, each of these is a separate coordinate system. So, but keeps everything kind of normalized, which is nice, gives you one clean visualization. And actually that's one of the strengths of MLflow also, is it can do this as well and help with hyperparameter tuning. Okay, last thing, I love to end on this, optimize TF Lite. So TensorFlow Lite, this is a little disconnected from the pipelines and stuff, but I just like it. I think it's cool. If you're not familiar with TensorFlow Lite, we actually cover this a bit in the book as well too, but it's a way to train your model. So let's say that you've trained your model, all right? We've gotten to that point. We ran distributed TensorFlow earlier, built some pipelines, got the model, and now we want to make this model a little bit faster. You know, maybe it's a little too bulky. You know, maybe it is 260 megabytes, and we need to fit this onto a smaller device, for example, or we just want to try out as a hyperparameter to try to quantize, is the term, from 32-bit down to 16-bit. When you can take 32-bit math and drop it down to 16-bit math, you will instantly get a 2x speed up for the most part, based on current hardware. And also even newer hardware, these newer GPUs like the Volta V100, which is in our P3 instances, they are actually optimized and have special hardware for 16-bit math. And so we can then use mixed precision also, which is kind of one more step of like optimization, where we can do certain operations at 32-bit to capture more of the dynamic range of our floats and our the like exponents. And then we can, for then other ones, we could use only 16-bit. And the hardware and the framework will figure out which ones, which hardware should actually get it, which of those cores, the 16-bit or the 32-bit cores, should be pulled in. So super cool. This like really required a lot of effort and joint effort between the NVIDIA folks, between TensorFlow, between PyTorch folks, and the folks at like Intel. You know, so hardware folks working with these frameworks, very, very powerful, huge gains. In terms of hardware, this is relatively low-hanging fruit, and in terms of what we're trying to do here, it's very obvious. And so the flip side of this is that we lose a little bit of accuracy. And in some cases, that's okay. Maybe we trained our model so well, it's 97% accurate, and maybe we drop to 94% by switching to the float 16, to the 16-bit. But at the same time, our predictions are twice as fast, and we can deploy them on small little webcams everywhere. So this is very powerful. These days, this is pretty common. So this term quantization can essentially quantize, you know, it will take a look at all of the values, all of the weights that you've learned during training, and could fit them into a smaller 16-bit range, but still keep that like dynamic range between. And by doing that, now each float, each weight that we've learned can now be represented with only 16 bits. And on a 32-bit processor, we could actually write like multiplex or like parallelize those operations, and yeah, instantly get a 2x speed up pretty quickly. And yeah, like I said, GPUs also have optimizations for 16-bit arithmetic. All right, so when we run this, let me show you something cool here. So here's an example. We have kind of a made up model, like just a simple linear regression here, I believe. And this is old school TensorFlow code. I like to get old school sometimes. Okay, so scrolling like crazy. All this is doing is just linear regression. We fit kind of a crappy model, doesn't matter. We're not focusing on the like accuracy for right now. Interestingly enough, this is linear regression. As far as TensorFlow is concerned, when you train your model, this is what your model looks like. And I had mentioned before that we actually save the model, or we have the capability to save this model in an inference optimized manner that'll strip out all of this stuff that's needed. This is needed to continue training the model. And yeah, these neural networks are like always meant to be retrained or to be fine-tuned or to be shared, and can get more data and can operate on this data and make small little adjustments. And this is what's needed to make those adjustments. You don't want this when you're going to actually deploy the model. You don't even want this bloat. This requires that my runtime has to know how to handle all of these different operations, yes, even though it's not necessarily being executed. And just the branching on its own, right, like requires a lot. And this is just extra bloat inside of the binary that we're deploying. So we don't want that. So we could actually freeze this, is, you know, a term that we've been overloading a little bit here, but in this context, freezing the graph simplifies it, gets it down. We see after freezing, so this is before, the graph is 12K. After freezing the model, which I thought I displayed here, it's only 300. I think there's a bug here. Yeah, but anyway, this model is much, much smaller. So 392. And yeah, this I think ends up being just a couple nodes. It like ends up being like five nodes. So I have to fix that. Anyway, back to this. So the smaller graph now obviously can be deployed anywhere. The other cool thing is, I'm skipping through a bunch of stuff here. So this is, if we predict with the larger model, we get approximately 6 milliseconds. That doesn't seem bad. This is, you know, linear regression though. It shouldn't be that slow. 6 milliseconds is a fairly long time. That's with the full, that's the full 32-bit. That's all of the weights being represented at 32-bit before quantization. And then afterward, we perform quantization using TF-Lite. We run a prediction, and it's 67 microseconds. And so this is simply by going from 32-bit to 16-bit. The next question should be, how much accuracy did we lose? And I hate to say, I don't have that data. I would need to actually go back and then run all these and give it a much larger data set, which I have not done. But based on the benchmarks that have been done by Google and by external third-party folk, TF-Lite does not lose a lot of accuracy because it's using well-known, well-studied quantization techniques, and you get you know, huge performance gains. So it should only be just a couple percent. Let me go back to the pipelines, and I think we will wrap it up. So okay, so this was the advanced pipeline. This is doing, let's see, this actually, I believe this one was doing hyperparameter tuning, and then here it's deploying, and looks like the service didn't deploy right. I don't quite know what's going on there. Gotta check that out. But yeah, basically this was the Kubeflow pipeline. From here. So this was advanced Kubeflow, and let's see if this runs. Did that actually run? Oh yeah, so this service is actually there. Looks like maybe just a UI bug or something, but we passed in a sample. So this was a Kubeflow pipeline that trained and was deployed. And then, yeah, this ended up with a model being deployed, and we make a sample prediction. We pass in a picture that is a 6, and we actually got back a 6. So pretty cool. The other pipeline we were looking at was the SageMaker one. And this one's all green, all right? We actually did a training job, then we created, we prepared the model for either batch inference or for REST endpoint inference. And we were able to deploy both at the same time. And I think we could probably hit it. We have to get the name of